Okay, so you're good on the audio then, in and out?
Yeah, seems to be fine. Yeah. Well, you know, just by switching the laptop, we'll end up.
Well, this is
hitting
what all the
wall.
settings will change on you. You see,
Okay.
if you switch laptop mid-meeting also, right?
Yes. This is the problem.
There is a power bar right there for this, so that you don't trip too. See what I mean? You want to, or is it going to die on you if you do that, or?
The problem is also
Is it the adapter? Is it
the
too?
adapter is too bulky.
Yeah, it won't fit in there.
Okay, so probably it's better if I'm just sitting there. If somebody comes and gives a talk, yeah, it's better to give him some room.
So I would take this. Is your computer going to die?
Yes.
Take this and plug it in there so they don't.
Yes, but I'm saying that then I will just need to move everything. If somebody is coming with his laptop and gives a talk.
Okay, well, that's kind of up to you guys. I mean, it's the way that you're doing stuff. So I'm here to make sure this goes into your Zoom meeting, and you can hear your Zoom meeting.
Okay.
I'll come back in 10 minutes. And
Yes,
check on it,
thank
right?
Screen. Marcos. Yes, they are. It's noise. It's not possible to fix that door
and keep it open?
Yes.
Yeah, we can.
Yes. Okay. So probably we should start. Okay. Okay. Hey. Yeah. Is working that? Okay, we cannot move this. Okay, so before starting, everybody that is on the line, can you hear me? Can you hear what happens here? What I'm saying?
Yes.
Okay. Thanks. Okay, so we still have some things to fix technically, but probably we are good to go, at least for the morning session. Okay, so hi everybody. I think that we should start. I'm Radu Timofte, and I'm the host of this workshop, the 8 new trends in image restoration and enhancement. I'll just minimize some things here. Okay, so yeah, it's been a long way. Already we have 8 editions of this new trends in image restoration and enhancement. And this year, actually, we had 14, not 8, associated challenges, like I wrongly wrote here. So are quite a number of interesting solutions and the interesting topics that were addressed in these challenges, but we'll see about them during this workshop. Okay, so we have our webpage that is containing up-to-date details and other pointers to the materials for the papers in this workshop. and also extra details about the speakers and talks that they will provide today. Yeah, unfortunately, what was intended to be an in-person workshop due to the big problems with the visa and whatever other logistics and traveling, we ended up having a hybrid setup. And yeah, we have an audience that is split both in person here in Vancouver Convention Center and also online. I'm leading a large group of organizers. Many of them are directly responsible on the challenges that were associated with this workshop. And here is the list. Okay, besides them, there were other people that are not in this list, but are co-authoring the challenge reports, and they helped to have a successful challenges and also a successful workshop. Besides these organizers, we relied on a strong program committee. We had, yeah, but those are like the numbers. So we are at the 8th edition of this workshop. And yeah, sorry for those that are in presence here, because they are seeing what I'm doing, like accepting the online participants. Okay, so we have 26 main organizers, 85 program committee members. So they assured the quality of the accepted papers. We totalized like 353 reviews. We have 77 accepted papers. All these accepted papers will have a poster presentation, and a subset of them will have also the oral presentation. We have, as mentioned before, 14 associated challenges, a large number of registered participants in the challenges that we organized, and yeah, 47 award certificates for the top methods, the top teams in these challenges. We have 4 invited talks and 9 sponsors. Here are the main sponsors of the entire workshop. We have also sponsors that were specifically for 1 or 2 of the co-organized challenges. So I'm grateful to Sony Interactive Entertainment, Modelscope, Reality Labs, and our administration back at Computer Vision Lab at ETH or the University of Würzburg in Germany. So here is a list of the associated challenges that we had this year. We had a long list. High resolution non-homogeneous dehazing, night photography rendering, real-time image resolution, bokeh effect transformation, 360 degrees, omnidirectional square resolution, image square resolution, the upscaling factor 4, light field image square resolution, image denoising, quality assessment for video enhancement, efficient image square resolution, image shadow removal, video colorization, high resolution depth from images with specular and transparent surfaces, stereo image resolution. So in total, we had 20 competitions for tracks, and most of them were also hosted by the CodaLab platform. So we are grateful for their support in running our challenges. Okay, yeah, we had more than 100 teams that competed in the final test phase, and a key element for our associated challenges is reproducibility. So the winners in these challenges were checked for reproducibility. Their solutions were verified. The top ranked teams, those that participated also in the challenge reports, submitted both sources and fact sheets describing their solutions. And typically we addressed real-world scenarios in our challenges. Okay, so we have 47 award certificates. Yeah, we somehow refrained ourselves from giving too many certificates. We just focused for the top ranking teams in each of the associated challenge, and the runner-ups and eventually second or third place awards. Okay, and there will be some money and product prizes that will go to the top ranked participants in these challenges, especially to the winners. As we are still processing some sponsorships, okay, I will not mention here exactly what those were, but there will be those top teams will be contacted by email. And yeah, the certificates will have also a PDF form and will be posted on the webpage. So big congrats to all the top teams that participated in our entire 2023 associated challenges. Now, we have 77 accepted papers, and these accepted papers have poster presentations. There are two poster presentations, two poster sessions. One is at noon, and another one is in the evening. And this concerns more those that are in person. The posters, the physical posters, should be placed and removed in each of the two poster sessions using a different poster panel ID, like provided on the webpage of the workshop. So on the webpage of the workshop, there is a list of the papers in this workshop, and you'll find there some ID that is for the noon poster panel and another ID that is for the evening poster panel. So all the challenge reports and the papers that are describing the top methods have in addition oral presentations. And yeah, we have a little bit of mix because many of the top participants were from China or from other countries that experience some visa and traveling issues. Okay, so a subset of regular papers, because we have also regular papers, like a good body, I think around 30, have in addition oral presentations. Okay, we have 4 invited speakers, and they are Professor Fahad Khan, Professor Ming-Shuai Yang, and we have the Dr. Rakesh Ranjan and Dr. John Barron. Rakesh and John, they are representing the industry, Meta, Reality Labs, and Google, respectively, while the professors, obviously, the academia. So this will be the talks about burst image restoration and enhancement. Will be at 10 a.m. Local time here. Then in the afternoon, we'll have the computational mixed reality talk by Dr. Rakesh Ranjan. And we'll have also the anti-aliasing neural radiance fields by Dr. Barron. And the last, not the least, talk will be provided by Professor Ming-Shuai Yang about learning to synthesize image and video contents. Okay, so once more, I thank to our sponsors for supporting this workshop and challenges, and a little bit of advertising. I'm just making you aware about the upcoming 9th edition of NTIRE workshop and challenges that will be planned for the next year, CVPR. Then we have the mobile AI workshop and challenges. By the way, this workshop will be tomorrow for this CVPR 2023, but also we have a plan for the next year. Then we have the workshop and challenge on image compression for the click, and is planned for the data compression conference this next year. Then advances in image manipulation aim that will be next year in conjunction with the European Conference on Computer Vision. Okay, before starting with the presentations of accepted papers and reports, just a little bit of advertisement. I'm still building my team at University of Freiburg, and yeah, if you have students that are interested in joining or already PhDs that are looking for postdoc positions, then yeah, please just feel free to share this information. Okay, so this is like an overview, and now I will switch to our first challenge report. So Marcos, will you come? Okay, so now I'll just
sensor. It collects a lot more light. So this is only possible through the capabilities of doing edge image processing, edge ISP networks. So we developed this as well, which is end-to-end ISP, which can correct optical aberrations, demosaiking, denoising, super resolution, the full image restoration pipeline that can run on a phone. Just as a quick example, even before we apply it to novel optical design, we can apply it to existing smartphones. And this is on an Android phone today. Left is the default ISP, and right is to a neural network. So we get a big improvement. This is some more examples comparing a Samsung S22 Ultra flagship, 100+ megapixels on the left, they claim, and then we have a 50 megapixel Android phone at half the price running in our network, and it actually outperforms it. Super resolution example compared to the shipping one pipeline. And then we have a demo running on an iPhone 14. Default processing on the left and network on the right. It runs on the phone. We've got a demo of that running on the phone, showed you in the break if you like. So one of the things you can see is we get lots more color detail, fine detail. This is because we're doing mosaiking, convolution, aberration, retouching, all running on the phone from the raw images. A lot of fine color detail, presence, and fine texture detail as well. So we took that approach and then we applied it to this novel lens architecture we made. These anamorphic lenses compress the image, so we have to correct for some special aberrations that come up and then unstretch it in one direction. So the result is we get a great image form. A little bit about how this works. Compared to the typical smartphone lens on the left and our architecture on the right, you can see that's kind of to scale. We collect a lot more light. This edge correct the aberrations that we get, as I said. And overall, we can reduce the cost of a smartphone camera by replacing, say, 3 lenses with one very high quality one. So to make this work in training, we have to model, simulate, measure the PSFs and the optical system, and then we train neural networks to compensate for that. A couple of benefits we get, obviously, even more improved resolution compared to the iPhone on the left. And then natural optical bokeh is a key thing we have here. So you can see this is not a portrait mode type effect on the right. This comes out from the lens itself because we have a larger aperture by the center. The foreground is naturally segmented from the background. Zooming in here, you can see compared with the portrait mode on an iPhone and our prototype on the right, we get the natural blur in the background, but also like a fine hair detail is well separated, which is very hard to do methods rely on, say, segmentation, depth estimation on the left. Another example showing the detail and the bokeh in the background, fine hair detail zooming in. So with that said, what motivated us to come up with this bokeh challenge? The fact that we get this natural glow in the background. There's an interesting fact is because we have this stretched anamorphic design, the actual bokeh we get is elliptical, as shown in the top right there. That's actually, some people say that's cinematic. See a lot of Hollywood movies with anamorphic lenses. Those are very expensive lenses. The reason no one put them in a phone yet is because they have many elements, they're very well corrected. We actually enable it on a phone because of the networks, but needless to say, this optical elliptical bokeh is a feature of the lens. But maybe someone wants to have a regular looking circular bokeh. So we thought, is there a way to transform that and maybe make a more circular bokeh? And we thought more generally, actually, sometimes you might have an image, say, from a DSLR or a lens where you have a natural depth of field, but you want to make it look like a different lens. And we had a look, no one had really worked on this problem before. So we thought, why not propose a challenge? which is transforming the bokeh from one image to another. Not going from sharp image to blurred image, changing the look. And blurred image, it's a different lens, so you have a different characters where you want to photograph. So I'll hand over in a minute to Marcos. Last thing I just wanted to say, workshop, come talk to myself or Manuel here with me. We have a poster as well and demos we can show you and have the results. So thanks and Marcos.
Thank you so much, Tom. Really interesting, right? So now we have to go over the actual hosting colorization. Most movies that you see out there, actually, there are theories that can move movies because of so it's a very interesting problem for the professional photography community, and we wanted to solve it together. Now, what is this challenge about? First of all, rendering both is an important problem. But controllable both is not explored. You know how to render from all important image. You know how to render Bokeh at stick nets. So in this challenge, we focus on so we introduce a new data set, cameras, and setups. And we aim to design models that can aid the Bokeh effect in the background, having the foreground function. Now, you can read all the details about the data set, but now here I will just cover it. So we use two DSLR cameras, two 50mm lenses, at 3 different aperture setups, and most of the training data is synthetic. We apply PSFs estimated from the camera, courtesy of class, and we apply those space-varying PSFs, generate a large amount of synthetic data, and train deep learning models. And then we evaluate the methods on 200 images that include synthetic data. So, okay, so here you can see in the first row a couple of synthetic images. In the second row, a couple of real images. Yeah. And here, something very interesting because we saw for the exact same region the effect of two different lenses. So two different lenses, two different Bokeh styles, and that's what we want to learn how to model. The complete benchmark is based on the paper, so you can check. We have plenty of methods. This is just the summary table. And kind of the results show that models can grade on synthetic data. They can emulate perfectly the lens behavior, but on real images is quite tricky because the complexity is orders of magnitude. But still, the perceptual quality is quite good on real images. Now, in order to solve this problem, we designed an open network, and it's a paper titled Efficient Multi-Lens Bokeh Effect Rendering and Transformation. Okay. And in a nutshell, what we do is design a model that can produce both in a controllable manner, so it is a state-of-the-art solution for controllable. The way we design this network is using nav blocks, very trendy paper nowadays, NavNet, and we incorporate into these blocks the lens information and position encoding, which really helps for this problem. The network is quite small, it's 1 million parameters and very few flops for high-resolution images, so I'm sure you can deploy it on phones, hopefully. And it's in an end-to-end model. We will use either depth maps, either segmentation maps to solve this problem. And these are some results from our model. On top, on a real image, how we are able to edit the background and emulate a different lens with respect to the inner lens that we use. And the second row is just the same synthetic image. As you can see, we can really protect the foreground and transform the background and apply this. Okay, so from this challenge, we conclude that it's a very interesting problem and there is a lot of work to do. It's the first study of this novel task, the transformation, together with a novel data set to solve this task. Most of the methods presented at the challenge are state-of-the-art methods for Bokeh. Either you want to render or transform these models. And we also noted, and you can read it at the papers, limitations of the methods on real images that probably we will tackle, hopefully, edition next year. There are multiple challenge papers from different teams, and I think we will have now a presentation from one of the teams that ended up on top. And all these papers will have a poster session, so you can show up and ask questions. Once again, thank you to the organizers, the organizers class, and the organizers, the sponsors of NTIRE workshop. Do you have questions now here? Yeah, a couple of questions probably. So, yeah, so I guess we move to the next one. Yeah. Would you like to hear?
Sorry, we are still trying to fix the settings. Yeah. Okay, so the next presentation will be selective bokeh effect transformation. The authors provided a video. Okay, but first of all, let's see if NAFBED, the people from Samsung Research China, are here or not. You? Okay. Okay, so you have the video with you? Okay, but this is about selective bokeh, is not Samsung. Okay, if you have with you, will be perfect. Okay. So you have the video?
Yes, this is the latest video. So
This selective
you
video.
can
Okay.
play this.
Okay, but the question here was about the Samsung team, not your team.
Oh, sorry.
Okay, so I see no Samsung team here, unfortunately. Okay, then we'll just move to the presentation from. Okay, selective bokeh effect transformation, and this is a work from Huazhong University of Science. Yes. Okay, of Science and Technology and Nanyang Technological University. Okay, I will run this pre-recording, and one representative is here, and I suppose also some of the authors are online. Okay. So I will restart because the people on online who are not able
Video,
to see.
we will introduce our work, Selective Bokeh Effect Transformation. Bokeh effect transformation is a novel task in computer vision and computational photography. It aims to convert bokeh effects from one camera lens to another. Typically, the transformation contains two aspects, lens type and blur amount. To facilitate blur amount transformation, we define a new concept of blur ratio. Before this, let's first introduce the defocus map, which reflects the blur radius of each pixel. The defocus map is related not only to camera parameters such as focal length and f-number but also to scene depth and focus depth. The blur ratio is then defined as the ratio of the target defocus map and the source one. Since the scene-related parameters are identical for the source image and the target image, the blur ratio is only related to the camera parameters. Under the condition of the constant focal length, the blur ratio can be further simplified into the ratio of the source f-number and the target f-number. Below is an example for a better understanding. In the following, we will introduce our framework in detail. We first predict an alpha mask of the focused object in half resolution by AlphaNet, which helps to preserve the sharp boundaries of focused objects in the transformed results. We then concatenate the source image, alpha mask, as well as two auxiliary maps before performing bokeh effect transformation. The first auxiliary map is a two-channel coordinate map for cat-eye encoding, because the shape and the direction of bokeh balls differ in different positions. The second auxiliary map is a two-channel one-hot map, which represents the lens type of the source image and the target image. Since there are only two lens types in the challenge, we set 0 for Sony lens and 1 for Canon lens. To learn the transformation of blur amount, we design a feature selection and integration strategy. Specifically, we apply 7 parallel phi nets with the same architecture to extract the multi-scale features, which corresponds to 7 different blur ratios existing in the dataset of the challenge. During inference, we can integrate the features of 2 neighboring phi nets, so that we can obtain the features with arbitrarily interpolated blur ratio. Subsequently, we use 4 dynamic residual modules to obtain the final result progressively. The architecture here is borrowed from DRB-net, which is proposed in CVPR 2022. The above predicted alpha mask and the transformed image are both in half resolution, so we further design a simple refine net to upsample and refine the transformed results. The challenge introduces a novel dataset BETD. The training set contains 20K synthetic samples, and each sample consists of a source image, a target image, an alpha mask and camera parameters. The test set contains 95 synthetic images and 85 real images without target images and alpha masks. Here is the official results of the challenge. Overall, our method ranked first in LPIPS and ranked second in PSNR and SSIM, demonstrating the perceptually realistic effects of our rendered results. We also show some qualitative examples of our method. One can observe that when the F number of the source image and the target image is significantly different, the bokeh transformation effect is prominent. We further conduct some analytical experiments to demonstrate the necessity of individual modules as well as the generalization ability of our method. Due to the random image cropping during training, the network cannot perceive the position of the cropped patch and the cat eye effect cannot be learned without offering a coordinate map. From the table, we can observe that adding the coordinate map significantly enhances the performance. The visual results also show its effectiveness in producing bokeh balls with different shapes in different positions. We also analyze the feature selection and integration strategy. To verify that the feature-level integration is superior to the image-level integration, we compare the two strategies quantitatively. Note that the transformed results from F1.8 to F16 can be computed by integrating the results from F1.4 to F16 and the results from F1.4 to F1.8. Also, the transformed results from F16 to F1.8 can be computed in a similar way. The final results are consistent with our expectations. In conclusion, our main contributions can be summarized as 2 points. First, we define a new concept of blur ratio to model the blur amount transformation and unite the bokeh rendering and defocus deblurring tasks. Second, we propose a novel framework with a feature selection and integration strategy to tackle the bokeh effect transformation task with arbitrary blur ratio. For more details, please visit our GitHub. Thank you for watching.
Okay, so this was the pre-recording. If you have questions, I think the authors are present. Okay, so if no questions, then let's move on to the next presentation. And Shanman. Okay. So let's do something like this. Okay. What is your? I'm not. You're not there. No. Okay. Should I? Ideally, yes.
Thank you.
Hi, my name is Sean, and I will present. Just a second. I'm not muted. Sorry for that. My name is Sean, and I will present our work, high perceptual quality, JPEG decoding via stereo sampling. In this work, we wanted to tackle the problem of JPEG artifact reduction. This is a joint work with Guy Ochayon, Theod Rei, and our advisor Mikelad from the Technion. And the problem formulation is the following. A highly detailed image X is heavily compressed using JPEG, resulting in Y, which contain lots of blocking artifacts and lacks fine details. Our goal is to restore a sharp image with fine details. And as JPEG compression is not invertible, there are many possible valid solutions. So we want to sample solutions stochastically. Each could have been the source of Y with rich and diverse details. Mathematically speaking, we have two goals. The first one is that restoration should be indistinguishable from natural images, meaning that the divergence between the distribution of restored images and real images should be zero, leading to perfect perceptual quality. Second, the restoration should be consistent with the measurements, meaning that applying JPEG compression to the restored image should produce exactly Y. Please note that Blau and Michaeli showed an inherent trade-off between any distortion metric and any divergence between distributions. For example, MSC and KL divergence. This means that any previous method that incorporated MSC, L1, or similar losses necessarily compromised on perceptual quality. This can be seen here where an MMC estimation is overly smooth compared to the real image. Moreover, it was shown that the posterior is the only distribution with perfect perceptual quality and consistent restoration. So theoretically, optimizing a GAN loss, while constraining our solution to be consistent, should be enough. Indeed, a prior work did exactly that even before the theorem was stated and proven. For example, given a highly compressed image from ImageNet, the work by Bat and Michaeli followed the theory and was perfectly consistent, but for some reason, the image lacked in perceptual quality. As a spoiler, this is what our perfectly consistent method can achieve on the same image. So, what is the gap between theory and practice here? Remember our limitation. First, we have networks with limited capacity. Second, a highly non-convex loss surface. Third, a finite size datasets, and finally, non-optimal optimization procedures. So we can't really expect to converge to the true posterior, okay? This makes us ponder, how can we come closer to the posterior? And our solution is to make the consistency term a regularization one. We test the effect of different coefficients on the consistency and perceptual quality. And we can note that Bat and Michaeli requires perfect consistency during the entire training process, leading to high FID. And if we do not regularize by setting lambda to 0, we achieve great perceptual quality with terrible consistency. By increasing lambda, we become more and more consistent at the expense of perceptual quality. By carefully annealing lambda, we achieve great FID with great consistency. And finally, as a post-processing step, we apply projection to achieve perfect consistency at a minimal damage to the FID. We compare ourselves to state-of-the-art JPEG restoration algorithms such as SwinIR and QGAC. And currently, we are leading in terms of perceptual quality across all compression levels, while being perfectly consistent as Bat and Michaeli were. Here are some more results of a highly compressed image, comparing to Bat and Michaeli and our restoration. And again, a highly compressed image, comparing again to Bat and Michaeli and QGAC. And please note our restoring fine details while being perfectly consistent. And for more theoretical and empirical results, please come visit us at the poster section. And if the time allows it, I would love to take questions. Actually, we decode the image 2 pixels of space, and we use the quantization table as a guidance to update our weights during the time. Thank you.
Next. Okay, so the next presentation, we have the second challenge report on a light field super resolution, and I think that the organizers are online, and they provided a video.
Hello, I'm Yingqian Wang from National University of Defense Technology. It is a great honor for me to make an Yingqian Wang from National University of Defense Technology. It is a great honor for me to make an online presentation of the first light field image super resolution challenge on NTIRE 2023. Recently, light field imaging has gained much attention in both academic and industry fields, and various kinds of light field cameras have been developed, such as litro and retouching, as well as camera arrays. Light field cameras can capture both the intensity and directions of light rays, and record 3D geometry in a convenient and efficient manner. By encoding 3D scene cues into 4-dimensional light field images, the image resolution can be enhanced by exploiting both spatial and angular information. In recent years, remarkable progress has been achieved in light field image super resolution, and various deep networks have been developed. For light field images, how to effectively incorporate both spatial and angular information is important but challenging. To develop and benchmark light field image super resolution methods, we host the first challenge on the NTIRE 2023 workshop. This challenge aims at establishing a new benchmark for light field image super resolution, and aspires to highlight specific challenges and research problems. This challenge employs the widely used and publicly available light field datasets as training set, and proposed a new light field dataset called NTIRE 2023 for both validation and final ranking. The popular bicubic degradation is used to generate low-resolution light field images, and the objective of this challenge is to make the super-resolved light field images as faithful as the ground truth high-resolution ones. This challenge provides a PyTorch-based open-source and easy-to-use toolbox called Basic LFSR to facilitate participants to quickly get access to this task and develop their own models. The Basic LFSR toolbox provides a complete pipeline to develop novel methods and integrates a number of existing models. The codes and checkpoints of each model are released, and a comprehensive benchmark is developed. The quantitative results of each method are listed, and their original results are also released for research purpose. This challenge consists of two phases, including development phase and test phase. In the development phase, the participants can download the validation set, apply their models to the low-resolution light field images, and submit the results to the validation leaderboard. In the test phase, the participants are required to apply their models to the released low-resolution test set and submit their results to the test server. The solutions will be ranked according to the PSNR results achieved on the test set. In this challenge, totally 148 participants successfully registered, and 11 teams have submitted results with PSNR scores higher than the baseline method light field internet. Here is the final rank of the challenge. Note that the winning method achieves 1 dB PSNR improvement over the existing state-of-the-art method Disentangle SSR, which significantly improved the state-of-the-art in light field image super resolution. We briefly summarize the common trends and useful tricks in this challenge. For architecture design, 6 of the 11 teams adopted Transformer as basic architectures, while the other 5 teams developed their networks based on CNNs. That is, Transformers are increasingly popular, but the well-designed CNNs can also achieve competitive SR performance. For subspace division, 7 teams adopted the disentangling mechanism to divide the 4D light fields into 4 2D spaces. 3 teams possessed features in spatial and EPI subspaces, and 1 team learned light field image super resolution in spatial and angular subspaces. It shows that spatial and EPI subspaces are quite important for achieving competitive SR performance. For data augmentation, random flip and rotation was widely used, but some advanced data augmentation approaches, such as cut blur and RGB channel shuffling, have not been adopted in this challenge. Finally, data ensemble and model ensemble were adopted in several solutions to boost the SR performance. There seems to be a considerable room of further performance improvement. The challenge report is available online and can be downloaded via the bottom link. Please refer to our challenge report for more details. Finally, we would like to present our thanks to the sponsors of the entire workshop. That's all. Thank you.
Okay. So this was the presentation. The first authors, the main organizers are here. NTIRE is here. So do you have any questions? Okay, so first thing first, let's see. Can you say something, NTIRE? Just to make sure that we can hear you.
Hello, everyone. Hello, Dr. Timothy. It's a great honor to make a presentation at NTIRE workshop. And this is my first time to take part in an online worldwide meeting. Okay, let's give time to the championship to introduce their solutions, right?
Yeah. Okay. So, yeah, if there are questions, he could take now. Otherwise, we'll take it offline. Okay. So, thank you, NTIRE. I will just probably proceed with the winner of the challenge. Okay. So, yeah. So we have a video provided by Yao et al. From Beijing Jiaotong University, and they are one of the winners in this challenge. And I will just play that.
Hello everyone, the title of our paper is Spatial-angular multi-scale mechanism for light field spatial super resolution. The light field images can be mathematically represented as LXYST. Two of them represent the spatial domain and the rest two represent the angular domain. As early devices for light field capturing is too large and expensive for normal use, people propose a handheld pan-optic camera that can capture light field in one shot. However, as a hardware limitation, these kinds of images have much lower spatial resolution than traditional images and brought lots of difficulties in practical applications. Different from traditional single images SR, the view image light field are highly corresponded. As the API shown, the information from agency to view images provide more detailed information. As shown in this figure, we show the movement corresponding to the different disparity of pixels on the API. As view changes in one direction, pixels with small disparity values, labeled as blue, move slowly at adjacent angles, and green pixels have a large disparity, moving quickly in adjacent SAI. However, as red label shown, the size of traditional convolution kernels can only capture subpixel information from a range of disparity. On API, for small disparity, subpixel information needs to be extended in the angular dimension, and for large disparity, it needs to be extended in the spatial dimension. This is our network structure for a given low-resolution light field image. The interaction between light field views is performed by the CACSID MDI group module to obtain image high-frequency information. Finally, the upsampled high-frequency features are summed with the low-frequency features to obtain the final results. One of the MDI group modules consists of several multi-dimensional interaction blocks. The main idea of MDIB is to untangle spatial and angular information by processing different forms of LF images. Specifically, we parallel process SAI, MACPI, and API through 4 branches. MSPB uses multi-skill operations to explore the differences between views to achieve accurate interpolation. We use different dilated convolution kernels in the spatial domain and angular domain to obtain richer subpixel information. For the experiment, we use 5 public datasets for training and testing. We compare our method with different light field and single image super resolution methods. Our model achieves the highest PSNR SSIM on nearly all datasets in both tasks, especially on the small disparity datasets EPFL and INRIA. Our method outperforms the other methods with more than 0.37 dB and 0.29 dB. Here we show the SR results. As shown, the textures are recovered accurately using our method. We also compare the API of super resolved images. Our method can perceive a larger range of subpixel information so that the geometric structure is well preserved in final reconstructed LF images. In addition to the above model structure, we propose a shear ensemble approach. First, we downsample the image and apply the shear operation based on the present disparity. The pre-trained model is used to upsample and the shared image. These outputs are then shared back, using the specific disparity to generate image group as the input. Usually, the model is able to recover better for a specific range of pixels. So by super resolving the skin's image under different disparities, there is some complementary information between these images. Finally, we incorporate a network to enhance the accuracy of the results. This is all the content. More details you can get through the paper. Thanks.
So this was the presentation provided by the authors, and that the authors are online. So if you have any questions, you will just
Excuse me, Professor. I have a question regarding this presentation.
okay.
Mr. Gao, you said that in the can anyone hear me?
I can hear.
Okay. Mr. Gao, you said in the proposed method, you used the deleted operation in the spatial dimension and the angular dimension separately. I have a question that why not performing the deleted operation in both dimensions simultaneously?
Thanks for your question. We think that perform the deleted operation in both dimensions at the same time can't get more sub-pixel information well. For EPS structures, it is different from traditional images and usually contain spatial information and angular information. It is representation of the intrinsic relationship between two dimensions. And if we perform deleted operation in both dimensions, this operation is actually very similar to that coupled without expanding the convolution kernels. And the sub-pixel information on the spatial range can be captured by both convolution very similar. The pixels that they are directly dealing with are on the same lines on the EPI. Although this operation can process information further away from the center pixels because of expansion operation. We are more considered with the questions of sub-pixel information for different disparate pixels. So we implement these structures in the final.
Okay, thank you. And dear Professor, the championship, the author of the championship is participating this conference online, and he is ready for the presentation.
Okay, so please. Okay, so if you are online, then you can give the talk.
Okay.
So please
Hi.
just-
Yeah. Hi, Professor. Can you hear me?
Okay, so can you share your screen? You have a material?
Yeah, I can share my screen, but I have no
Okay.
permission.
Okay. I'll make you propose. Okay.
Oh,
so
I
you
see.
can
I
share
can
now?
see it. Yeah. Well, can you see my screen? Okay. Wow. Oh, okay. Sorry for the late participating in this session. And
Okay, so just
okay.
remind yourself that you have 5 minutes. Okay.
Okay. Oh.
Okay.
Hi, yeah. Hi, everyone. I'm honored to share our work on light field super resolution track dist EPIT enhanced disparity learning for light field image super resolution. And this work is finished by Jing Kai, Agli Yang, and Gao Mingzhi from Beagle Corporation, and Guo Xia from Peking University, as well as Wei Zeqiang and Zhou Xiuzhuang from Beijing University of Post and Telecommunication, and the Global Explorer. And firstly, as we all know that the light field camera could capture all of the information in the entire environment by processing this data, we could realize the depth estimation and commonly used in photography, virtual reality, and augmented reality, and etc. However, since the limitation of the light field camera, the image made with very low resolution. By using the light field super resolution techniques, it could further expand the resolution to the more large size. And refer to the prior works in dist SSR. It mentioned the multi-view of light field images in different viewpoints. The first view is the SAI sub-aperture image. This spatial image is captured by different sub-cameras. And for second view is the magpie. SAI reorganize according to their angular location to generate a micropixel like this one. And the third is the EPI view. The image projection vertically or horizontally and reflect disparity more details. Like this image, we can see the horizontal, the views, sub-views into groups or one picture, and the vertical images. Also, recently, there are some methods has proposed like CNN-based networks and transformer-based works. CNN become mainstream architecture in recent works due to its strong capability of attracting the local spatial features. For example, the dist SSR conducts various count-based attractors to distinguish light field images into different subspace for feature attraction. But the CNN-based network are able to handle large disparity since it lacks long-range modeling ability. However, but the transformer-based works could based the long-range modeling ability and applied on various low-level vision tasks. For example, the recent work like DPT, LFT, EPIT adopt transformer block architecture to modeling long-range dependency. Unlike to capture spatial feature adjacent correlations as CNN does. So in this work, we have initial motivation to how to combine those two structures into one network to utilize the CNN-based method, attract essential spatial features adjacent angular correlation, and also use the advantages of transformer-based method to modeling long-range disparity. As we can see in this picture, the dist SSR do not modeling well in this area, and the EPIT do not modeling this area, but our proposed makes the architecture with CNN-based structure and the transformer-based structure could modeling it well. So let's see our proposed architecture. Our network with combined with three modular. The first is the non-local correlation modular, and the second is the local correlation modular, and finally is the hierarchy fusion modular. The first non-local correlation modular consists of a series of transformer-based block inspired from the IPIT method, and each block combined with the horizontal transformer block and the vertical transformer block by using the EPI view to attract the long range views to realize or to know more content in the long range, and also all of the features to attract by the non-local block and feed into the local correlation modular. Note that the local correlation modular is inspired by the dist SSR method, so it received in the magpie view in this image views. So feature in magpie view and feed into the local correlation modular with the spatial branch, angular branch, horizontal EPI branch, and the vertical EPI branch. And all of this branch and all of this block is for convolution structure, so it can strongly to attract the local feature, has a strong ability to extract the local feature. Those two modular has a characteristic is all of them with the upsampling block. So transform a non-local correlation modular to reconstruction super resolution images, and the local correlation modular reconstruction upsampled images, and all of them to fusion in this modular. This modular is very important because it can reveal the advantages for different branch. And we can see these images. The hierarchy fusion is consist of the bicubic upsampling and the non-local correlation branch result and the local correlation branch result to get a final result. As we can see in non-local correlation branch based on the transformer-based block, it can modeling well in this area, but SIM-based network do not. And we can see when SIM modeling well in this area, transformer-based network do not. So combine these two advantages, our network can modeling well in these two areas to local correlation area and the long-range content. Okay, and also we exploring the impact of the model size and the model order for the supergeneration result. By increase the network channels, we can see it can significantly improve the accuracy of model. For example, the dist SSR channels from the 60 to 64 to the 1060, and the PSNR can improve the 0.29 dB. And for EPIT transformed channels from the 64 to 180, the PSR improved from 0.18 dB. So the important question is if our network be better due to from the promotion of the flops. So we compared with this line and this line, we can find even with the same flops, our network with better performance. But we also try to improve the EPIT method, but it has reached the maximum memory in one single GPU in one samples. So it just to achieve less hours result. Also, another question is if we can swap the modular order, fit data into count branch, then transformer branch, and we try to this experiment, the performance dropped by 0.12 dB on average, dropped more on data with large disparity. This we analyze because the convolution first strategy would lose the long-range disparity information. Also, because the limitation, the memory, we need to implement a chop operation for inference. To avoid the disparity problem of patches on different sub-aperture images, we proposed the operation of position-sensitive windowing method. For example, the left figure shows a windowing method with 0 offset and 0 padding, and the boxes on the border need to be filled with 0 value to form a complete patch, but it destroys the correct disparity. From this to this, there is not the true disparity. And also, as for PSW method, for border values, it backtracks to fill in the entire patch without introducing extra padding or extra views, so it can keep the correct disparity, like this one. And also, we compare the 4 kind of the different padding strategy to demonstrate our our PSW, our advantages for the PSW method. The first one is center offset with mirror padding, center offset with replicated padding. They are also disparity changed over border from the over border. And for another cases, zero offset with mirror padding and zero offset with replicated padding. The disparities changed over bottom right border. So the intrinsic sort is zero offset B. The result of zero offset is better than the center offset. The fact that the actual result is indeed it. And we can see the zero offset padding is better than center padding for preservation of disparity in top left corner. So it has a large promotion because it has less destroys on the disparity. And the replicated padding is better than the mirror padding because mirror padding has inverse the disparity. Yeah. So the PSW achieved the best result because it maintains original disparity relationship. As we can see for this EPIT. And also we can find the transformer-based method is more sensitive to those Vendeling method because they have some positional encoding modular to attract features. So for this challenge, we have do some data. We have some experiment setting. First is the data set. We use the 5 public data set.
Okay. Okay. It was supposed to be 5 minutes talk.
Oh, okay. Sorry.
Okay. So could you go and conclude? Okay.
The final result we can see. Our method have achieved the best result and using TTA technique and model ensemble techniques. So, thanks everyone in our team, Aguli Yang, Wei Zeqiang, Gao Minzhi, Guo Shan, and Zhou Xiuzhuang. And any questions can ask can access our GitHub repository, and we have released our code. So thanks everyone.
Okay, thank you.
Yeah.
So this was the winner of the challenge. So congrats.
Okay.
Okay, so I think we are like half an hour behind with our schedule. So if you have questions, just address them directly to the authors. They'll be more than happy to answer. Okay, now let's move to the next presentation. So thank you, Jihad.
Okay, thank you.
So again, so the next presentation will be about dehazing. That's my share. That's good. Okay. Everybody can hear. I guess everybody can hear. Am I right? Yeah. Okay. So thank you all. My name is Florin Alexander Vasmeanu, and I'm presenting and report over the non-homogeneous dehazing challenge. We work together with Lucian Cuți, Cosmin Cuți from the Universitatea Politehnică Timișoara and UCL. And of course, Professor Timofte, that's today's host. We're going to go through the introduction. We're going to say a little about the challenge data, the winner solutions, and about the results. Yeah, so the setup is quite clear. We have a light source, and
Of course, in haze, it's composed of water droplets. We have subsequent reflections, refraction, diffractions that are happening there. Usually consists of a loss of contrast in the low haze areas, and in the highly affected haze areas, it's loss of contents also. Yeah, so we have the image scene, and given the image scene, yeah, we're going to go with an image like this. Of course, lots of contents are lost, so we have to recover them. For the data, we have a paired data set consisting of 50 high-resolution image pairs that were acquired using a Sony Alpha 7 III camera, 24 megapixel sensor. You will have a professional fog generator. The size of the droplets is between 7 and 10 microns. So you can see for this outdoor scene, for example, yeah, we have a non-homogeneous haze effect in the scene. Of course, we hosted our challenge on Podolab, so we have to thank them for the support. In the first phase, we had the development phase, the training split of the 40 image pair was made public, and then the validation split of 5 image pairs, of course, public. Of course, in the testing phase, we had the last 5 image pairs, and the image pairs were part of the user study that we conducted to actually distinguish with the best results. Here we have some samples from the data set. I'm trying to move this ribbon, but it's not so easy. Yeah, so you can see we are focusing our work around the outdoor scenes with complex textures and quite vibrant colors. Sorry? Oh, sorry. Okay, so we are focusing our work around the outdoors scenes with quite challenging textures and colors. Now, of course, we have to congratulate the winners of the challenge because the quality of the results was very similar for the first 2 teams. We consider both of them the winners. The first team is the DWT HTCAN. They are extending their work in 2021. They were the winners of the challenge in 2021 with a similar solution. The solution, it's a GAN-based solution, adversarial training, and the generator uses two-branched solutions. The first branch is based on the frequency domain with R wavelets and fast Fourier convolutions. And the second branch, it's a knowledge adaptation branch based on the convext model. Yeah, the second solution that achieved very good performance in our challenge is the ITB Dehaze. Again, a two-branch solution using the swing transformer V2 and an image refinement branch on the other side of the model that's operating on full resolution. About the results, as you can see, it was quite difficult to distinguish between them in terms of SSM and PSNR. They were quite similar. Of course, in SSM, it's mostly same numbers. In LPIPs, again, very similar. The difference appeared a little bit in the mean opinion score after the user study. So here we have some quantitative samples of the solutions that were proposed. Here we have the inputs. You can see heavily affected images, heavily affected by haze, and yeah, you can see like the results for the top 10 solutions. So you can see like some degradation happening at least in this bottom right corner of the image, and at least for the second sample that we use here for evaluation, you can actually track how the models are hallucinating this little tree in the middle of the scene. Of course, the dataset being quite small, we observed pretty good effects. Some other teams also tried more difficult solutions, and yeah, with various results. Then, if you want to get the challenge data, the submission platform on Codalab is still open, so you can actually scan this QR code. If I'm gonna actually move this, yeah, and then if you have questions, feel free to ask. I'll try to take your questions, and I thank you all for attending and for being here, either physically or on Zoom. Okay, no questions.
Any questions? Yeah, yes. You want to present in person? Oh, okay. Take the video. Okay. Brilliant. This was the report, Dehazing challenge, and now we'll move to the winners in this challenge. Okay, we have okay, I will play for the winners their presentation, and the authors are here to take the questions.
Hello, everyone. My name is Han Zhou from McMaster University. I am very glad to present our workshop paper, Breaking Through the Haze, an advanced non-homogeneous dehazing method, based on fast Fourier convolution and convnext. I will introduce our work form the following 3 sections: introduction, method, experiments. In general, non-homogeneous dehazing is a quite difficult task due to 2 factors. Firstly, the distribution of haze is usually intricate and non-distributed, thus the recovery of structures and color is quite challenging, especially in some areas with heavy haze. For example, as depicted in DW Gain, which is the winner of 2021 Non-Homogeneous Dehazing Challenge, the limitation is that DW Gain cannot address severe hazy areas. Secondly, existing non-homogeneous dehazing datasets are too small. Only with these datasets, it is difficult for us to design deep learning networks to learn feature mappings between hazy and clean images. To tackle these 2 problems, inspired by DW Gain, we propose a 2-branch dehazing network. The first branch is designed to directly learn the feature mapping between hazy and hazy-free images. This branch is named as DWTFFC branch. Specifically, at each downsampling stage, we adopt the discrete wavelet transforms, which have been verified to help extract features from hazy pictures. In addition, in order to improve the perceptual quality of the dehazed results in the latent space of the network, we apply fast Fourier convolution residual blocks to capitalize on the global context. The second branch is the prior knowledge branch, whose purpose is to use pre-trained weights to bring prior knowledge from quite large datasets, for example, ImageNet dataset, to assist our dehazing task. Res2Net is a popular pre-trained model. In recent dehazing papers, for example, both the winner of 2020 and 2021 Dehazing Challenge utilize the pre-trained Res2Net for knowledge transfer. Here, we use pre-trained convnext because its classification performances on ImageNet are much better than Res2Net. To verify our model, we conduct comprehensive ablation studies by devising and constructing 6 distinct networks, each featuring a unique combination of modules. The results are shown in the table. We can find that both DWT and FFC can help improve dehazing performance, and our proposed 2-branch network performs better than any single branch. In addition, we compared our model to another two-branch network, where the pre-trained Res2 weights are introduced. The increased performance between row 6 and row 5 can demonstrate the effectiveness of the pre-trained convext weights. Also, we have compared our method with state-of-art models quantitatively and qualitatively. The quantitative comparison results are shown in this table. Our model surpasses DW gain by an average of 0.72 dB for PSNR across these 4 non-homogeneous datasets. Here are some qualitative comparison results. We can find the color and structures in our dehazed images are more similar to the ground truth. For example, the rock in the first image and the grass in the second image. These are our dehazed results on the HD&H haze test set. We are very honored to be named the winner of the Dehazing Challenge this year, and we will take this affirmation and encouragement to engage in the future research. Thank you for listening. If you have any questions about our work, please send me an email to the following mailbox.
Okay, so this was the presentation, and we have a representative of that have questions. Okay, yes, please.
So, if I understand correctly, so your question is about asking about the key observation or the problem in the dehazing, right? Oh, it's most likely like the reconstruction result. So we usually observe that if we use the FFT or some like frequency domain knowledge, and then the reconstructed image can be like sharper and have more high frequency informations there. So we will say that it usually like they were pleasing or this effects. Or if you do not have this kind of things, you have some restored images, you will see like some of the edges are blurred or this kind of effects. And that's the main observation we use the frequency domain knowledge in the processing. There's another question.
Yeah, please.
This is one big issue of the using the frequency domain knowledge. So you will do the DFT or FFT. Usually, the transformation from spatial to frequency domain is somewhat low in running time. So this can be a like a future study you can solve, like making it faster. Yeah. Okay. A good suggestion. Yeah. Then we can do the next one.
Okay, now let's move to the next presentation. That will be also from the same laboratory, and also a winner in this challenge.
Hello everyone, this is a pre-recorded video for our paper titled as A Data-centric Solution to Non-homogeneous Dehazing via Vision Transformer. My name is Yang Liu, and this project was jointly done by Dr. Huan Liu, Liangyan Li, Zijun Wu, and my supervisor, Dr. Jun Chen. Let's start with a brief introduction about the non-homogeneous dehazing problem. It is challenging because of two reasons. First, comparing with homogeneous dehazing tasks, the correlation assumption between the thickness of the haze and the depth is violated. Secondly, the quantity of non-homogeneous haze datasets are still limited. One common belief is that models intend to encounter overfitting problems when training on such small datasets. Here are some examples of non-homogeneous hazy images provided this year. Knowing what the challenges are, we started to construct our solution from these three aspects. Firstly, we want to leverage the data from previous years as much as possible. we believe larger datasets should yield better results. Secondly, as we know that all 3 years' data combined are of just 120 pairs of images, we need to make use of the existing knowledges about the natural images themselves. Finally, all the knowledges we got should serve in the target dataset domain for achieving the best results. With all that being said, here are our methods. We started out by simply combining all 3 years' data together to train a model, and compare with just using this year's data training on the same model. Surprisingly, there is not much performance difference. This motivates us to compare the previous year's data with this year's data in detail, and found the obvious color discrepancy. We plot out the histograms of each RGB channel, as we can see in the left column. The distributions of each color channel are indeed very different. That explains why a simple combination of all the data fails to outperform training on this year's data only. We got an inspiration from the winners of 2021 challenge. They performed gamma correction to adjust the luminance of the data. Expand on this, we did the same trick, but on each RGB channel to realize more refined adjustment. From the left column to the right, we can see that the distributions of the data from 2020 and 2021 were brought closer to the data of this year. We call this data-centric engineering because it is in line with the idea of data-centric AI. Data-centric AI proposes that the researchers have put much more attention in developing models rather than engineering the data. In later slides, we will show how this data-centric engineering technique helps us obtain better results. This slide shows our model architecture. The pre-processed data is fed into a two-branch framework. We incorporate the swing transformer as the encoder part of the first branch. With an ImageNet pre-trained with initialization, we call it transfer learning branch, and this branch should extract subtle features of the inputs. In contrast, the second branch, the data feeding branch, is trained from scratch. It is responsible to complement the knowledge learned from the first branch and work on the domain of the target data. In the end, a fusion tail aggregates the outputs from both branches and produces dehazed images. Let's see the results produced by the methods we have just mentioned. The figure comparison is a qualitative ablation study on the data-centric design. From left to right, A is a result produced by training on simple combination of 3 years data. B is a result from training on this 3 years data, but with our data-centric engineering. And C is the ground truth. If we zoom in, we can see that after adjusting the training data, the results have more accurate color as the ground truth. Here, the color of the trees and the buildings in the middle are much better than those on the left. Numerical results also prove it. Here in the table at the top right corner, for both architectures we have tried, our data-centric design generates the best PSNR and SSIM. Actually better than other methods quite a bit. The table at the bottom right is the comparison between our model and the state-of-the-art. Our model is generally good. As we incorporate the swing transformer, the model complexity increases. This causes our design exceptionally better than the others on relatively larger dataset like OHAZE and NHHAZE23. In conclusion, combining a data-centric pre-processing technique with a swing transformer-based two-branch framework, our solution has a number 1 PSNR, SSIM, and LPIPS indexes. This further stimulates us to suggest the future challenge participants, treating the model and the data equally important. In the end, we appreciate all the help we have received during the competition. Especially, we thank the committee for designing and hosting the challenge. Thank you. Now, we welcome the questions, and Dr. Huan Liu will answer them.
Okay, so this was the presentation, and Huan Liu is here, and we can take the questions. I will start with our questions. So first thing first, what top solutions in this challenge are having quite comparable fidelity scores? The difference seems to be more perceptual.
on some cases. Okay, so how do you comment on that? Is it just a matter of the trading off or the kind of weighing that you are doing in your objectives?
Yeah, that's a good question. So yeah, actually, the first two these two solutions like produce a similar result in terms of the quantitative result, like the PSM and SSM, and have like very different visual difference. So I think for the two algorithm, they use like a different concepts. One is for using the frequency knowledge, and the other is using the something like the original like a two branch we proposed in the next like previous challenge. So our experience show that actually the algorithm for achieving a very competitive result in this challenge is not the main thing. So it's almost like a neural network. So you learn the mapping from the data. So our takeaway from this challenge is more like you need to work on the data. The data-centric the concepts is the key for our to success in this challenge, and you will see that in the report. The two our solutions have the like maybe I'm not sure the difference, but the main is it's like achieves very high competitive like PSM SSM. So I just want to emphasize the importance of data-centric concepts here.
Thank you very much. Another question that I have is, okay, you are top performer in this challenge on a non-homogeneous case. Okay, but have you tested on some normal uniform case or homogeneous case samples? Is working?
Yeah, this is also the other problem within the dehazing field. So usually, if you train a network on the homogeneous haze and test on non-homogeneous haze, it won't work. And if you train on the non-homogeneous haze dataset and test on the homogeneous, it will generate a lot of artifacts, the black holes and this kind of things. So it doesn't work. So this is also gives us a very like a parent queue to work on the data-centric things. So you will like make your data more like a real data set. And then if you any algorithm you design, it's just like a UNet, a simple UNet you train on it, and you can perform very well on the real world. So this is also, I think, one valuable things introduced by the non-homogeneous data challenge, right? It gives really some real data. So this is a very valuable data set in the dehazing field. Yeah.
So thank you very much. I think that, okay, I know that we have questions, so it's better to take offline or to the poster. Okay, thank you very much. This was the winning solution in the dehazing challenge. Thank you. The next presentation, let me check if the output for the presentation. I will just play the provided. The next presentation is okay, running now.
Hello everyone, I am Bilal Mijdira and I will present for you our paper, Streamlined Global and Local Feature Combinator SGLC for High Resolution Image Dehazing. The author are me, Anas Ali, and Anis Quba. We are from Rio 2 Lab at Prince Sultan University in Saudi Arabia. First of all, the goal of our paper is to remove haze from high resolution image without having to resize the input image or dividing it into patches. How we have done this? We proposed the SGLC architecture, which is composed of two successive blocks. The first is the global feature generator, the GFG block, and the second is the local feature enhancer, the LFE block. We use it as our customized loss function to mitigate spectral bias. This is the diagram of our architecture. First of all, we get the input hazy image, and we want to dehaze it following the global feature generator, and after that by passing it into the local feature generator to get the final dehazed image. Beginning by the global feature generator, we make padding, then we make a grid patching process. This is the algorithm of the grid patching. Once we get the grid patches, we pass it one by one to the dehazing model, which is trained on grid patches, and we constitute we reconstruct the original image from these patches. This is the algorithm of reconstruction. Finally, at the end of the GFG block, we get a first dehazed image. Here we use simple window patching, and we pass it into an enhancing model, which is trained on window patches. Once we get that, we use a smoother algorithm, which is the multiple overlapping patches smoother, explained in our paper, to reconstruct the final image from this window patches got from the EM model. At the end, we get a final image having a strong global and local feature. We use this customized function. First, we compare the predicted image with the grounded truth, and we compare the Laplacian pyramid of the predicted image with the Laplacian pyramid of the ground truth image, and we add a small constant for strong loss conversion. This is the result of our method. This is our method. This is when using the dehazing model without SGLC by resizing the input size into 1024 by 1024. This is a state-of-the-art method designed for high resolution image, and this is the grounded truth. First of all, the local by making the local experiment, we noted that every block is important in improving the result. Using GFG only improved the result by a big margin from the original U-former. Then by adding the LFE block but without MOPS, we get an improvement margin. And at the end, by using the full SGLC architecture, we get a better result. The process is better than the inverse process, which begin by the LFE, then the GFG block. And finally, these are the result in the challenge result in the non-homogeneous dehazing challenge. Our rank from all solutions was 5th. We were the 3rd in the PSNR, the 4th in the SSIM. But considering the solution that did not use extra data, we were ranked the 1st among 12 solutions that did not use extra data, both in the PSNR and the SSIM. Our limitation were noted in the LPIPS and the MOS metrics. Thank you for your attention, and your questions are very.
Okay, so this was another top solution from the dehazing challenge. Currently, I think we are quite behind with our schedule. So I will just, if you have questions, approach directly the author, the author actually couldn't come in person. So you can just use the email and send questions. Okay, now I will move to the next presentation that the authors provide video, pre-recording, and the authors are here. Take the questions afterwards. Okay, so actually this presentation is 10 minutes and was supposed to be 5 minutes long. Okay.
Hello everyone, this is Yuanzhi. I will give a presentation about our work denoising diffusion models for plug-and-play image restoration. This work is done under supervision of Dr. Kai Zhang, Jingmin Liang, Jiezhang Cao, and co-authors Professor Bi Hanwen, Professor Roden Timft, and Principal Investigator Professor Luke Van Gu. I will first show you some preliminaries about the denoising diffusion models, then our method and results. Denoising diffusion models aims to build the connection between a true data distribution, QX not there, here, and a simple data distribution such as Gaussian that we can easily sample from. And the key is to build a forward process which consists of capital T steps and under the Markov assumption here. And what we want to do is to model the unknown reverse process with p theta here, and we want to model each step of it as shown here. So with some derivation, we can write the objective as to minimize the chiral divergence between a known quantity qxt minus 1 given xt and x0 and the modeled distribution p theta. And with explicit parameterization of this p theta, we can simplify the loss function here as RT simple, which is the MOE loss between zt and d theta. Zt is the noise added between current state t, xt, and the data x0. D theta is our model with input of xt and the current time step t. In this case, we can consider the diffusion model as a denoiser, where given the current state xt and the output of the diffusion model, we can reconstruct the predicted clean image x0. In traditional plug-and-play image restoration, our target is to, given this measurement, we want to reconstruct x hat from this posterior probability. And most of the case, we can use the maximum posterior estimation, where the x hat is equal to max x with the sum of log p likelihood and log of prior. On the right, we have several examples of the measurement and the reconstruction. Now, I will show you how this MAP optimization problem is solved traditionally with HQS algorithm. With half quadratic splitting algorithm, the original target is split into two problems, the prior subproblem and the data subproblem. In the prior subproblem, it actually can be seen from this degradation model, and this is actually a noised version because the degraded operator is identity matrix. And then we can write the solution of this prior subproblem as dk equals to a denoiser of xk, and this one is the current noise level. And for the data subproblem, we have analytic solutions here for these specific degradation models here. If we can't find analytic solution, we can also approximately solve this data subproblem with one step of gradient, as shown here. And this image is from a previous work of US Arnett, which utilized this schedule for super resolution. And we find that there are several limitations of this work, such as the schedules are empirically chosen, and the denoisers here is discriminative. In this, and since we know that diffusion models can be considered as a denoiser, we want to introduce diffusion models into this plug-and-play framework. And what we get from diffusion models, first of all, we can get not only the generative power from the model, but also a well-defined sampling schedule, which could be more important in this case. And after we introduce the diffusion sampling schedule, we can turn to the original optimization problem into a sampling problem. That's our sampling framework. So in this slide, I will show you how we get our sampling framework as a combination from HQS algorithm and the DDIM sampling framework. The first line here is the one-step sampling of DDIM, which is denoising diffusion implicit models. And here we can construct our HQS one-step here. What we did here is actually we first estimate the current xt, x0 t with diffusion models as a denoiser. Then we solve the data subproblem to get the information from measurements. Then we can calculate the effective conditional noise epsilon hat. Then we can finish one sampling step by add noise back. That's direction point to xt. So to better illustrate it, we just what we did is upgrade the traditional HQS algorithm into our HQS-based sampling framework, and the algorithm, the whole process can be summarized in this algorithm. And the main difference from this algorithm and the DDIM unconditional sampling strategy is that we have extra data proximal subproblem in this purple color. This is an illustration of our sampling framework. At each time step xt, we first use denoiser from this noise image to get this smooth and clean image, and then we solve this data subproblem to get more information from measurement y, and then we add noise back to the next step xt minus 1, and by repeating this step capital T times or several times subsequence, we can get the final result x there. Now let's have a look at our results. First, have a look at the quantitative results. By comparing with several concurrent or the traditional plug-and-play based method and the other diffusion-based image restoration method, we find that our method is state-of-the-art performance and computed result on most of the tasks, such as Gaussian deep learning, motion deep learning, and spatial resolution. This slide showed the benchmark score on noise cases, and in this slide we have the performance of our method on the noise-based quantitative results. Yeah. On the FFHQ dataset, our method is still the best of them. Now let's have a look at some qualitative results. Here is the noise 4 times the spatial resolution, and we found that our method can have the reconstruction both vividly and faithfully to the measurements. For noise motion blurring, it's the same that our method can produce the most clear reconstruction. And for impending, we show that our method can reconstruct, can have diverse reconstructions, even for masks with 75% of the area masked. Mr. do you have reasonable reconstructions here, as mentioned in the last rule? And this diverse reconstruction can also be observed for super resolution tasks. Here, for example, we have 8 times and 16 times resolution with noise here, and we can have multiple samples. They are very diverse, and you can see these ladies have different ages and even gender different from the other samples, which is very interesting. That's all of our work. Thank you for your attention.
Okay, so this was the presentation. Unfortunately, we are quite behind the schedule, so I will invite you to address the questions directly in our course. Now, okay. We have 2 other works that will be presented by representative authors. Okay, and I will let him introduce the works.
Hello, everyone. My name is Vivatman. I'm here on behalf of Kalens. I was asked to keep this short. Today, my topic is about high-resolution synthetic RGBD dataset for monocular depth estimation. It's a bit different from what we have been discussing. So I'll quickly jump into it. So monocular depth estimation is basically when we try to generate the depth map of an image from just one image. The key contributions of our paper is basically 2. One is the synthetic dataset that we generated, and the other is we tweaked the model DPT model and made some changes to it, which improve the performance by quite a bit. So why we decided to generate our own dataset, because the existing dataset, there are multiple depth datasets which are Kitty, NYU, Midas, diode, but most, as you can see, the first 2 have a problem of low resolution, and the second 2 have a problem of being sparse. So how we decided to generate the dataset was basically we created a plugin for the game GTA 5, and we created about 100,000 synthetic datasets which contain different kinds of scenarios and different kind of weather condition, different kind of lighting condition. We segregate the dataset into 2 parts. One is the outdoor and other is the indoor. The depth range is about 0.1 meter to 10 meters. And for outdoor scenes, it is about 50 meters. So the changes to the DPT architecture is basically we propose that we add a feature module to it. So instead of directly inputting the image, we first extract the features of that image using ResNet 50. We also experiment with ResNet 101, and the results are good. The second contribution in changing the architecture is basically in the end we add a different kind of loss function which is called the attention loss function, which is mentioned in the paper. So these are the results. This column is the ground truth. This is the DPT output. These 2 rows are test data, and this is a real world image, so there is no ground truth for this image. As you can see, the proposed algorithm has much more texture in it as compared to the DPT. DPT kind of smooths all the objects in the image. So the adding more data basically has improved the texture by a lot. These are some quantitative results. Overall, we found about, on an average, we have 11% lesser loss than the original DPT also. And these are some of the references. So in favor of questions, yeah, sure. Right. So we did separate experiments on indoor and outdoor. We felt that the bottleneck was not the depth range. In our experience, we found that the bottleneck was not the depth range, but the data set itself. Being like the high resolution data set helped the transformer learn better instead of the depth range in the data. So this is a synthetic data set. If you look at these images, these images are generated from the game itself. So game in rendering pipeline, there is a thing called depth buffer. So we extract the bottom row is basically the depth buffer itself, and we do some. They don't give, though they give relative depth maps, but we do some transformation on it since we know the near plane and far plane, and we kind of compute the real depth map from it. Yes. Okay. Sorry. Can you go? Sorry. Right. So for example, if you have ever used, so there are lots of use cases for more textured depth maps. Basically, for example, if you have ever used backgrounds on Gmeet or something, you might find that there are some artifacts where your background is not completely blurred out. So if you have a more textured depth map, then you can kind of extract your face and extract more information from it better, basically. Yes. So Kitty depends on the data set, what data set you are talking about. Yes, this is 920 by 1080. I think for Kitty, it's the width is much higher than height since it's for outdoor scenes and captured. So maybe you can ask the authors. You can just email the authors. Sorry.
But it's one of the higher resolution data set as well. So it's the next step.
Sure. So the second paper is about the video super resolution and how we can create synthetic real world degradations in that super resolution. So just to give you a brief idea, super resolution is basically the technique of taking a low resolution image and converting it into a high resolution. So for the spoiler, this is the output of the our output. As you can see, the real basic VSR, which was the state of the art, had some problems with generated some artifacts in the letters, and the proposed method will kind of mitigate that. So the key contributions of this paper are basically we create a pool of different degradations, and when we randomly apply those degradations for generating this data set. So the degradations are divided into two parts: image degradations and video degradations. Image degradations are basically blur degradations, noise sampling, downsampling, and sensor noise. Blur kernels are being generated using a GAN called kernel GAN, and the sensor noise is generated using the cycle. There are few video degradations which are pixel binning degradations and MPEG compression. The pixel binning is basically taking the raw data from the sensors of the camera and then mixing the few pixels into a super pixels. So the noise from nearby pixels is blended into each other. The second contribution is the K-Lens VSR dataset. It contains 56 videos of 100 frames each, and it's about 1600 cross 1080. So this is just the definition of the degradations. This is the pool of degradations that we propose. There are two methods. We kind of randomly sample the degradations, and there is a predefined order of degradations that is applied. So in this method, this is the pool of degradations. These three are the blur degradations that are generated. This is the kernel GAN pool. These are other two pools. Then there are downsample degradations, pixel binning. The sensor noise, the Gaussian noise is added, and then we add compression artifacts. So this is the model. We use FlowNet to calculate the optical flow between the LT+1 and LT-1 low resolution. Once we have the optical flow of forward and backward, we change the unidirectional feature propagation to bidirectional feature propagation. And then we input it into a RDB net dataset for superset. So these are some of the quantitative results, and these are some of the qualitative results. So as you can see, in this bottom patch, the grid becomes blur for the TECOGAN and real VSR, whereas the grid remains intact for So this is just a video. That's it. Thank you.
Okay. So we have time for lunch. Yeah.
I'm sorry. I heard the question. So I'm just representing this paper. I'm not in the author list. I would highly recommend you can find the authors and you can email them.
Okay. So thanks.
Thank you.
Now we'll change a little bit of the schedule, and we have our invited speaker, Professor HTCAN. So what is your
Okay, so thank you very much. Thank you very much. Good morning, everyone. My name is Fahad Khan, and I will present today some of our recent results on burst image restoration and enhancement. So today, as we all know, that high-end DSLR cameras can capture images of excellent quality with vivid details. However, on the other hand, if we look into smart phones that are available these days, the demand for capturing high quality images as that of DSLR quality is increasing day by day. And as this popularity increases, the main goal of computational photography also goes towards generating these DSLR-like images with smartphone cameras. However, the physical constraints, as we all know, of smartphone cameras hinder this image reconstruction quality. For instance, if we have small cameras with a small sensor size, they kind of restrict the spatial resolution. And if we have small lens and aperture, that provides somewhat noisy and distorted images in low light conditions. And similarly, if we look around and have small pixel cavities, we also can accumulate less light, thereby yielding low dynamic range images. And to this end, existing single image processing approaches strive to restore or somewhat also enhance the image using some learned priors. And while they can generate natural images, they still kind of lack fine-grained details of the image content. And this is where burst image processing comes into the picture. So to alleviate these issues, burst or multi-frame photography offers a natural solution to single image processing by capturing multiple images of a scene in a quick succession. And it is now getting more and more popular because of the recent advancements in the smartphones, for instance, live photos. However, when capturing image bursts, the movement of the camera or somewhat the scene objects that are in the scene can lead to alignment problems when merging information from each frame. And this can result in some undesirable artifacts. For instance, if there is a boosting or blurring artifacts in the final out. And this is where the goal of burst image processing comes, that is to generate a single high quality image from this successive burst or degraded frames of the scene that is captured in a rapid succession. So there is a need to develop a multi-frame processing algorithms that are robust to these alignment problems and requires no special burst acquisition conditions. Okay, now when we look into the existing literature into burst image processing and enhancement, we can see that typically these existing techniques extract and align features of burst images separately, and then subsequently they later on try to fuse that information in a late fusion mechanism. However, we can note that this kind of a strategy can hinder flexible information exchange across frames and can also cause errors during the explicit alignment that are then subsequently propagated to the next stages of the whole pipeline, thereby negatively affecting the generated output. And looking into the literature, we can also observe that there are alternative approaches that uses, for instance, dynamic kernel predictions. However, the consequence of such a strategy is that this makes the entire network more bulky and sometimes can also face with some training instabilities. Okay, now to address these issues, we introduced a burst image processing approach called BIPNet that was presented at CVPR last year. And so the highlight of this proposed BIPNet is that it strives to align burst features implicitly following by an interframe communication using a mechanism which we named as pseudo burst mechanism, then also having an adaptive grouping upsampling scheme. So the key contribution here is as I said, is the introduction of this pseudo burst feature mechanism, and which strives to enable interframe communication and also feature consolidation. So specifically, if I talk about this pseudo burst, this is generated by exchanging information across frames such that each frame in the pseudo burst succession kind of contains the complementary properties of all the input burst frames that we have. Okay, and here is the holistic overview of our proposed BitNet. It takes an input raw image and then generates a high quality composite image, having three key stages. The first one is edge boosting feature alignment, and then the second one is pseudo burst feature fusion, and the third is adaptive group upsampling and module. So the first one, this edge boosting feature alignment module, strives to extract features, reduce noise, and then also remove the spatial and color misalignment issues that are typically encountered with the burst features. And then the second key component here, the pseudo burst feature fusion mechanism, then enables interframe communication and then feature consolidation. So this pseudo burst is generated by exchanging information such that each feature map in this pseudo burst now contain information, all the complementary information of all the actual burst image features. And then the third one is related to upsampling. So in contrast to the existing approaches, what we do is that we introduce an upsampling scheme to progressively increase the spatial resolution while also merging this multi-frame information. So this one here is example is only illustrative of the super resolution task. However, we performed experiments on different restoration tasks, including low light image enhancement and also denoising. Okay, now let's zoom in to discuss each of these components in detail. So as I discussed in the start, that one of the major challenges in burst processing is to extract features from multiple degraded frames that are often contaminated with noise. And they can also have unknown spatial displacements and can also suffer from color shifts. So, and these issues can arise due to, for instance, camera motion or object motion in the scene or lighting conditions. And therefore, it is essential to align this input burst frames so that the relevant pixel level cues can be aggregated in the later stage of the pipe. With this aim, to align the other images in the burst with the base frame. So now here in this presentation, I will mostly talk about with the base frame as the first frame for simplicity. However, it could be other frames as well. We proposed an alignment module that is based on modulated deformable convolution. And however, the key difference here is that in contrast to the existing deformable convolution that is not explicitly designed to handle this noisy raw data, we propose a feature processing module here called FPM to reduce the noise in the initial burst features. So our boosting feature alignment module consists of feature processing, and that is followed by the alignment procedure for feature alignment. Okay, now let's look into this feature processing or FPM module within this EBFA or edge-based boosting strategy. So here we strive to denoise input frames first so that it can facilitate easy alignment. That is kind of a pre-processing step before we can actually do the alignment. And it comprises residual learning, which is empowered by the global context information. So this residual learning allows abundant low frequency information to pass easily via skip connections. And since it is getting very popular these days to capture long range pixel dependencies, which extracts global scene properties, and we have seen it for other restoration tasks as well. In this module, we utilize global context attention named GCA that aims to refine the latent representation that is produced by the residue. Okay, now moving to the second main component of our approach, and just to recap to the motivation which I presented in the start, that existing burst image processing techniques typically separately extract and align features and usually employ a late feature fusion mechanism. And this has some consequences in the form of artifacts that can come in the final output. So in this work, what we do is that instead we propose a pseudo burst feature fusion mechanism that generates feature tensors by concatenating the corresponding channel-wise features from all the burst feature maps. So what happens then consequently is that each feature tensor in this pseudo burst contains complementary properties of all the actual burst image features. And we empirically observed that processing these inter-burst feature responses also helps us to simplify the representation learning task and merge the relevant information by decoupling the original image feature channels. Okay, so this is about the pseudo burst fusion module. Further, we also need to generate deep representations of that. And to do that, in this work, we use a lightweight unit architecture that extracts these multi-scale features from the pseudo-burst representation. So we used a shared bits in the unit and employ over this FPM module instead of regular components. Okay, lastly, the third component of our proposed BitNet, that is for the upsampling, and which is the key final step to generate the super resolved image from the low resolution feature maps. Again, different to existing burst super resolution methods that uses that performs upsampling in a single stage, for instance, a pixel shuffle layer. In this work, what we do is that we use information that is available in multiple frames to exploit in order to get a high resolution space. And to do that, what we do is that we introduce an adaptive and progressively merging multiple low resolution feature maps kind of a mechanism, which kind of utilizes effectively the available information in multiple frames in order to get this high resolution space. And specifically, it handles pseudo burst features in groups and then progressively performs upsampling. So we sequentially divide the pseudo burst features into groups of different groups, and then these groups of features are then upsampled with the upsampler that is on the right side. And this upsampler, what it does is that it first computes a dense attention map carrying attention weights for each pixel location, and then these dense attention maps are element-wise applied to the respective burst features. And in this way, at the end, we generate or produce the final high resolution output. Okay, now moving on to experiments. We performed experiments for different restoration tasks, starting from super resolution and then low light image enhancement and burst denoising task as well. And for the network parameter efficiency, all the burst frames are processed with the shared BitNet modules. However, we train separate model for each of these three tasks. Okay, for burst super resolution, we follow the instructions of the NTIRE 21 burst super resolution challenge. So here we performed two different experiments. The first one was performed with synthetic burst dataset, which comprises 46,839 raw bursts for training and 300 for validation. Here, each burst contains 14 low resolution raw images, each of size 48 by 48 pixels that are synthetically generated from a single sRGB image. And the burst SR dataset consists of 200 raw bursts, each containing 14 images. And to generate these burst sequences, the low resolution images and their corresponding ground truth high resolution images are captured with a smartphone camera and a DSLR camera respectively. And here each input crop is of size 80 by 80 pixels. Okay, so we trained this proposed network for 300 epochs on the training set and then evaluated on the validation set of the synthetic burst dataset. And here we have showing the results on the in terms of the image quality scores on the two datasets. Just to summarize the results, we observe our approach to perform favorably against existing methods in literature, and specifically, the proposed architecture achieves a PSNR gain of 0.37 dB over the previous best method, MFIR. And in case of real data as well, we observe a consistent gain over the existing works. And here are some qualitative results. We can observe that the super resolved image produced by our proposed architecture exhibit more sharper and faithful details compared to other algorithms, mainly due to the capability of reconstructing structural content and fine textures without typically introducing artifacts or color distortions. Okay, now to further show the effectiveness of our architecture, we also perform an experiment on the large scale factor. So we perform an experiment on ×8 burst super resolution. And to this experiment, we synthetically generate the low resolution and high resolution pairs following the same procedure as described in the synthetic burst dataset. And here are some visual results. So we can see that the approach is able to recover rich details even for such large scale factors as well without artifacts. And moving to the second restoration task, which is the image enhancement task. So here we perform, so basically given a low light raw burst, our goal here is to generate a well light sRGB image. And since the input is mosaic raw burst, we use only one level of our upsampling to obtain the output. And we perform all the experiments on the SID dataset that contains input raw burst images that are captured with a short camera exposure in low light conditions. And here are the results. So again, we observe consistent improvements in terms of different metrics over the existing methods. And if we look into the visual qualitative comparisons, the approach also is able to better preserve color and structural information in these examples. Okay, then lastly, going to demonstrate the effectiveness of the proposed architecture on the burst denoising task. So here the architecture processes the input noisy sRGB burst and obtains a noise-free image. So since there is no need to do the upsampling, the extracted features, the transpose convolution in the upsampler is replaced by simple convolution, with the rest of the network architecture is kept unmodified. So we performed experiments on grayscale and colored burst denoising datasets that are introduced in recent literature. And following benchmark experimental setup, we utilized 20K samples from the open image training set in order to generate the synthetic noise burst of burst size 8 and spatial size 128 by 128. And here our network is trained for 50 epochs for both color and grayscale burst denoising tasks. Okay, and here are the results. Again, for both color burst denoising and grayscale denoising, we observe consistent improvements in performance. One notable result here is the numbers with the noise parameter with the highest noise gain, here 8, which is unseen during the training. So this kind of also testifies the performance of the architecture on the noise levels, which is kind of a generalization of the network because it is an unseen noise during. Okay, just to summarize, we propose a burst image restoration and enhancement framework, which is developed to effectively fuse complementary information from multiple burst images, introduce an edge boosting alignment module that is robust to camera scene movements, and then a pseudo burst features to enrich multi-scale information and later progressively fused to create upsampled outputs. And we show experiments on 3 restoration tasks. Okay, now I will quickly move further. So while the proposed architecture, this BeepNet, which I just presented, shows potential of burst image processing techniques in order to reconstruct fine details, it is still computationally expensive architecture. And in addition to having this computationally expensive nature associated with it, another key thing is that these approaches only target the local features at a single level. So while they don't use the global information with multi-scale features in this work. So this is where our recent work, which we are going to present this week, comes into picture, named Burstformer. So Burstformer strives to incorporate multi-level local global burst feature alignment and adaptive burst feature aggregation. It is a transformer-based design that leverages multi-scale local and non-local feature for improved alignment and fusion. And it further strives to do interframe communication in the burst neighborhoods for information aggregation, and then subsequently progressively fuses it while modeling the burst-wide contextual information. And one notable characteristic of this approach is the flexible design that allows processing of bursts for variable sizes. And we again perform experiments on multiple restoration tasks. Just to give a glimpse of the results in terms of both efficiency, the x-axis and the image quality, the PSNR, we can see that the proposed Burstformer, while being efficient, computationally efficient, performs favorably compared to existing works in literature. Specifically to our prior work, BIPNet, the Burstformer yields improvements of 0.9 dB here, while having 47% fewer parameters and 80% lesser flops. And here is the overall pipeline of the proposed Burstformer for burst image processing. It has two main parts. The first one is enriched deformable alignment, and the second one is image reconstruction. So now, in contrast to previous works that employ bulky pre-trained networks of explicit feature alignment, what we do here is that we introduce this enhanced deformable alignment EDA module that handles misalignment issues explicitly. So overall, this EDA module strives to reduce the noise and extract both local and non-local features with a transformer-based attention, and then performs the multi-scale burst feature alignment and enrichment, which is not the case in the previous architecture which I presented to you. Okay, now in the image reconstruction stage, what we do is that we progressively perform feature consolidation and upsampling while having the access to multi-frame feature information at all the time. And in order to achieve that, what we do is that we introduce a no reference feature enrichment module. So this module, what it does is that it initially generates burst neighborhoods with the proposed cyclic burst sampling mechanism that are then later aggregated with our burst feature fusion. And one key difference, unlike the existing the pseudo burst which I introduced in BIPNet, here the proposed burst neighborhood mechanism allows flexibility and also enables interframe communication with significantly less computational overhead, which was kind of our objective when we designed this architecture. Okay, now again zooming in to discuss the design of these components. As I mentioned in the start, that this effective alignment of mismatched frame is a kind of an essential, as if this error arises in the start, it can also propagate to the later stages of the architecture, and that makes the reconstruction part, which is the second part of the pipeline, even more difficult to do. So this becomes our motivation of this EDA module, which employs a multi-scale design, where each subpixel shifts among frames are naturally reduced at a low spatial resolution using the multi-level hierarchical architecture, which kind of starts feature alignment from the lowest level and then progressively passes offsets to upper high resolution levels in order to help with the alignment procedure. And this EDA module further has two components. The first one is feature alignment, FA, and the second one is reference-based feature enrichment. Okay, now since these burst images are often contaminated with random noise, that kind of impedes in finding the dense correspondence some of the frames. So it is always a good idea that before we perform the alignment operation, we first extract these noise-free burst features by using this burst feature attention module, BFA here, which is built upon the existing transformer block, as in our previous work Burstformer that was presented in CVPR last year. So this block, this BFA block, unlike this BIPNet approach, here encodes both local and non-local context. And further, unlike existing attention techniques, this BFA module is efficient enough to be applied to high resolution. And then the denoise features from this BFA module are passed further for the feature alignment. And this feature alignment module utilizes a modulated deformable convolution to align features of each burst frame to those of the reference frame. Okay, now moving further. So here we propose a reference-based feature and enrichment module, which enables additional interaction of aligned features with the reference feature frame to generate more consolidative frames. So compared to existing approaches, which does this interaction only one time, here we are doing this interaction multiple times in order to do a further refinement based on the reference frame information. Okay, now moving to the last part of the pipeline, which is the image reconstruction. Once the burst features are aligned, high quality image is then obtained through this proposed image reconstruction process. And what we do in this image reconstruction process, so unlike existing approaches that are typically rigid to using a certain number of burst frames during alignment and fusion to operate on burst, here we propose an adaptive burst feature pooling mechanism that allows arbitrary number of frames to be processed. And these burst features are concatenated along the channel dimension, followed by a one-dimensional average pooling operation, which kind of enables us to adaptively pool the burst features as per the requirement. And in our experiments, we fix it to size of field. And then the pooled burst features, feature maps are then passed to this no reference feature enrichment module as shown here. So the key idea of this module NFRE is to pair immediate neighborhood frames along the feature dimension and then do this fusion of them using the proposed BFF module which I introduced earlier. However, here the key thing is that if we do this, it will limit the interframe communication to only the successive frames in the burst representation. And to mitigate that and to allow a communication for more than multiple frames, we introduce cyclic burst sampling that gathers the neighborhood frames in a zigzag manner. This is where the name this burst neighborhood comes from, such that the reference frame could also interact with the last frame as well as the intermediate frame. So this is something which kind of allows a much more richer information flow as well. And afterwards, the sampled neighborhood frames are combined along the burst dimension and processed with the BFF to integrate the useful information in order to produce a high quality output. Okay, again, we performed experiments similar to the BIPNet on 3 different restoration tasks. We kept the same pipeline, everything is the same, the data sets, the processing, everything is the same. Just the results here compared to BIPNet, our approach performs favorably. However, as I mentioned in the start, the key objective of the design of this approach was to be more computationally efficient. So these results are obtained while significantly making the network architecture more efficient. Here are some visual results for burst low light image enhancement. Again, we can observe some more faithful color and structural content that is preserved or retrieved in the proposed approach compared to existing works. Just to summarize, we propose a transformer-based framework named Burstformer for burst image processing. It is capable of generating a single high-quality image from a given burst of noisy images having pixel misalignments among them. It employs a multi-scale hierarchical module that generates denoised features encoding both local and non-local context, which is kind of we show helps to improve the results. And we also further fix the minor alignment issues by having a reference-based feature enrichment module that enables additional interaction of the features of each frame compared to the base frame features. And overall, this EDA improves robustness by yielding a burst of features that are well denoised, aligned, consolidated, and also defined. And then lastly, in the image reconstruction stage, we repeatedly apply the no reference feature enrichment and upsampling modules until we obtain the final image content. Some future directions, I think, in my opinion, and as one of the potential next steps would be to develop a reference frame selector algorithm, which adaptively selects the reference frames for a given burst rather than assuming that the first frame is the reference frame. So in both works, which I just presented, that was one of the scenarios that we kind of assumed. In addition to that, I think one of the next steps could also be to explore self-supervised burst processing techniques in order to overcome this pre-training of the synthetic data first, and then doing the adaptation to the new data. And then lastly, I think it would be interesting to also investigate the proposed modules in some other multi-frame applications such as satellite image processing or medical image analysis as well. So I would just like to acknowledge all the co-authors, especially Akshay Dudane, who is the first author of both papers, And then finally, please visit our poster sessions. We are going to present this Burstformer on Tuesday, and also we have another paper on burst image processing and restoration on Thursday. And if you have more questions, we will be very happy to entertain on our poster session. With that, thank you very much. And I will
We have time for questions. So, you are preparing some questions.
Yeah, sure.
Okay. So you are mentioning several times about the time complexity and the complexity of the new solution. That is a better complexity, lower complexity than the previous one. So how does this look like?
So I think, there is still room for improvement. Relatively compared to previous solutions, which kind of get this bulkiness because they are using some explicit alignment techniques, or they are using some kind of a post-processing. The important thing is that that in the design, we kind of carefully design it in a way that all this alignment and fusion modules are very lightweight. And kind of the motivation came from our previous work, which was Burstformer, not designed specifically for burst image processing for standard image restoration task. How we kind of adapted it for the burst processing techniques. But I think there is still room, a lot of room for improvement when we talk about computational complexity. This is not something I think still optimal.
Okay, and how does it translate in runtime? And what is the relationship between the resolution of the images?
Okay, in runtime, we also observed compared to the first approach, BitNet, that it's 2 times faster. So the efficiency kind of translates into runtime as well. The relation of the inference with the resolution, I think yes, there will be some relation. I'm not too sure about it at the moment, so I can't comment on it in a concrete fashion. But I assume that at least will kind of the inference time will degrade faithfully compared to the previous approaches, and will increase as well.
Here in this particular case, about the normal from this.
We achieve. I think here, as I mentioned, it's 2 times faster. I don't know the exact things, so it is difficult for me.
Okay. So anyone? Yes, yes.
Yes, as I explained, the whole architecture is kind of designed in that kind of a careful manner. So first of all, we are not using any explicit alignment techniques. It's an implicit alignment technique. But then on top of it, the fusion modules that are kind of used, that are introduced here, are kind of, the inspiration came from our Burstformer paper. But they are again carefully integrated into the architecture to reduce the overall efficiency. And then the next question could be, okay, yes, the efficiency is kind of improved, but why the performance is still comparable or better than BitNet? I think that is because we are incorporating both local and non-local contextual information. That is something that was missing before. So that is one of the advantages of the transformer-based design. Yes. So it was raw images. I think there is some, depending on the task. So for example, we are doing some kind of a demosaicing for this first, but it is consistent compared to previous work. So that we just take a raw. No. Yes. And specifically when I talk about the denoising experiments, there was one particular experiment for a very high level of noise, because that was even not seen during training, and that is kind of typically used for looking at the generalization capabilities of the model. So here also we kind of observe consistency in terms of performance.
Other questions? Yes, please.
No. It is created by. Yes, so we kind of followed. I mean, both the synthetic and the real one. We followed the previous works. There is a very nice work that was in CEPR 21 from Radu and colleagues from ETH. And this work, the first work, the BIPNet, is kind of based upon. Yes. So the only difference is that we are not using explicit alignment. It is more like in the direction of implicit alignment. So that's a more in the architecture design difference. However, the protocol and everything is consistent. Yeah.
Okay. So when or did you try to see when actually kicks in the benefits of your designs? Let's say after 3 or 4 or 8 frames that are integrated in the burst mode, or already after 2 frames you are seeing some benefits?
I mean, again, it's difficult for me to comment on that. I think Akshay would be the right person to answer this. But I think, I mean, all this, that's the result which I kind of presented is, I mean, this is consistent 8 frames. So in terms of just looking into the benefits, I think here we kind of have seen this, but I'm not sure about if we reduce the frames, how kind of I assume that okay, that it's kind of the benefits are still, I mean for more, but I mean in this extreme case of 2 frames, I'm not sure that.
Another question. Okay. What about perceptual quality?
Yes. So here the results in the we kind of use a standard 3 matrix and to measure the image quality, the perceptual quality, also the qualitative results or the comparison that we perform. I mean, it seems to preserve the structural information and also the color details, specifically for the low light restoration task. So compared to previous works, I think an very interesting thing is with this alignment, implicit alignment modules and this architecture design is that we observe it works to be better compared to previous works that are using explicit alignments, especially when the object is moving fast. So this is some of the scenarios, and this is typically can happen in burst processing. If the object in the scene is moving too fast, there in that case we observe very consistently.
Okay. What is your opinion about line burst restoration? Because you treated like 3 cases individually.
Yeah, I think this is again a very interesting direction, and I think yes, this is something worth exploring. And I think, I mean, if we look into other topics or disciplines right now in vision, this is something I think immediately will be someone who will be trying this kind of thing. One can name it under foundation model or something that kind of unifies it, rather than that's why I explicitly mentioned that. Okay, there is no ambiguity here that these are separately trained models. Yes, the architecture is the same, but okay, by no means the current definition. We are training one model. I think this is definitely the future.
Okay. Any other questions? Yes, please.
What is the benefits? So there could be, I mean, when I started the whole thing, I mean, the whole motivation is that okay, that with smartphone cameras, we would like to get the quality of a DSLR or high quality images. So this line of work is actually in the direction of burst processing, just to get excessive shots and then kind of achieve a composite image as an output with a high quality compared to others. So in this particular one, we kind of are using raw images as an input. So this kind of thing, I think there are advantages to use this kind of thing. Again, there was a question about explicit noise mechanism as well. So there could be other alternatives to address the problem. What is the ISP process for that? No, I think not in this one. Yeah.
Okay. Yeah.
We haven't explicitly done that experiment yet. I mean, yeah, everyone could think about it in that direction, but I think the real benefit may be, I'm not sure how much visible the improvements will be in that case. Yes, yes. Yes, yes. Yeah, that could be something. Yeah, that could be something.
Okay. So, any other question? Rasta? I still have questions,
Yeah,
but
sure.
probably we'll take it offline. Okay. So let's thank the speaker.
Thank you very much.
Thank you. So now we'll get back the presentations. We are still behind with our schedule, and we'll go to the single image super resolution report. Okay.
Hello everyone, I'm Zhen Chen. I will present you the new trends in imaging restoration and enhancement 2023 challenge on imaging super resolution method. Hello everyone, I'm Zhen Chen. I will present you the new trends in imaging restoration and enhancement 2023 challenge on imaging super resolution methods and results. The task of imaging super resolution is to generate a high resolution output from a corresponding low resolution input by leveraging prior information from paired LR and HR images. We hold this challenge with two motivations. First, to provide an overview of the new trends and advances in super resolution areas. Second, to obtain a network design capable of producing high-quality results with the best performance. We want to explore how high performance we can achieve regardless of computational cost and debt. The challenge has two phases. First is the development and the validation phase. The participants train their model and submit their restored high-resolution images to the evaluation server to calculate the PSNR value. Second is the testing phase. Participants submit their restored high-resolution images to the code lab server and provide their fact sheet and code by email. As we mentioned above, the challenge doesn't specify training datasets. Participants can access any training data. We recommend some datasets like Div2K, Flick2K, and LSDR. For the track, the ranking of a team is determined by the PSNR value on the Div2K testing dataset. The challenge attracts 33 registered teams, of which 15 teams submit valid entries. These entries set the state-of-the-art in imaging super resolution. Here we show the detailed information of 15 teams, including team names and leader names. The final testing results and rankings are presented in the table. As we can see, The ZZPM team achieves the highest overall rankings in this challenge. Moreover, the average PSNR value of the top 5 teams is above 31 decibel. Next, we will briefly introduce the method of the top 3 teams. First, for the winner ZZPM team, the overall workflow of the solution proposed by ZZPM team is isolated in Finger. The method first performs data augmentation locally on the div2k and LSDR datasets. A total of 6 data augmentation methods are used. These methods greatly increase the diversity of the data and improve the robustness of the model. Moreover, the team selects a total of 5 state-of-the-art models. These models are widely used and have shown excellent performance in super-resolution tasks. For inference, the final imaging is obtained by fusing the outputs of all methods in the post-processing part. The post-processing part firstly calculates the mean of the 5 imagings to be fused, and then the MSE is calculated between each imaging and the mean. The smaller the MSE value, the greater the weight assigned to the model during fusion. Finally, the output result is obtained by performing a weighted fusion of the output of 5 models using the calculated weights. The significance of this method is that it can avoid the final result being harmed by spatial bad points. For the second place, graphing, the team proposed a transformer model with cross-scale attention and wavelet hallucination. The framework is shown in the figure. In cross-scale attention, the method adds the depth-wise convolution in the query transformation and adds the multi-scale depth-wise convolution in the key and value. Such depth-wise convolution can extract the local features and models the relationship between features across multiple scales. The cross-scale attention is used to improve the original shift window attention. For the wavelet hallucination, the method first hallucinates full frequency subbands, and hidden higher resolution features is predicted by hallucinating features in different frequencies. Such hidden high resolution features help to extract their finer details. The wavelet hallucination is used to replace the convolution at the end of each transformer layer. For the third place, the IP lab, the team designs the attention retractable frequency transformer ARFT. The ARFT has 2 attention strategies, DMSA and SMSA. The DMSA allows each token to interact with a smaller number of tokens from the neighborhood position of a non-overlap window. Meanwhile, the SMSA allows each token to interact with a smaller number of tokens from sparse position with a constant interval size. By using DMSA and SMSA alternately, ARFT is able to capture global information. Furthermore, the team designs the FEB network to capture the long-range context in the frequency domain. As shown in the figure, the FEB network is composed of 2 components, a frequency branch and a spatial branch. The frequency branch generates a frequency feature, while the spatial branch produces spatial feature. The outputs of 2 branches are concentrated and operate by a convolution layer to obtain the final results. Moreover, the progressive training strategy is used to train ARFT to improve the super resolution performance. Specifically, the model is trained with different patch size and batch size at different stages. In conclusion, The challenge provides several new trends and advances in super-resolution areas at the method and data aspects. For method, adapting and modifying the transformer architecture is the mainstream technology, and global information is crucial for super-resolution. For the data aspect, more training data and better imaging augmentation methods could effectively improve the super-resolution performance. That's all. Thanks for listening.
So this was the report on the image resolution challenge. We'll go to the quality assessment challenge report, quality assessment of video enhancement.
From Shanghai Jiaotong University. I'm going to present about the entire 2023 quality assessment of video enhancement challenge. This challenge was organized by the team led by Xiaohong Liu. I would like to introduce this challenge in detail in the following sections: background, the dataset we built, the challenge results, and finally I will make a conclusion. First is the background. Since videos captured by a camera or smartphone always need post-processing to get better visualization, many video enhancement methods have been proposed in recent years. The main goal of such video enhancement methods is to improve video quality in different terms, such as contrast, colorfulness, and so on. However, how to evaluate the quality of the enhanced video is an urgent problem. Therefore, we held the entire video enhancement quality assessment challenge. This challenge aims to promote the development of the VQA method for enhanced videos to get the improvement of the performance of video enhancement methods, thereby improving the viewing experience of videos. This challenge uses the training, validation, and test sites as defined in the VDPVE dataset we built. The VDPVE dataset has 1,211 videos with different enhancements, which can be divided into 3 sub-datasets. The first sub-dataset has 600 videos with color, brightness, and contrast enhancements. The second sub-dataset has 310 videos with deburring, and the third sub-dataset has 3,001 distinct videos. The video length is 8 seconds or 10 seconds. We invited 21 subjects to rate all enhanced videos in the VDPVE. They were asked to score the enhanced video in the range of 0 to 100, and the score from low to high indicated that the quality is from poor to excellent. After the subjective experiment, we calculated the modes for each enhanced video. This figure shows the distribution of modes for all enhanced videos in the VDPVE dataset. Then we split the VDPVE into a training set, a validation set, and a test set according to the ratio of 7 to 1 to 2. The enhanced videos generated from the same reference video were divided into the same set. Next, I will provide a detailed introduction to the process and the result of the challenge. The whole challenge consists of 2 stages, the developing stage and the testing stage. In the developing stage, we released the training videos with most labels and the validation videos without most labels. In the testing stage, the participants could access to the test videos without most labels. In the challenge, we use average of PLCC and SRCC as a measure scores to calculate prediction performance. The charted timeline is shown below. On January 30th, the training stage began, and we released the training and validation sites. On March 40th, the testing stage began, and we released the test site. Participants are required to submit the predicted result of the test site before March 20th. March 22nd, we announced the final rank to all participants and invited them to submit workshop papers before April 50th. A total of 37 teams participated in the testing stage, and 90 teams submitted their final code and fact sheets. This table summarizes the main results and important information of the valid teams. From the table, it can be seen that the prediction performance of the top 4 teams have reached about 0.8. Next, I will introduce the method proposed by the top 1 team in detail. Team TBVQ is the final winner of the challenge. They propose a NRVQ method based on swing transformer with improved spatial temporal feature fusion and data augmentation strategy. The network is based on simple VQ and is composed of 2 key models: the feature extraction model and the spatial temporal feature fusion model. In the spatial feature extraction model, they use swing transformer V2 as the background the backbone network to extract spatial features. In the feature fusion model, they introduce a convolutional layer which depends the spatial features extracted from the intermediate stages of the pre-trained network. Then all features are fused for video quality prediction. To further enhance the robustness of the model, data augmentation strategy is performed to increase the number of video frames in the training stage. Especially, they first train their model on the LSVQ dataset, and then they build a dataset similar to the VDPVE training set, and further train the model on the dataset they built. And then fine-tune it on the VDPVE training set. Finally, it's a conclusion. This challenge provides a new video enhancement quality assignment dataset, VDPVE. To our knowledge, this is the first VQA dataset that includes different video enhancements. In addition, participants have proposed many high-performance quality assignment methods for video enhancement, which has promoted the development of VQA methods. Of course, there is still room for improvement in the prediction performance of quality assessment methods for video enhancement. More details can be seen in our challenge report. Thank you for watching.
Okay, so this was the presentation, the challenge. As we are still quite a bit behind, just go directly for the quality assessment of cancer detection. So this is so a simple question: if the main organizers of the video colorization or here. Video colorization challenge. Yes? Okay. So let's go for the video colorization because right behind. Okay, so the rest is okay. So that's gonna that part. Let's see. That was really fun. Is anybody that has a HDMI to Type-C or Type-C to HDMI converter? You have? Okay. So, slots. Let's see. So hello everyone. Oh. One moment. This is what is okay. It's not very stable, so I'm sure that we will touch. Yes, it's working. One. This one. I can't see that. Okay, so still no. Response here.
Yeah, you can see your structure there. Okay, so maybe the best is just to share them. Share. Share. Okay, here. Yeah, excellent. Yes. Hello, everyone. Sorry. Here I'm introduce our sweep chart challenge. Yeah, this is a video colorization challenge. This challenge addressed this challenge is supported by Damo Academy and the model school community. The target of this challenge is to convert the grayscale videos into color videos with better colorization performance and temporary consistency. Here we have two tracks. The first one, for track one, the aim is to obtain a solution with the best FID while being constrained to maintain or improve over the baseline in terms of CDC. For track two, the aim is to obtain the solutions with the best CDC while being constrained to maintain or improve over the baseline in terms of FID. For both tracks, we choose or define the famous open source colorization method as our baseline. So as for the dataset, we employ a subset or large-scale diverse video dataset and the training set and the validation set. The LDV dataset includes diverse categories of contents, various content or motion and different frame rates. We use 200 of them as the training set and 15 of them as the validation set. The videos are further divided into frames that are publicly available to minimize the difference caused by different video decoding methods. All video frames are converted into grayscale. As for the test set, it contains 15 diverse videos collected from YouTube. Each video contains 100 grayscale frames in the size of 916 by 514. The videos contains multiple types of scenarios, like animals, city, human, indoor scenario, and so on. Following the experimental settings of most existing colorization method, we mainly use FID to evaluate the colorization performance of the method, where FID measures the distribution similarity between the generated image and the ground truth image. For temporal consistency, we adopt color distribution consistency index. It is computed on the output colorized frames. Specifically, it computed the gestational divergence of the color distribution between consecutive frames. These divergences can measure the similarity between two color probability distribution. The overall index considers the long-term and short-term temporary consistency together. There are 93 and 113 teams in these two tracks, and 50 and 40 teams takes the final testing phase. Among them, 6 teams submitted valid results. Here is a visual comparison for track 1. The first column is the grayscale input, and the second one is our baseline. The remaining results are the competitive results. There are 93 and 100 teams in these two tracks, and 15 and 2 terms. Here is another visual comparison for track 2. Now let's move to the method part. Most of the proposed methods incorporate temporal features in various ways, such as bidirectional temporal fusion blocks, bidirectional recurrent transformer networks. Some exemplar-based video colorization methods achieved higher ratings in the challenge, but higher quality reference reframes are required.
The NGSTIRE team adopted by BitNet and their BitSlime model. BitNet is a deep video colorization method that leverages semantic image prior to guide bi-directional temporal feature viewing. It can effectively exploit the color information or reference exemplars and propagate it to colorize other frames. The NGSTIRE team first experimented disco and image colorization method to generate colorful reference frames. Experimental results show that disco generates reference frames with good visual quality, but overall the colorfulness is far from satisfactory. Therefore, they finally adopted to search for the closest possible color image from the internet and reference frames for BitNet. The video colorization models based on these reference frames performs very competitively. And then the QuickPlus team proposed a bidirectional recurrent transformer network for video colorization. The proposed network BRT is based on RTN, which with the difference being that the transformer adopted in it is a Burstformer network. BRT takes a series of video frames as input. A shallow net feature and optical flow information will be obtained after encoder and flow respectively. Learnable guided mask model will fuse this information and fit the output features mapped into Burstformer network, which can capture more multi-scale semantics during training and reduce the occurrence of color artifacts. The Mi-AI Go team proposed a multimodal fusion strategy. The approach involves training CT2 on a large amount of unfiltered YouTube data and naming the model as CT2 Classic. Subsequently, the data is cleaned and filtered to select video frames of the common sense using the official shared training data. Another CT2 model is trained on the filtered data, and we name it as CT2 Vivid. During testing, a content-based image retrieval system is utilized to match the test video and the filtered training data set. If the distance is larger than the predefined threshold, the vivid result is used. Otherwise, the classic result is used. This design is intended to increase the robustness of the method by using different models for different scenarios. And the final vector team proposed the temporal consistency automatic video colorization with semantic correspondence, which combines the semantic correspondence network into automatic video colorization. The proposed network framework is divided into two stages. The first one involves automatic image colorization network, and the second one includes a semantic correspondence network, the image colorization network. In the first stage, the first frame of each video is selected to be automatically colorized, and the resulting image is then regarded as the reference image in the second stage. Now let's move on to the conclusion part. As the first challenge to focus on general video colorization, this challenge aims to access and advance the last level of video colorization. We set up two tracks that emphasize high colorization quality and time consistency solutions, respectively. A total of 93 and 130 teams in the two tracks of the challenge. We hope that more new technologies like diffusion model, text-guided video colorization will emerge and be applied in this field to promote faster and practical application of video colorization. Okay, thank you.
So, are there questions about this challenge, video colorization?
More detailed can be found in the later.
Sure. Okay, so if you have questions, always you can approach the authors. We will be also at the poster session. Okay. I will. Okay, so now we have, according to our schedule, we have the post reception within the exhibition hall at the ground level in this building, and we have also the award ceremony. But as far as I can see, most of the winners are not here, are not in person here. So probably I will just go through the certificates, and if somebody is here, just raise your hands. And I have some printed diploma. Otherwise, the winners will receive their certificates as PDFs. Okay, and will be made available also on the webpage. Okay, so I'll start with the non-homogeneous dehazing challenge. So, are the winners here? Anyone on the dehazing challenge? Okay, then I'll just browse through the lens-to-lens bokeh effect transformation. Anyone from the challenge? Then the 360 degrees omnidirectional image resolution. Okay. So let's move on. The video resolution, the same 360 degrees omnidirectional. Quality assessment of the video enhancement. Okay. So video colorization. No one in person here. Okay. Light field image resolution. Okay. Image denoising. Okay. Then we have the stereo image resolution. Okay. Efficient resolution challenge. Night photography rendering challenge. Okay, so I was right. Most of the people are not here. So fast. Efficient deep models for real-time 4K image resolution. Yeah. Let's see which team. This team. So you are one of the winners. Okay, just have a seat, and we'll get back to you, Marcos. Okay. So, Just take a picture. Okay, let's see. Maybe we are lucky. Second place award in high efficient deep models for real-time. No one from NTIRE. Okay, the third place award in the same challenge. The track 2. So Mustafa actually contacted me. He's not able to in person. Okay. Finishing team? No. In case it's not. Then shadow removal. No, no made one. The high resolution depth challenge. Samsung team? No. Vivo? No. The challenge of image resolution, I'm scaling factor 4. No. Yeah, so those were like the award certificates. They will be made available on the webpage of the workshop as PDFs. So all the authors are free to use them. And okay, so a little bit of logistics. So on the web page of the workshop, there is a long list of papers, somewhere at the end of the schedule. And for each paper is mentioned the poster ID in the noon session that started like 18 minutes ago, and also in the evening session. The noon session basically takes up to 1:30 when we are returning and resuming with the presentations session. And the evening session will start at 5:30 in the afternoon. So those that are having here posters, okay, they should just pay attention and bring the poster, have the poster during the session, and remove it afterwards, because the organizers are using those poster panels for other purposes. Okay. So all those papers will have also some extra materials that are provided. Okay, so for those that are online, we'll resume our workshop at 1:30. Okay, so the posters are in downstairs for the exhibition hall.
Hello，它关机了。Hello。 Hello? Hello? Can you hear me? Can you hear me?
Okay. Okay. So a little bit of checking. Those that are attending online, can you hear? Well, yes. Okay, perfect. Can you see the slides? Everything is fine?
Yes.
Perfect. Thanks. Okay, so I think we'll start the afternoon session of the workshop. And we'll start with a challenge report. We have the challenge on stereo image resolution. And the organizers, unfortunately, couldn't come in person here, but in the CPR, but they provided a recording that I will play now.
Long Wang from National University of Defense Technology. I'm very glad to introduce the second NTIRE stereo image super resolution challenge and present the challenge report. Recently, with the popularity of dual cameras in mobile phones, autonomous vehicles, and robots, stereo vision has attracted increasingly attention in both academia and industry. In many applications like AR, VR, and robot navigation, increasing the resolution of a stereo image pair is highly demanded. Although deep learning has achieved remarkable progress in single image super resolution, stereo image super resolution has two particular challenges. First, disparities between stereo images can vary significantly for different cameras, with various baselines, focal lengths, depths, and resolutions. Second, limited receptive field of convolutional layers hinders plain CNNs to capture long-range stereo correspondence. Therefore, stereo image supersolution still remains an open problem. In our challenge, we aim to establish a benchmark for stereo image supersolution. 800 stereo images in the training set of the Flickr 1024 dataset are used as the training data, while 112 stereo images in the validation set are used as the validation data. Both low resolution and high resolution images are provided for the training and validation sets. In addition, 100 low resolution stereo images with private high resolution images are adopted as the test data. This challenge is an extension of the entire 2022 stereo image supersolution challenge, with more focus on realistic degradations and the perceptual quality of the super resolution images. This challenge has 3 tracks. Track 1 is inherited from the entire 2022 challenge. The standard bicubic degradation is used to generate low-resolution images. For evaluation, PSNR and SSIM are used as metrics. Note that PSNR scores calculated in the RGB domain is employed for the final ranking. Track 2 focuses on the perceptual quality of the super-resolution images. The standard bicubic degradation is used, but different evaluation metrics are adopted. The high visual quality of a stereo image pair is attributed to the high perceptual quality of separated images and their promising stereo consistency. Therefore, we use LPIPS to measure the perceptual quality and calculate the MAE loss between disparity maps to measure the stereo consistency. Track 3 focuses on realistic degradations. Low-resolution images are generated using realistic degradations, including blur, downsampling, noise, and JPEG compression. PSNR and SSIM are used as metrics for evaluation. For Track 1, 175 participants were successfully registered, and 21 teams competed in the final testing phase. The winner solution has beat the champion last year and set a new benchmark. For Track 2, 93 participants were successfully registered, and 17 teams competed in the final testing phase. Compared with Track 1, the perceptual quality of the super resolution results are significantly improved. For Track 3, 103 participants were successfully registered, and 12 teams competed in the final testing phase. Among the submitted solutions, we have several key observations in 3 aspects. First, in terms of network architecture, all solutions are based on deep learning techniques. Compared to the challenge last year, CNN architectures becomes popular again, and many solutions are developed using CNNs. 43 out of 50 solutions use parallax attention mechanism to capture stereo correspondence. Diffusion model is adopted to synthesize images with high perceptual quality in Track 2. Second, in terms of data augmentation, random flipping and RGB channel shuffling are widely used in most solutions. Moreover, random horizontal shifting, mix-up, and cut mix-up are also used in several solutions. Third, in terms of ensembling strategy, both data ensemble and model ensemble are widely employed in several solutions to further boost the super resolution performance. Thanks for your listening, and let's leave time for the champion and the runner-up to introduce their solutions in details. Thank you.
Okay, so this was the presentation of the report. Is any of the main organizers here? Okay. So I'm not seeing them, and probably the best is to move to the next presentation. And if you have questions, just approach directly by email. Okay, the next presentation is one of the top solutions in this challenge. And our course provided a video.
Hello. Yeah. Okay. Hello everyone. We are others from the BSR team from the ByteDance. We will play a pre-record video to demonstrate our proposed method. Is that okay for us to play the video?
Okay.
No?
So
okay.
If you want, you can play it yourself. Yes, it's okay.
Okay. Thank you. Let me see.
Is the same video like the one that you shared with me?
Yeah, of course.
Okay. Good. So you can start.
Let me see.
ByteDance. I am glad that our BSR team has won the first place in track 1 of the NTIRE Stereo Image Super Resolution Challenge. In this presentation, we propose a hybrid transformer and CNN attention network, HTCAN, which utilizes a transformer-based network for single image enhancement and a CNN-based network for stereo information fusion. Stereo image super resolution aims to reconstruct high-resolution images from the given low-resolution left and right view images. It has attracted more attention in recent years as it has shown promising potential in downstream tasks such as stereo depth estimation and VR applications. Although stereo image super resolution shares many similarities with single image super resolution, there is a very important difference. Single image super resolution can only utilize the information from one view, while stereo image super resolution can use the information from both views with a large overlapping area. This is not trivial because the information lost in one view might still exist in the other view, and utilizing the extra information from the other view can largely benefit the reconstruction process. Therefore, the final performance of the stereo image super resolution algorithm largely relies on the feature extraction capability of each view and the stereo information exchange capability. In our proposed method, we utilize a transformer as our first stage to make sure most of the important features of the single-view low-resolution images are kept for the further process, and a CNN-based method in the second stage to conduct effective stereo information exchange. The final performance illustrates the effectiveness of our design. In summary, this paper has the following 3 contributions. First of all, we propose a unified stereo image super resolution algorithm, which integrates the transformer and CNN architectures, where the transformer is used to extract features of the single-view image while the CNN module is used to exchange the information from both views and generate the final super-resolution images. Secondly, we conduct a comprehensive study on the multi-patch training strategy and other techniques and apply them to stereo image super-resolution. Last but not the least, our proposed method achieves new state-of-the-art performance and wins first place in track 1 of the Stereo Image Super Resolution Challenge. The transformer architecture has proven to be very effective as a super resolution algorithm in previous works. This is because a traditional convolutional neural network works on the locality prior and may suffer from long-range dependency. But transformers have a much larger receptive field compared to a convolutional neural network, and their self-attention mechanism can effectively model long-range dependencies. The effective feature extraction capability of a vision transformer can largely benefit stereo image super resolution because the information from both views should be carefully utilized so that useful information is not lost during the super resolution process. On the other hand, the memory and computational cost for a vision transformer is usually much larger compared to a convolutional neural network. This problem will get much more severe when the resolution is high and a lot of query tokens exist. The long-range modeling capability also relies on a huge amount of training data. This makes the convolutional neural network performs well when the training data is limited. The previous state-of-the-art stereo super-resolution method NAFSSR is completely developed from a convolutional neural network, demonstrating the effectiveness of the convolutional neural network on the relatively small dataset. Because of its efficiency and computational cost, CNN-based models can usually afford more parallel exchange modules compared to transformer-based models and allows a more thorough information exchange. Therefore, we present a hybrid transformer and CNN attention network. The proposed HTCAN is a multi-stage restoration network, as shown in the figure. More specifically, given the low-resolution stereo images L-LR and R-LR, we first super-resolved them with a transformer-based single-image super-resolution network to L-S1 and R-S1. In Stage 2, we adopt a CNN-based network to stereo enhance L-S1 and R-S1 and get the enhanced images L-SR and R-SR. In the third stage, we use the same CNN-based network as Stage 2 for further stereo enhancement and model ensembling. First, we introduced the data augmentation methods channel shuffle and mix-up, denoted by the abbreviation DA, which resulted in a performance gain of 0.07 decibels. These methods have been shown to be effective in improving the generalization ability of deep neural networks by introducing random perturbations to the input data. The abbreviation MPHAT denotes HAT-L with multi-patch training strategy. The proposed multi-patch training strategy improves performance by 0.04 decibels. The reason is that the multi-patch training strategy expand the receptive field of the network, thus improve the information aggregation within single image. We further improved the performance by fine-tuning the MPHAT model with mean squared error, MSE, loss, which resulted in an additional performance gain of 0.04 decibels. Additionally, we found that using a larger window size 24 × 24 resulted in a 0.01 decibels gain. This strategy involves using a larger receptive field to capture more contextual information and improve the network's ability to reconstruct fine-grained details. To further improve our method's performance, we adopted a self-ensemble strategy, which improved the performance by 0.07 decibels. We rotate and vertically flip the input image and averaging the results to obtain a final prediction, which has been shown to be effective in reducing the variance of the network's output. Finally, we presented the results of the model ensemble, denoted by MPHAT ensemble, which combined the results of MPHAT MSE M×8, MPHAT CELU M×8, MPHAT Fourier UP M×8, and MPHAT window size 24 M×8, weighted according to their respective performances. Specifically, we weighted the results of these models with weights of 1/7, 1/7, 1/7, and 4/7, respectively. We set the largest weight on MPHAT window size 24 because it outperforms the other three models. The model ensemble strategy further improves performance by 0.02 decibels. As shown in the table, our method outperforms other state-of-the-art single-image super-resolution methods and stereo-image super-resolution methods on most test datasets. On the in-distribution dataset Flickr 1024, our method achieved a 0.27 decibels gain over NAFSSRL and a 0.23 decibels gain over HAT-L. On the out-distribution dataset Middlebury, HAT-L achieved the best results, likely due to its pre-training on the large-scale ImageNet dataset. This figure demonstrates the superiority of our proposed method. Please look at the pillar, the window, and the text on the road sign. Our proposed multi-stage strategy has effectively restored the textures. The primary objective of the NTIRE 2023 Stereo Image Super Resolution Challenge was to obtain a solution that can produce sharp results with high fidelity, PSNR, from bicubically downsampled input images to their corresponding ground truth images. Our proposed hybrid transformer and CNN attention network achieved first place in track 1 of the challenge. We would like to note that our method utilized self-ensemble and model ensemble strategies to improve its performance. Ultimately, our method achieved a PSNR of 24.34 decibels on the validation set and 23.90 decibels on the test set. That's all for our presentation. Thank you.
That's all for our presentation. Thank you. Do you have any questions?
Yes, the first one. The presentation was supposed to be 5 minutes.
Okay. Oh, sorry. We had an email to tell us it's a 10 minutes presentation. Sorry.
Okay, so I don't know. Is any question from here? Yes. Okay, the question that came from here is about complexity of the model. Could you elaborate on the complexity of your model?
The complex of the model. Oh, okay. The complex of the model is, I think this model is quite huge because this is a plan for the, this is algorithm for the competition. It has 2 stages. Each stage, in the first stage, there is a model which is have the same complexity with the head model, which is a common single view super resolution model. In the second stage, there's a smaller CNN based module. Its complexity is the same with the NARF SSR.
Okay. Yeah. So we need another challenge for efficient methods.
Yeah.
Okay. Yes, it's huge. Yes. Okay.
Well,
thank you, Mario.
Okay.
We move on to the next presentation.
Okay,
Thanks.
thank you. Thank you. Bye-bye.
Bye. Okay, the next presentation is also one of the top winners in this challenge. Okay. And we have a recording.
Hello everyone, thanks for watching this video. Today, I will briefly introduce our work. Our work is based on NAF-SSR. For perceptual-oriented stereo image super-resolution, we combine the LPIP's perceptual loss with the traditional VGG perceptual loss for training. To improve stereo consistency, we perform supervision on each HTCAN. Our method without GN end up ranking second place on the test set of NTIRE challenge. This is our framework. The blue arrows indicate supervision during the training process, including pixel loss, perception loss, adversarial loss, and stereo consistency loss, and I am going to talk about them. To improve the stereo consistency of stereo super-resolution images, a direct approach is to supervise the disparity of an SR pair and the disparity of the corresponding HR pair. Specifically, given a pre-training model for a disparity estimation task or optical flow task, we calculate the disparity maps for the SR image pair and the HR image pair respectively. Then, we calculate the relative errors between the SR disparity map and the HR disparity map as losses, namely parallax supervision loss. But since pre-trained models on other training sets are not allowed, we follow PASSRNet, calculates the photometric loss, smoothness loss, and cycle loss using the cycle attention maps and valid masks of HTCAN, as a stereo consistency loss. For perceptual guided training, we found that combining LPIPs with VGG perceptual loss can achieve better perceptual performance. We use the UNet discriminator of real estrogen to stitch the left and right images into the discriminator. The losses in the discriminator include the encoder and decoder part output loss, both of which use relative losses. The overall loss function consists of MSE loss, perceptual loss, stereo consistency loss, and adversarial loss. And the total loss can be expressed as a weighted sum of the above losses. In the ablation study, Table 1 shows that after replacing parallax supervision loss with stereo consistency loss, the score has dropped, but it is better than no consistent supervision. In Table 2 we also examine the impact of other strategies on the results. It indicates that applying EMA improves the stability of the model and helps convergence. Also, randomly cropped of the dataset during fine-tuning enhances the generalization performance. Our GN-based method achieves the best results on LPIPS metrics and score, and our GN-free method also achieves the second-best results. Our method produces more complex textures while PSNR-oriented tends to generate smoother textures. However, models trained with LPIPS loss generate many regular artifacts, especially in dense and complex textures such as leaves and branches. By applying the modified GN method to our original scheme, the artifacts are reduced while maintaining the perceptual quality and stereo consistency. And the visual effect is greatly improved.
Okay, so this was a presentation. I don't know if the first author is here. Is okay. Okay, if not, then we move on to the next presentation. And if there are questions, just contact the first author. The next presentation
I'm Pierluigi Zamora-Ramirez from the University of Bologna, and I'm here today to present to you the report of our challenge on depth estimation from high-resolution images containing transparent and reflective objects. In computer vision, accurately estimating depth from images has captivated the minds of countless researchers. But why is this quest so important, you may wonder? Well, the answer lies in the fact that depth estimation serves as the fundamental building block for a multitude of groundbreaking applications, from enhancing images to creating immersive augmented reality experiences, empowering robots with spatial awareness, enabling advancement in medical imaging, and much more. When it comes to measuring depth, we have two approaches at our disposal. The first involves using specialized active sensors, such as LiDARs and TOFs. On the other hand, we have the option of leveraging a standard imaging sensor and developing sophisticated algorithms or deep neural networks to estimate depth. Regarding passive sensor, the remarkable advancement in machine learning and deep learning techniques have paved the way for significant improvements in reconstructing three-dimensional structures from single or multi-view images. However, despite these achievements, there are still important considerations to address. One major challenge lies in resolution. On one hand, active depth sensor typically provides sparse depth measurements, rarely reaching 1 megapixel. On the other hand, while standard cameras feature resolution up to dozens of megapixels, processing them with deep neural networks requires significant computational efforts. Another challenge arises from transparent specular materials, which pose difficulties for both active sensor and image-based techniques. These materials violate the underlying assumption of most depth sensing technique. For instance, in the case of active sensors, issues may arise from the refraction of light beam emitted by a LiDAR or its projection onto an object behind a transparent surface. Similarly, image-based approaches, such as stereo algorithms,
struggle to estimate depth for transparent objects as they find matches for the content located behind them. Nevertheless, accurately estimating the correct depth for these materials is crucial in many practical applications, such as a robotic arm dealing with a transparent object would fail to manipulate them if it lacks of an appropriate depth perception technology designated to handle such challenge. Our primary goal with the challenge is to advance the development of a state-of-the-art solution for depth estimation that can effectively tackle the challenges we have discussed earlier. Now, let's dive into the structure of the challenge. It is organized into 2 tracks, each focusing on different approaches for depth estimation. The first track is the stereo track, where participants are tasked with estimating depth by calculating the disparity between pixels in 2 rectified stereo images. The second track is mono track, which assesses the accuracy of single image depth estimation techniques. In the stereo track, we had 49 registered participants, which only 2 teams submitting their final meters during the final testing stage. Similarly, in the mono track, we had 51 registered participants, with only 3 teams showcasing their final models. Some have opted for off-the-shelf solution, others have taken a more innovative path, combining different methodologies and leveraging the synergy between them to achieve superior results. To ensure a rigorous evaluation, we have carefully selected the booster dataset as the benchmark for this challenge. This dataset, as the only one of this kind, provides a diverse range of scenarios with transparent and reflective materials, all captured in high resolution of 12 megapixels. The booster dataset also includes material segmentation masks that categorize pixels into 4 distinct categories, such as opaque materials, colored in dark blue, and transparent or specular materials, colored in yellow. These masks offer valuable insight into the material properties of captured objects and enable the evaluation of method performances across different materials. In both tracks, we have selected the official metrics in the booster benchmark, such as the mean absolute error and the root mean square error. To rank methods, we use the mean absolute error for the stereo track and the absolute relative error to the ground truth for monocular track. To ensure the accuracy of the estimated monocular depth maps, we apply adjustment using scale and shift factors obtained through least square error estimation and on the ground truth depth map. It is important to note that all these metrics are evaluated across different material classes, ranging from opaque to transparent and specular materials. This comprehensive evaluation allows us to assess the performance of the methods across various materials. In this slide, we show the results of the stereo challenge. The first row showcases the performances of a state-of-the-art network for stereo matching, fine-tuned on the booster training data. As we can observe, the best submitted method, highlighted in the third row with a gold color, significantly improved the performances, particularly for class 1 and 2, that correspond to surfaces that are partially reflective or transparent, such as metals or glossy materials. The proposed network comes from the SRCB group of Samsung Research China and consists of 2 main blocks, a base architecture shown on the left in the figure and a high-resolution refinement module in the right in the figure. Here are some qualitative examples of the depth map estimated by the baseline network and the winning network of the challenge. As we can observe, the winning network performs significantly better in handling challenges, such as the translucent white surface of the bidet and the transparent area of the window. Similarly, in this slide, we present the result of the mono challenge. The first row of the table displays the performance of a state-of-the-art network for single image depth estimation, fine-tuned on booster training data. As we can observe, the best submitted method, highlighted in the fourth row with a gold color, significantly improved the performance by a substantial margin. The proposed network comes from the CV Challenge group at Vivo, and symmetrically to the stereo network consists of 2 main blocks, a base architecture shown on the left in the figure and a high-resolution refinement module. This network demonstrates remarkable performance in the single image depth estimation task. Here are the qualitative example of the depth map generated by both the baseline and winding network. While the winding network produces depth map with more artifacts compared to the baseline, it also captures higher resolution details. The qualitative results further confirm that the winding network has significantly lower errors in depth measurements. However, transparent and reflective objects continue to present challenges in depth estimation. The network often estimates depth based on the reflection or visibility through this object, leading to inaccuracies. Overall, it's worth noting that the best methods in each track have surpassed the baseline, making a significant step forward in addressing the proposed challenges. This achievement is a testament to the dedication and innovation of participating teams. However, despite the advancement, there are still areas that require further attention. Particularly, high-resolution prediction continue to exhibit significant errors. For example, in the monocular track, delta 105 metric stand at only 52%, indicating room for improvement. Similarly, in the stereo track, the BAT2 error remains at 32%, indicating the need of refinement. Additionally, our qualitative analysis reveals that monocular networks still struggle with transparent and specular surfaces, hindering accurate depth estimation in such scenarios. In conclusion, while commendable progress has been made, it is evident that more investigation and development are necessary to effectively handle high-resolution images and challenging materials. Thank you for your attention. We also thank HTCAN for kindly supporting our challenge.
Okay, so this was the presentation of the challenge, and the main organizer, Pierre Luigi, is here. So if you have questions. Okay. Yes, please.
Sorry, I couldn't hear you. Yeah, because monocular depth estimation is typically estimates that up to a scale factor and a shift factor. So it's better to evaluate it with the relative metrics respect to the ground, which is more robust. And yeah, and on the other hand, the stereo track is better to evaluate with mean absolute error, and that gives you the exact error of the image.
Okay. Well, if you have other questions, Carly will be here. Okay, thank you. Now let's move to the next presentation and pre-recording provided by the authors.
In this paper, we present a new method, called flexi-curve, for photo retouching. Unlike most existing methods that perform image-to-image mapping, which requires expensive pixel-wise reconstruction, flexi-curve takes an input image and estimates global curves to adjust the image. The adjustment curves are specially designed for performing piecewise mapping, taking nonlinear adjustment and differentiability into account. To cope with challenging and diverse properties in real-world photos, flexi-curve is formulated to produce diverse estimations. The spatial dependencies among these estimations are implicitly modeled by a transformer structure to improve local retouching of different regions. Thanks to the image-to-curve formulation, flexi-curve only needs a lightweight network. Our method improves efficiency without compromising the retouching quality and losing details in the original image. The method is also appealing as it is not limited to paired training data, thus it can flexibly learn rich retouching styles from unpaired data. Extensive experiments demonstrate the efficiency, retouching performance, and flexibility of our method quantitatively and qualitatively. We summarize the contributions as follows. 1. We present an approach that performs photo retouching by piecewise curves estimation through a deep network. Unlike existing methods that spend expensive computation for pixel-wise reconstruction, the new notion of curve adjustment enables parameter-efficient network structure, fast inference, and good details preservation and enhancement. 2. We explain how piecewise adjustment curves can be designed as the network's output. We show that a flexible curve can be realized through knot points and nonlinear curve parameters,
which collectively perform piecewise and nonlinear adjustment while being differentiable in the process of gradient backpropagation.
Okay, so this was the presentation. Just the online guys. Are the authors there? Johnny? Okay. Okay, then let's move to the next presentation. The authors provided. The authors do not provide a video. Let's see if Iman Abbasnejad is here. No. Okay, so if he's not, then we move to the invited talk. Rakesh. Good. So the floor is yours. Thank you.
Thank you. Good afternoon, everyone. My name is Rakesh. I'm a research manager in Reality Labs, Meta. So I'll talk about primarily the problem of denoising in the context of mixed reality. Specifically now, mixed reality is becoming more mainstream because of the more recent product announcements, Vision Pro from Apple and Quest 3 from Meta. This is mixed reality in general is going to become like a very interesting right playground for a lot of computer vision research across the entire stack.
And today I will touch on just one of the small pieces, and basically would like to walk you through what's the holistic problem of denoising looks like in a mixed reality setup. So what is mixed reality? Mixed reality is you have a head-mounted device where you see your surroundings as you would perceive without the device. So that's your reality. And then you would fuse it with a virtual content, right? Now, if you have looked at a typical VR device, it has the camera is called the pass-through cameras. So these cameras, it's a stereo camera setup that is set up at IPD distance. However, your eyes are not at the same place as the cameras are located. So what essentially pass-through pipeline would do is it will take the camera image stream and reconstruct your eye buffer images. So essentially, you are looking at a reconstructed view of reality. And the challenge of mixed reality is to pass the visual Turing test. Can it feel like what you would see if it wasn't for the device that you're seeing through? Now, this is, as I said, since every single pixel that you are seeing is reconstructed, that opens up a very interesting, so as to say, experimental test bed where you can use these pixels to denoise, to upscale, to understand the semantics of those pixels, understand your theme, and so on, right? And there are challenges across all of those layers of the algorithmic stack, on the device stack, system stack, everything. What I will talk about today is a very specific problem just about the denoising in the context of the reconstruction of the camera stream. So what are the key challenges in mixed reality? What are the pain points? The first one is low light. I mean, we know about night mode photography, which is not the most common thing you do with your phones. You capture videos mostly outdoors and so on with your phones. But however, when it comes to mixed reality devices, it's an indoor device. It's a device that you're using in your living room, in your office room. And usually these settings tend to be low light. And oftentimes, like 50% of the times, actually, the device is being used in a low light scenario. And low light here, I mean like roughly under 40 lumens. This is not the common scenario oftentimes we think about when we are thinking of capturing a video for a common use case. So denoising becomes particularly important because low light, you have less photons, so you have a higher problem with noise. The second thing is you still want a very high dynamic range. So let's say you have your VR device on, you are in mixed reality mode, and you are playing some game or trying out some experience in mixed reality, and suddenly your phone has a message, or you want to look at your laptop screen. Now that's pretty bright, and your device should be able to handle those bright screens so that you can read what is there. You know, a message coming to your phone, you should be able to read it without taking off your headset and putting it back. So it's really important to be able to support high dynamic range. And the third one is low latency. And this constraint is imposed by how our brains perceive the vision and the motion of our body. So if my head is moving in a certain way, and what I see with my eyes, if those things are not synchronized, then you would feel motion sickness. So that limits how much latency you are allowed to when you are reconstructing your camera image stream into your eye buffers. So latency is a very strict constraint here. So coming back to, so here what I will do, I'll explain why the denoising problem is important here in mixed reality setup. How does it relate to dynamic range? And then we'll go through a few directions that is that can help in thinking about the problem. So why is the noise problem so big? Well, first thing is about the sensor. If you look at a DSLR sensor, typically the sensor that you have on your typical smartphone is already 20 times smaller than a full frame DSLR sensor. And smaller the sensor, smaller the pixels, less photons you're able to capture, and higher is the amount of noise. Now, take that and make it 10x even further smaller, and then that's what you get the size of your sensor on the Quest Pro device, for example, or most typical devices, head-mounted devices. So we are talking about 200x less photon capture by each pixel in the sensor. So that's the first challenge that causes such a big noise problem to begin with. On top of that, this is a head-mounted device. So your head is never static, it's moving. In fact, head motion is even worse than hand tremors, like when you're trying to take a photo with your smartphone versus we don't think about intentionally trying to keep our head still when we are using our device. So there is head motion, which causes the additional problem of blur. In order to limit that problem, you want to do low exposure time. Typical exposure time in the case of head-mounted device, you want around 5 milliseconds. So that makes the problem of noise even worse than what you already had with a smaller sensor. And so given the limits of physics and usage, here, in fact, we don't have any good solution other than to go with computational denoising. And this entire community is very well familiar with this problem. I just hope that the context becomes more clear as to where computational imaging really has the biggest impact. Now, AI-based denoising has proven to be the most powerful method for denoising so far in the last several years. Pretty much all of the state-of-the-art methods are today machine learning based. And the reason is that today we are also very well able to do very accurate noise modeling of camera sensors. And that has really helped in the success of AI denoising methods coming into actual products. And another big advantage of machine learning based denoising is these learned representations of natural images really helps it to disentangle noise and some high frequency details which you actually want to keep, which is something that traditional methods struggle a lot with. So knowing NTIRE for last several years, I know that I don't have to make a case for AI-based denoising. What I would try to do is that beyond just pushing on the quality aspect, there are many other aspects of this problem that we need to understand. This is an example of, on the left, what you see is image from the Quest Pro camera sensor that is processed by a regular ISP, state-of-the-art good ISP, in 20 lux condition and with a 5 millisecond exposure. And what you see on the right is the same image, the same conditions, but processed by an AI denoising model. And you can see like the result looks quite promising. And this is a pretty tiny model that can actually run on device. This is just another example, and you can see like it saves details. There is a lot less chroma noise. It's overall just much better than the state-of-the-art ISP. So hopefully I could give a sense that why AI denoising is I would say, pretty much the only path right now we know about how to solve problems with so many constraints. I want to give another angle of like how denoising is also affects our problem of dynamic range that I talked about. So we want to be able to read screens on phones and monitors through the display. So dynamic range is really important. Now, here I'm plotting like just the relationship between per pixel luminance and the signal that you read out of that pixel. So if you have more light coming into the pixel, obviously the signal that you read will be higher, and it's a somewhat linear relationship. Now, this doesn't go on forever. Of course, there is a cap, and that is what we call as the full well capacity. That's when the pixel gets saturated. So beyond that, you can't collect any more. You can't read any more signals. And it is also capped on the bottom end by the SNR threshold. So basically, it's too dark for you to read any signal out of that pixel. So what happens is these two limits your effective dynamic range of your what you can actually read from your pixel. Things on the left are too dark, and things on the right are way too bright to be useful. So, for example, if this is the case, if I have to read my phone screen, I can't really do that. And this is a challenge. And this is, we want to see like how we can help with this problem. This is an example of an actual capture. So you can see like the phone screen is pretty much unreadable. It's the pixels are too saturated to be able to read anything out of that. You can say that, hey, like how about I reduce the exposure time, and if I reduce the exposure time, then it will just take much longer for the pixel to reach its saturation, the full well capacity. What happens in that case? If we do that, then in that case, your lower SNR threshold is also going to shift. And basically, you will have a new dynamic range. So now there are some darker sides of the scene that you will not be able to read, which you were able to do before. And of course, you can say, hey, can I just do some tone mapping and, increase the gain and recover some of the dark regions? You can do that, but it will be full of noise, and that's very challenging. So this is what the same scene that I just showed before will look like if you lower the exposure time. So you will be able to read the screen, but the rest of the image becomes too dark. And if you brighten up the background with tone mapping, you will basically see a lot of noise, so which is not a desirable scenario. So how does denoising come into this picture? What we are trying to do with denoising is we lower the SNR threshold. So now that if we have a lower SNR threshold, our effective dynamic range is we can not only recover the lost dynamic range. If the quality of denoising is really good, then we can even increase the dynamic range beyond what was possible. That becomes your new dynamic range. And this is exactly the example of the same scene. Now you are able to read the phone screen, and you're able to see the background without much noise that you come from just tone mapping the scene. And this from an actual quest. That's interesting. We need some audio denoising here. So this is again side by side. I just want to show like what happens on the left when our SNR threshold is higher. We couldn't read the phone screen, so we had a choice between the foreground or the background. But we are by doing a better denoising, you can actually increase the dynamic range, and you can see both the phone screen and the background very clearly. Just a replay of the same three images that I showed earlier. So summarizing what I'm trying to say here is if you look at the problem holistically, there are a bunch of conflicting challenges. Like if you want to optimize for one, you're challenged on the other side. So the key problems that there are with a device, like a VR device supporting mixed reality, is first of all, the problem of latency. It's a hard constraint, as I said, like the photon to display latency is something that is constrained by our human brains. So we are limited there in how many milliseconds. This is roughly between 10 to 50 milliseconds of latency that can be tolerated. And as I said, most of the usage, not most, but half of 50% of the usage is in low light scenarios, because oftentimes in our living rooms, office rooms, the lighting condition is not super bright. And those are also the places we want to look at screens. and be able to read text, and those are challenging in 20 to 40 lux levels. And on top of that, because it's a head-mounted device, there is a lot of motion. In order to reduce blur, and we need to reduce the exposure time. And when we do that, the problem of noise becomes even more exacerbated. On top of that, all of this is happening on video. So this is video processing at 60 plus FPS. And this community knows very well, like AI-based processing of videos needs some special treatment in order to make it temporally stable. The reconstruction has to be temporarily stable, especially when it is on a head-mounted device. You would observe it if you don't pay attention. And if these were not challenging enough, the challenge of power efficiency is equally hard. So on a VR device, most of these tasks you have a maximum budget of 100 milliwatt. If you go onto an AR device, you would likely be making it even 10x more constrained, like 10 milliwatt. And why are you power constrained here? First of all, it's a battery connected device. So you don't have a cable connecting your device to a power source. So this is limited by how much battery you can put there. And secondly, which is even more important, is the thermal limitation. So it is a head-mounted device. It is touching your skin. And every time you do computation, you're going to release heat, and that heat has to be dissipated. And you can't, that's limited by the surface area of the device, but also like where it is touching it. If you are touching a device with your hand versus it's touching your skin on your face, it's that also impacts the thermal envelope of the device. So that puts additional constraints on how you design the solution. Now, to solve this problem, there is no single silver bullet, you can imagine. I think the most important takeaway message here, besides understanding all of the different competing constraints which are there for this problem, is also that the solution is that of co-designing the entire pipeline end-to-end. So there is how you design your sensor readout, how you move the data from the sensor to the various stages of the image processing. Do you move it to memory? Do you read out of memory? Do you bypass the memory somehow? All of this contributes to the latency and the power. You might know that moving data to and from memory is one of the most expensive things you can do. So a sensor processing to display pipeline that is designed to avoid memory transfer as much as possible is the right direction to solve these problems. So, and this comes down to every stage of the processing. So not just sensing the sensor, but also like when you even coming down within the AI model, you have to design the model so that you minimize memory traffic. So that's where like designing very efficient backbones. There are a lot of efficient backbones literature that exists in the community, but they're primarily targeted towards classification tasks and so on. But when it comes down to high resolution image processing, this needs attention from the research community to be able to design efficient backbones for processing high resolution images. One direction is to design tiled model architectures. Some of these tasks do not require the entire global context of the image, so you can actually tile your input. Of course, like you have to design the model in such a way that it is aware of tiling so that you don't see tiling artifacts in the output. But what happens is when you tile your input and you process it in a tiled fashion, then you can design your tile size such that all of the intermediate computations, like the output tensors of one layer, which becomes the input to another layer, those can be cached in the most local memory that is closest to the compute. So you don't go to lower levels of memory, which burns a lot of power. That's around the efficiency. Temporal architectures, this is extremely important because temporal stability is, if anytime you process videos, whether it is video denoising, super resolution, video stability, temporal stability is super important, especially because it is being, like projected into your eye buffer, so you notice it. And we need to design better metrics for video stability. One of the techniques to address some of these problems around latency and power is also case-based foveated processing. Now, these devices have eye tracking cameras, so you know where you are looking at. And the way our eyes work, we have something called the fovea, which is ideally it's less than 5% of the entire field of view. And within that 5% of the field of view, our brain notices all of the details. And anything outside the fovea that we call as the periphery, in the periphery, we don't notice details. So we can take advantage of that, right? Like as long as your eye tracking is in the critical path. And remember, what matters at the end of the day is end-to-end latency. As long as your eye tracking can fit in that budget and you can process, do your denoising, do your HDR improvements within that, you can process just the fovea region. However, having said that, the periphery, even though we don't notice details, but we are very good at noticing temporal artifacts in the periphery. So when we are designing solutions for image processing, either denoising or super resolution or anything else, we can put some expensive models to do high quality reconstructions of the fovea, but the periphery needs special attention so that it doesn't produce any temporal artifacts. Even though it might be blurry, it doesn't have a lot of details preserved, but temporal stability is extremely important. And we have observed this with user studies that we are very sensitive to temporal instability in the periphery. So these are some of the interesting directions that are worth looking holistically in order to address the problem of denoising and dynamic range for mixed reality devices. That's all from my side. I'm happy to take any questions at this point. So at least so far in the work that we have, that I am showing here, like that's a fixed exposure. You are right, like multi-exposure can help there, but it complicates the pipeline a little bit more. But yes, it is. Yes, it's true. I mean, again, like it comes down to some trade-offs, like, like once you increase with head motion, it's kind of different from what we are used to with smartphones. Like when you do multi-exposure, of course, your longer exposure will have a lot of blur. Head motion is pretty large. We do not realize. So. Yes. I mean, so basically, like on the lower end, right? Like so, the SNR threshold is limited by like how much noise I can remove from the signal. Like if I can remove more noise out of what I read out from the sensor, then effectively I'm able to get more useful signal in the darker regions of the scene. So that's essentially I'm able to see more in the darker side of the image by doing a better denoising. So, I mean, this is always a kind of debate that always exists. Like, what can you build a fixed function hardware for versus what you should make programmable. Now, I mean, AI accelerators are one of the in-between design points, right? So of course you can have something like very general purpose GPUs, which can be used for running some of these AI models. Again, they are not the most efficient one. Like if you look at per watt, you are not going to get the best throughput per watt out of GPUs or general purpose hardware. On the other hand, of course, like, you can design a hardware and accelerator that basically just maps in the hardware the entire data flow of your denoising model. That's possible, but that's difficult to do, especially in a thing like AI denoising, where the algorithms are still evolving, like things change year after year. I mean, the model that we have today wasn't the model we had a year ago. So, so having some amount of programmability is really good. In general, like if you are careful around like the co-design process for the AI model and the hardware accelerator, then you can get a really good mileage. Like you can get really high efficiency and utilization of the hardware up to 80–90% of utilization if you do a careful co-design. And that's another key aspect of solving the problem holistically, is you have to design AI models while aware of where it is going to run. That's a good point. I mean, understanding the scene and semantically and be able to process it differently can potentially, you can have specialized, you can have, in fact, something like you can run something like you can have a different model for different noise range. You can train a model, you can specialize a model for different parts of the noise range that you want to cover. So there are some other design points as well that are possible. Yes, I mean, indeed, that's possible. So, I mean, at least as of now, we would apply like high quality denoising only for the fovea. For the periphery, you don't want to use the same model. There is obviously no reason to do that. That's a huge amount of cost you would pay for denoising, parts of the pixel where details are not so important. So you definitely want a different solution for them. What you want after you have processed them separately is to how you blend them together so that you don't have these boundary artifacts and all, but you certainly don't want the same solution for the fovea and periphery. Yeah, so this is extremely important actually, because once, so you want to run denoising in the early part of the pipeline where you have not done any kind of nonlinear processing on the images, because once you have done that, it's extremely hard to model that noise. And in order to train like super tiny efficient models that can do the best denoising for the amount of throughput you put in there, you want to specialize that model on the camera noise model, the noise model for that specific camera. So in that's, I mean, that noise model is not anymore, not very correct. You can't do a very good noise modeling in the later stages. So it's all in the raw domain. Yes. Can you please repeat that? Yes. Yes. So
you can collect images from a specific camera sensor, and then you can collect the statistics of that to model the noise. And once you have a very accurate noise model, then like if you have a or let's put it this way, the challenge in this kind of training a model is like the data sets, right? You want to do supervised training for the best quality results. In this case, if you have a really good noise model, you can get a noise model, you can train a noise model for any new camera sensor with just a handful of images. And you can have your, whole database of training data that you can inject at noise. So now you have the noisy image and the ground truth image, and you can just train a model for any new camera. So, yeah. Cool. Thank you.
Okay. I still have some questions. Okay, so very similar to the complexity of designing the denoising model for a specific camera is about the same like the complexity of designing an ISP pipeline.
Designing a denoising model for a specific sensor is way easier than, or I would say not easier. It's much more robust and reliable that you can actually ship into a product. Surprisingly, it's not. Like, so many of the later stages of the ISP pipeline, there are many nonlinear stages, and modeling for a neural network model to learn the entire range of those improvements or processing is very hard to learn unless you put a super gigantic transformer model that can just learn everything. But in order to ship something in that can run in these constraints, you need to be very specific to a very particular problem you are trying to solve. In this case, denoising.
Design something that should be adapted to some specific sensors.
Yes, for now, unless someone can come up with a new model that can just learn to generalize across different camera sensors and still meet the real-time constraints and power constraints.
Thank you.
Thank you.
Okay, so we are continuing the challenge report on 360 degrees omnidirectional image and video super resolution.
Hello everyone, my name is Minden Cao. Our challenge is 360 degrees omnidirectional image and video super resolution. Here I will introduce the datasets, methods, and the results of this challenge. 360 degrees or omnidirectional images and videos can provide users with an immersive and interactive experience and have received much research attention with the popularity of AR and VR applications. Unlike ordinary two-dimensional image with a narrow field of view, 360 degrees image can represent the whole scene from all directions. However, 360 degrees images suffer from the lower angular resolution problem, since they are captured by the fisheye lens with the same sensor size of capturing ordinary images. Although the 360 degrees images are usually in high resolution, their details are missing. In many application scenarios, increasing the resolution of 360 degrees images is highly demanded to achieve higher perceptual quality and boost the performance of following tasks. In this challenge, we aim to establish high-quality benchmarks for 360 degrees image and video super resolution and expect to highlight the challenges and research progress. This challenge can provide an opportunity for researchers to work together to show their insights and novel algorithms, significantly promoting the development of 360 degrees image and video resolution tasks. By resolving the low-resolution omnidirectional images, we can provide a more immersive user experience in various AR and VR applications. We provide two tracks. Track 1 is the omnidirectional image super resolution with scale factor 4, and track 2 is the video track with upsampling factor 4. The participants are required to develop algorithms to reconstruct the high-resolution omnidirectional images or videos from the degraded low-resolution counterparts. The newly corrected Flickr 360 dataset and the ODV 360 dataset are utilized for two tracks respectively. The weighted to spherically uniform peak signal to noise ratio, shortly as WSPSNR, is employed as a quantitative metric. As for the Flickr 360 dataset, we collected 3,100 omnidirectional images from the official Flickr website, and further captured 50 images with Insta360 degrees cameras. The scenes in the dataset vary indoors and outdoors, containing natural scenery, human architecture, and street scenes. The dataset is split into training, validation, and testing subsets, and the details are shown in the right table. While the ODV 360 dataset contains 250 videos in total, and each video contains 100 frames. Meanwhile, 90 videos are connected from YouTube and other public 360 degrees video dataset, and the left 160 videos are recorded by Insta360 cameras. The detailed configurations of the dataset split is shown in the table. As for the degradation setting, we follow the realistic downsampling strategy in OSRT. In details, we first transform the ERP images into the facial images, and then apply bicubic downsampling to get the degraded low-resolution facial images. Last, these images are reprojected into the low-resolution ERP images. The image track only applies its degradation to generate 4 times downsampled LR images, while the video track further performs video compression with FFmpeg library. Let's see the challenging results. There are 100 participants and 56 participants registered for 2 challenging tracks respectively. 7 and 3 teams enter the final testing phase and submit their results, source codes, and fact sheets in the image track and video track. The table shows the main results on the validation and testing subsets of these teams. We see that most valid teams surpass the baseline models with a large margin. Meanwhile, we observe that all teams' results are consistent in the validation and testing subsets in terms of WSPSNR metric. The winner of the image track is the BSR team. They achieve the best WSPSNR by adding extra data for training and further improve the model design. Specifically, they further collected omnidirectional images from the YouTube 360 degrees videos and designed a degradation learning network to learn the degradation in the Flickr 360 dataset. Meanwhile, the participants designed a 2-stage model and integrate the distortion maps into the model to improve the performance. MVideo team is the winner of the video track. They adapted the basic VSR++ framework to super resolve the omnidirectional videos and achieve the best performance in the validation and testing sets. In this challenging, all the teams in the image and video tracks consider the distortion characteristics of ERP images, achieve the performance improvement, demonstrating the effectiveness of considering the additional distorted priors. These results also indicate the differences between the omnidirectional image resolution and ordinary image super resolution. We also note that omnidirectional image and video super resolution shares similarity to ordinary image and video super resolution. The high-performance models for ordinary images, such as HAT model, also achieve high performance on omnidirectional images. Omnidirectional image super resolution aims to provide ordinary users with high-quality and immersive experience in AR and VR applications. The challenge has shown some promising results. However, some opening problems still require to be tackled, and some promising directions can be explored to further improve the performance. First, most methods only consider the distortion characteristic of ERP image, while the omnidirectional feature is also significant and requires additional explorations. Second, high-quality AR and VR applications usually require omnidirectional images with much higher resolution to provide user immersive experience. Yet existing models still cannot super resolve these images with such high resolution. Third, we should consider the blind settings in ordinary image resolution tasks to get visual-friendly images, and utilizing the generative priors to achieve this is a promising direction. Then, assessing the image quality under multiple projection types is practical since the omnidirectional images may be projected into different types for various applications. Last, as for the video resolution, the temporal colorization and the compression in omnidirectional videos are highly different from that in two-dimensional ordinary videos. More explorations on them may improve the performance significantly. Thanks for listening. If you are interested in this challenging and omnidirectional image and video resolution, you may visit our project page to acquire the datasets.
Okay, so this was the presentation. Let's see if any of the main authors are here. So could you say something if you are online? Okay, so apparently no response. So if you have questions, it's better to address them directly by email. Okay, now let's move to the next presentation and will be our work and our solution proposing this challenge. Currently, provided video has some everyone ready to our campaign. Okay, so the video provided doesn't work. Okay. This means that we can move to the next one, and let's see if Marco, are you ready? Okay, so let's move on to the next presentation, and we'll be the report of the real-time 4K resolution. Okay. Just. No.
I'm sharing on Zoom.
Yeah, perfect. Yeah, hello everyone. My name is Marcos Conde, and I'm going to introduce the real-time super resolution challenge. So, I think in the previous years we had like for scaling factor 4, and this edition we also have efficient super resolution, but we realized that we need more than efficient super resolution to solve some of the most industry challenges. So, for example, IMDN and RFDN are baselines for lightweight super resolution that you can find on the papers, but these methods process images at 10 frames per second. Actually, in this challenge, we aim to find methods that can process images at 60 up to 120 frames per second, and actually not patches, high resolution images. So these approaches should serve as a naive baseline for super resolution. And we also aim to have the first benchmark of this task. Now, summary of the challenge, we got over 200 registered participants, more than 500 submissions. We had 2 tracks, one that consists of upscaling from full HD to 4K, and one upscaling from HD to 4K. And we run the teams based on performance like PSNR, but also on random metrics. Now, what is the challenge of the challenge? The methods must be at least 3 times faster than the previous state of the art, like with super resolution, and we need new designs for real-time processing. And also, in contrast with most of the research out there, we use high-resolution images as a input. We don't use crops of low resolution. And the minimum requirement to participate was to be at least 24 frames per second. And methods must be reproducible, so we can show that everything is okay. We didn't constrain the participants on the dataset selection. They could use whatever public dataset they wanted, but we created a new test set of unseen images for 4K resolution, including render content from a real engine, digital art, and professional photography. 60 pixel cover. And the most important part, evaluation. Evaluating these models and measuring the runtime properly is key to ensure that we have achieved the challenge. So the participants had to submit their models. They didn't have access to the test data, and we run the models internally, ensuring that the visibility was okay, and models run the requirements that we specify. This is just a summary benchmark of the paper. You can find a complete table, but the take-home message is that most methods can process images under 7 milliseconds, which is more than 120 frames per second. And the reconstruction of the high-resolution image was quite bad. These are the RGB domain or the Luma. Now, as you can see in this plot, most of the methods fall into the 60 frames per second to 120 frames per second, which was a surprise. The performance in terms of metrics was also quite Now, how can we start to build a model for real-time super res? Something that we don't do in this paper. We'll just study summary of things. So we start from a shallow stack of convolutions, and we distinguish a couple of tricks. So one trick is to distinguish between high frequencies and low frequencies. Usually on the high frequencies, you want to preserve them, and it requires usually a high resolution. You don't want to downscale that information. So on high resolution, we apply low computation, and on low resolution, we apply high computation. That's another 2 techniques that are very useful for this problem, and most of the participants use them in the challenge, are reparameterization of the convolutional blocks. Reparametrization is a technique that is quite common nowadays on classification networks. And we moved and explored this technique to superres. That allows you to reduce some complex convolutional blocks into simple convolutional layers, like tracing the kernels. And besides that, shuffle is a very special technique. If you are familiar with super resolution, you might go with shuffle, the space also is known. And in this case, we apply the opposite operation. We go from space to depth. So we can reduce the spatial resolution while increasing the receptive field. And together, these two techniques, we also do a simplification of an enhancement block, which is quite the standard nowadays for image restoration. So yeah, in summary, our approach applies high computation, and most complex part of the method is concentrated around downscale features and low frequencies, and we put the low computation on the high resolution features. This kind of computation is mainly focused around spatial attention. We also found, you can check the amazing studies on the people, that the model design is way more important than the training data. Because as a matter of data we put into the shallow networks, they do the design to learn. Now, I will highlight the best two methods from the challenge, because actually are different from our baseline and also very interesting. So, the first method from Huawei included the modification of dynamic convolutions that they named symbol convolutions. They also use this pixel shuffle trick, this space to them, to reduce at the very early resolution of the image, such that you can apply a lot of computation on a low resolution image. And the second method is from 90s games, and it's an early work that applies distillation to solve this problem, and they aim to learn from a big teacher how to those hidden features or how to process the image from the teacher into the shallow state. Here you can see some examples from the data set. Obviously, at the paper you have everything at high quality, so check that overall the reconstruction is very accurate. And the conclusions from the challenge are one, that surprisingly we really managed to get release 10 methods that can process images at 120 frames per second. Okay, and these are already fully input images, not much is really. So we can use them online or offline to screen any image that we want. That is very important for online applications or other applications out there. Reparametrization is a standard widely used in this challenge. We also found that pruning, other kind of techniques that you can apply to reduce the complexity of the network, also help in the case of super resolution. And we also realized that it's not about the amount of training data, but the quality of the training data. And hopefully, and most probably, next time, we will also include quantitation into this challenge. So we can explore other dimensions of efficiency. Yeah, and these are the challenge papers. Actually, I think one of the authors is here in person for the presentation, but you can email them and read the complete description of them. Yeah, and finally, thanks to the sponsor of the challenge, Entertainment, and I'm ready to take questions from your side.
Oh. Yes.
So in terms of performance, in terms of runtime, it really improves a lot because except for the first convolution, the rest anyways, you kind of change the number of channels. So you need to worry, and the spatial resolution is way smaller, so you gain a lot of performance. And in terms of runtime, in terms of fidelity performance, I think the results are quite there in the sense that the decay is not that much, and actually in the paper you can find the details, but it's like expanding the receptive field. It's like the original paper was called like subpixel convolution, and in this case we are doing the opposite, but the effect is quite similar. The pixel unsampling and pixel sampling, both techniques that are very useful for supervised. Can you repeat that? No hurricane. Actually, we got many different implementations. The only requirement was 24 frames per second and 1 inch. There were many participants that submitted models that some frameworks. We didn't support augmentation. That was the only point. And the models were tested on floating point 16. Sure. You can read all the details out. And yeah, as I said, we want to see what happens, and hopefully the performance we don't lose too much performance. Yeah.
Okay, thank you. Okay, so now we'll continue with one of the top methods in this challenge. We have a presentation provided by the authors. We'd like to introduce our entire paper named as ConvSR, Fast and Lightweight Super Resolution Network with Assembled Convolutions. In recent years, most media contents are produced and distributed in high resolution like 720p, 1080p. However, these high-resolution images and videos cannot achieve the expected visual effect due to the limitation of the internet bandwidth. Previous works mainly aim at lower input resolutions like 540p and 640p. Their real-time performance cannot be guaranteed on higher input resolutions. Furthermore, it's very intuitive to apply different enhancement methods on the patches with different textures and contents. Designing an efficient dynamic network will also become the key to solve the above problems. In this paper, we revisit the efficiency of several network designs and propose a lightweight block named Assembled Block which can adaptively assembles the convolution kernels according to the input features. Architecture of our method is demonstrated in Figure 1. There are several key points to our method. The first one is pixel and shuffle. By using pixel and shuffle, we can restructure the features, reduce their resolution, and increase the number of channels accordingly. According to equation 1, assuming the number of network channels remains unchanged, adopting pixel and shuffle do not change the flops of the first convolution layer, but greatly reduce the flops of subsequent convolution layer. Therefore, by selecting appropriate number of channels and pixel and shuffle coefficients, the network can achieve higher efficiency. The second key point is the skip connection. Besides the convolution layers, skip connections also occupy a large amount of computational resources. They not only require additions of 2 feature maps, but also have to cache the previous feature map which consumes more memory. We discard all intermediate skip connection and replace the classical interpolation used in the global skip connection by repeat upscaling proposed by ABPN. The third point is the assembled block. By reviewing the idea of divide and conquer, we propose assembled convolutions which can adapt convolution kernels according to the input features. In AsConv-SR, we replace the residual block with the assembled block. Each assembled block contains one control module and 3 assembled convolutions. Control module, which consists of convolution and pooling, can generate the assembled coefficients from the input feature map. And the function of assembled convolution is 1. Multiplying the coefficient and the basic convolution kernels to obtain a classical 3x3 convolution kernel. Second, perform convolution on the input feature using the convolution kernel obtained from previous step. Note that the control module and the multiplication between coefficient and basic kernels are performed at the weight dimension, so their computational cost is very small compared with the convolution performed at feature dimension. Therefore, using assembled convolution will not increase too much runtime, and can improve the effectiveness of the network. Dynamic convolution generates the whole convolution kernel in a linear combination of the bases. An assembled convolution assembles the optimal convolution kernel for each channel. Compared with dynamic convolution, the assembled convolution we propose has finer granularity and higher flexibility in parameter generation, leading to a better performance in super resolution. We compare AsConv-SR with the state-of-the-art efficient super resolution models. We train 2 versions of our model, AsConv-SRL denoting the model with a larger scale and AsConv-SR a smaller one. As shown in Table 1, none of the methods can achieve the real-time performance with 1080p input except ours. Our method also achieves the best scores on every benchmark dataset as shown in Table 2. Figure 6 demonstrates the visual results of other efficient SR models and our method. In general, our method shows competitive performance in sharpening the images and restoring compressed textures. In the ablation study, we evaluate the relationship between fidelity improvement and runtime consumption of various network structures. Adopting pixel and shuffle, removal of residual and bias does not deteriorate the performance of the model in PSNR and reduces runtime at the same time. Reducing the number of channels in the network increases the score by greatly reducing the runtime, but also reduces the PSNR. Assembled convolution can improve the PSNR without increasing the runtime, resulting in a significant score improvement and achieving highest efficiency among all the models. As demonstrated in Table 8, our model also wins the first place in NTIRE 2023 Real-Time Super Resolution Track 1. In conclusion, we propose a fast and lightweight super resolution network with assembled convolution for real-time super resolution. We revisit the efficiency of several designs such as pixel and shuffle, repeat upscaling, residual and bias removal. Furthermore, we design a lightweight block named assembled block which can adaptively assembles the convolution kernels according to the input features. By introducing these designs, our model runtime is significantly reduced while an excellent super resolution performance is kept. Quantitative experiments demonstrate the competitive performance of our model. That's all of our presentation. Thanks for your attention. If you have any question, please contact us.
Okay, so this was the presentation. Now, let's see if it's somebody from Huawei here. Okay, no one person. Maybe online. Okay, is anyone? Okay, then, yeah, if you have questions, better contact directly the main authors. Okay. The next presentation is about robust, efficient, and component-specific makeup transfer.
Hello everyone, and welcome to the NTIRE workshop at CVPR. Today I'm excited. Hello everyone, and welcome to the NTIRE workshop at CVPR.
Today, I'm excited to present our paper titled Beauty REC, Robust, Efficient, and Component-Specific Makeup Transfer, which proposes a novel approach for accurate makeup transfer in images. In this presentation, I will cover the following topics: introduction, challenges, our proposed method, and conclusion. Makeup transfer is the problem of transferring the makeup style from a reference image to a source image without changing the identity and the non-makeup regions of the source image. Virtual makeup applications allow people to find well-suited makeup styles online. The following image provides a great illustration of the makeup transfer task. The left is a reference image, the middle is source image, and the right is the transferred result. However, transferring makeup styles between a source image and a reference image is challenging. The large misalignment is easy to lead to the makeup leak. The use of real-paired training data is almost impossible. The identity and the non-makeup regions of source image are fragile in the process of unsupervised learning, resulting in distorted textures and artifacts in the result. Efficient makeup transfer is also demanded, as transfer algorithms are usually deployed on resource-limited and real-time devices, such as mobile platforms. Our main contributions are summarized as follows. We propose a component-specific correspondence for accurate component-to-component makeup transfer. We propose a transformer-based global makeup transfer, which models the long-range visual dependencies between the reference image and the source image. We employ a content consistency loss coupled with a content encoder, which endows our method with an extremely lightweight makeup transfer structure. Beauty REC is a single-pass structure, as shown. First, the content features of the source image are extracted by the content encoder. With the use of content consistency loss in feature space, the content features are insensitive to the makeup of the source. Second, a global style encoder is used to obtain the global makeup style of the reference image, while a component style encoder aims to extract the style features of different components of the reference image. Third, with the features of lips style, skin style, and eyes style of the reference image, we transfer them to the corresponding component of the source image using a component-specific correspondence. Fourth, with the global features of the reference image, the long-range visual dependencies between the reference image and the source image are modeled by the multi-head self-attention. At last, image reconstruction is employed to integrate features and produce a makeup transferred image. The loss function includes the following terms: content consistency loss, to reduce the effect of the makeup of source image on makeup transfer performance and preserve the content of source image in the transferred result. We constrain the content consistency in feature space. Second, following previous method, our method also uses the makeup loss that consists of local histogram matching on different components of the source images and the reference image. Perceptual loss, to preserve the perception similarity between source image and the transferred result, we use the perception loss. We also employ local adversarial losses to further enhance the significance of the local makeup style. We show the feature changes in the process of component-specific feature transfer. As shown, the feature of source content changes in the specific regions from lips, skin to eyes, using the component-specific correspondence between the reference style features and the source content features, thus implementing the component-specific feature transfer. Additionally, it is insensitive to the order of feature transfer. We also show a set of results of the model with different component-specific transfer orders below. As shown, we achieve almost the same transferred results. Please look at this figure. Our method can transfer diverse makeup styles, handle different ages, and preserve the identity and the non-makeup regions of the source images. In the right of the picture, our method can implement flexible makeup transfer, such as handling the large spatial misalignment between the reference image and the source image, achieving the makeup removal by swapping the source image and the reference image, and producing the component-specific makeup transfer, only lips. In this figure, compared with the state-of-the-art methods, our method successfully transferred the makeup from the reference images to the source images. It does not introduce makeup leak and artifacts, and reserves identity and non-makeup regions of the source images well. Our method achieves the highest best selected ratio, which suggests the better performance of our method for accurate makeup transfer than the compared methods. Our method has the lowest trainable parameters and flops and the fastest inference speed. The results suggest the efficiency of our method. While there are some makeup datasets, such as MT and web datasets, their diversity is insufficient and the resolution is low. Especially, some of them were collected several years ago, thus excluding the new fashion styles. To supplement existing makeup datasets, we collect a new dataset from the internet, named Beauty Face. It contains about 3,000 high-quality face images with a higher resolution, covering more recent makeup styles and more diverse face poses, backgrounds, expressions, races, illustration, and so on. Besides, we annotate each face with parsing, which benefits more diverse applications. We show some examples of Beauty Face. Okay, at last, I will summarize the main contributions of our work. We propose a makeup transfer method to overcome the limitations of previous methods, such as robustness, efficiency, and the compatibility of content preservation. The success of our method mainly lies in the component-specific transfer, together with the global transfer and the content consistency loss. The lightweight structure and the robust performance of our method outperform the state-of-the-art methods and make it suitable for practical applications. We also contribute a new makeup dataset, which facilitates the research of this research area. Thank you for your attention. I hope you found our presentation on Beauty REC informative and engaging. I would now like to invite any questions or comments from the audience. Please feel free to ask anything related to our work. Thank you.
Okay, so this was the presentation. If you have questions, it's better to address them directly to the main authors. Now, because we have this request from Mustafa, well, he provided a YouTube video. Mustafa, if you want, and if you have a 5 minutes presentation, then maybe you could directly share your screen and play the video.
Hello, Radu. Is it possible if you can play the video for us, please? Because I'm on the phone and it's about like 2 a.m. here, so I don't have time to switch to my laptop. Can you do that, please?
Typically, you should have provided the video.
Actually, we provided the video, but it's on the it's on YouTube.
YouTube link.
Yeah, it's a YouTube link. Yeah.
Okay, so now what do you want me to do? To stop my broadcasting to run your YouTube?
Oh, I don't know if you can do that or not. I don't know if it is possible or not.
This is the issue.
Oh, okay, that's the issue. Okay.
Okay, so maybe somebody else that is on Zoom and can directly go on YouTube and play the video. So who has some connection? Okay. Yeah, so until we are figuring out, maybe the best is to move on to the next presentation. And we have the invited speaker is John Barron from Google Research, and he will discuss about this. Okay.
This is gonna stay here?
Yes.
Okay. I have to do a bunch of display stuff. Right. The Zoom thing looks. Oh. No, I know, but can we give it the feedback? My mic's off.
But your shell structure.
I would like to resolve that. Seems like if that's not muted. I am on Zoom. Are we gonna do the feedback thing? Is this what we want to do?
Okay, so sorry for those that are online and were unable to hear the presentation. We had some issues. Okay, so now let's continue with the next presentation. Florian.
Okay. Went on mute? No. Okay. Good. So hello again. My name is Florin Vasuianu, and together with Tim Seisinger and Professor Timofte, the host here, we're going to introduce the entire 2023 image shadow removal challenge. So we're going to go through some introduction, the challenge data, winner solutions, and the results. And we're going to do some conclusion. On the right side, you have some sort of motivation for shadow removal. You can see like some sort of a nightmare of a beginner photographer that tries to get some shots in the golden hour with some people that are moving around. The current state of the field, it's quite like that. Usually the data set that we have are focused on the natural light. Very simple scene with like a few interactions. We have low variety in terms of shadow casting objects. Again, we have low variety in terms of scene objects and surfaces. And of course, sometimes we have semantic misalignment or color misalignment for the objects or surfaces that appear. Yeah, so in the end, we can conclude that the phenomenon isn't really sufficiently studied. There is more that we can do to actually have a better better understanding of what's happening. And yeah, here we have some examples from the STD benchmark, one of the most, let's say, popular benchmarks in the field. You can see here on the top left, we have some semantic misalignment between the images. Here we have part of a shoe in the image that, of course, doesn't appear in the input image. And of course, here on the bottom right, you can observe the color misalignment between the images. Of course, shadow means some sort of a transformation that affects light. And when you have light affecting transformations, it becomes very difficult to actually align in terms of colors. So we decided we want to explore more, and we created this this setup where we have a high resolution camera sensor that is going to capture the image of a scene, and in the scene, of course, we are going to have some objects, and apart from those, we also have shadow casting objects that are outside the scene, but their shadows interact with the self-casting shadows from the objects inside the scene. And of course, for this, we use a combination of two lights. The first light is a diffuse light that interacts with a softbox that is going to equally distribute the light throughout the scene. And for the shadow casting, we use a directional light. For the current setup, you're going to find more details in the presentation that follows. The data set that we have public consists of 1,200 image pairs that are roughly aligned. Of course, I told you like the limitations and the difficulties into getting like the purely aligned data. Of course, we hosted our challenge in Codalab, so we have to thank them for the support. We had the development phase with 1,000 image pairs for training and 100 for validation. along these images in the final testing phase. Another 100 images were made public, and 10 of these that we consider the most challenging we used for the user study that helped in differentiating between similar performance level solutions. So here we have some examples of the images we got in the dataset. We focus ourselves into complex textures, very fine-grained objects, and different types of objects. Of course, in the presentation that follows, you're going to find out more about the objects and what was the algorithm behind the splitting and so on. Now we have to mention the winner solutions. The first solution is the one proposed by the MTCV team. They proposed a model that's called pyramid ensemble structures that was based on NAFnet. NAFnet is quite a popular backbone nowadays towards fault, so everybody went through this. The important details about this method are the usage of the pyramid inputs and pyramid stages for training. So basically, they train the model at different resolutions, capturing features at different levels. And in the end, they deploy some model ensemble that they call shadow ensemble based on 10 maximum function applied pixel-wise. The second winning solution, because the results were quite similar, so we have two winners. It's the team IRA SD. Of course, they extend on their previous work that's called IRSD. It's a diffusion model that's quite popular. And again, they're using NAFnet as backbone, adding some additional parameters for the timestamp in diffusion. And of course, as I told you in the beginning, the data was roughly aligned, and they optimized also for pixel alignment, and that improved significantly their performance in terms of perceptual metrics. Here we have the quantitative results of the teams that we had. We had 19 teams that submitted solution fact sheets and valid solutions to be ranked in the challenge. And of course, we did our ranking based on firstly the mean opinion score, actually the results for the user study, and the most correlated metric with the mean opinion score was actually the LPIPS. Then the last three criterions were the SSIM, the PSNR, and another criterion that's based on the gain per million parameter used. And this is how we did the leaderboard. Here we have some qualitative results. Two of the most challenging samples that we had in the testing split. You can see how different solutions are actually performing on challenging pictures and cluttered scenes with more interactions between objects, and also shadows casted by some other objects that are not appearing in the scene. And of course, if you want more details, you can check our GitHub page. Also, the data is available there. We have to thank everybody for the effort put into the challenge, for organizing the workshop, and also for the participants in the challenge and their effort. So if you have questions, feel free to talk. I will keep that. Okay.
Yeah, now it's like, so I'm gonna present WSRD, which is basically like our data set and also the baseline method we proposed. So as Florian already said, basically like the thing we went from is like, we only have like simple scenes, which are like shadow casted on like a surface, but there's like no self-shadowing. And also because of the lag on like controlled environments, you have like slight differences in like luminosity between different images. So yeah, we wanted to solve that with our data set. So basically we only have like controlled, like a completely controlled environment with scale objects. So for this here, we use one diffuse light and one direction light. Both of these are in this situation fixed to like keep it still kind of like it's like a first proposal. The diffuse light makes sure that there's no hard like shadows on the objects if we are in the case of a non-shadow frame. And in the case of a shadow frame, we also activate the direction light. And then there's hard shadows, but the diffuse light makes sure that there's still information in the shadow areas. Because if you only fire the direction light, the scene is like the shadows are so hard that there's like from the camera sensor very little information. But there's actually like we tried it and it kind of works when you only do the directional one, but it's probably a much harder task, which is not very realistic. So yeah, and the camera is always also in the same fixed position. For the occlusion, we have like the two objects, which there's one like directly in the scene frame with self shadows, and we also have like one object that's outside of the scene in some pictures, and we also have a variety of backgrounds. Yeah. So in total, we have like 1,200 roughly aligned images. This is because in the beginning, we still had no camera remote. So if you want to like collect like data sets with paired images, use a remote. It helps. Also, the other thing is because we have like two lights, I needed to align the luminosity of the images still. But for example, like white balance is the same between both images. And because like it's about like 1 EV difference, so that was like fairly easy to correct. But yeah, you can see like I shows like a variety of objects, about 100 in total. We have like of like varying sizes, also some real stuff like the main board may have in some situations, but also like tiny houses or this like model roller coaster, which produce like very complex shadows. Yeah, and for the surfaces, I mean, here, unfortunately, on the examples I chose, there's not really much diversity, but we had like, we had fabrics, we had cardboard, and yeah, other types of surfaces. But the diversity here especially can still be increased a lot. For the data set split, as we mentioned, we made sure that there are some surfaces that are only exclusive to the test and the validation set, or the validation set rather. And there's also objects that are only apparent in those. So we checked for the generalization capability of the methods on the completely unseen surfaces and objects. Yes, so this is the baseline we proposed. It's a unit with like a distillation in the middle, and this has mostly been Florian's work. So if you have like any specific questions about this, you probably could direct the questions to him. But it gets fairly good performance in both our new proposed data set and also in the this slide already. Yeah, in the ISTD, like in the old data set where you only had the surfaces with natural light and shadows. So yeah, this is a few examples still. Up on top is the ISTD set. You can see that it's like there's like very little artifacts. For example, like Shadowformer still has some darkening spots, or like other methods like change the areas that shouldn't be changed. And on the our new data set, you can see that it's like able to like reconstruct like complex patterns and remove complex shadows. Yeah, so this is it. For any questions of the data set, you can ask me if there's any. So yeah. Yeah. Okay.
The solution proposed by each individual laboratory for the quality assessment.
Okay, so question for those that are attending online. Is the Mate1 team online? The authors of pyramid ensemble structure? Okay. So pyramid ensemble structure for higher resolution image shadow removal. Okay, so if not, then move on. The next presentation, diffusion, and we have provided pre-recording. In this video, we'd like to present our work. Hello everyone. In this video, we'd like to present our work with Diffusion, on very large-scale realistic image restoration with latent space diffusion models. Our main contributions are summarized as follows. We present a unit-based latent diffusion model for large-size image restoration. We also propose to change the diffusion-based network from unit to NFNet. We perform a comprehensive study of cell training strategies to improve the restoration performance, and we evaluate our approach on extensive real-world and synthetic data sets. Our method leverages IRST as the base model for realistic image restoration. Consider the mean reverting ST as equation 1. IRST proves that it has a closed form solution for all times, and the transition curve is a Gaussian with mean and variance. Specifically, as t is large enough, the mean would convert to mu, and the variance would convert to lambda. By letting mu be the LQ image and x0 be the HQ image, the power of ST would naturally simulate the image degradation process. Iteratively running a diffusion model is notorious time-consuming. Latent diffusion compresses images and performs diffusion on the latent space, but it requires VE with gain learning, which is unstable and would miss details in the reconstruction. In this work, we propose a unit-based latent diffusion, which has hidden collections from encoder to decoder and uses latent replacing learning strategy. Our model is thus stable in training and traces cross-modality images, and the restored results are also accurate. The latent replacing learning strategy is shown in this figure. We would like to combine LQ hidden collections with HQ latents to generate high-quality images, which could ensure that transforming the latent to HQ space would restore the HQ image accurately. Here is a modified nonlinear activation for a block, which embeds the time into a network and the same as other diffusion models. The NAFnet performs better than UNet, while requiring less parameters and flows. We also analyzed 4 training hyperparameters: noise levels, denoising steps, training patch size, and optimizer and scheduler. All results are performed based on the image shadow removal task. In the experiments, we apply our diffusion model on 4 different tasks: image shadow removal, stereo image super resolution, Bokeh effect transform, and HR non-homogeneous dehazing. Here are the shadow images and our results, and our method won the 2nd place in the NTIRE image shadow removal challenge. Here are stereo input images and our results. For the Bokeh effect transform task, given the length information, our model can generate the corresponding images. For the dehazing task, the input images are almost 6,000 times 4,000 resolution, which is very difficult to normal diffusion models. We apply our unit-based latent diffusion model on this task and achieves good results. In summary, first, we present a unit-based latent diffusion model for large-scale image restoration. We change the backbone from UNet to NAFnet to accelerate the diffusion process. We comprehensively analyze different training strategies to improve the results. We also apply our model on extensive experiments and win the 2nd place in the NTIRE image shadow removal challenge. You can scan the QR code to access our code and pre-train models. Thanks for your listening.
Okay, so this was the presentation. Okay, I see Jiwei.
Okay, hello.
Okay, so we have the first author here. If there are questions. Okay, so if there are no questions, because we get a bit behind schedule. It's more presentation. Okay, the next presentation is about the quantum annealing for single image resolution. And we have a presentation provided by Yao Chang. Is here. Okay, so let's play.
Hello, this is a presentation on the paper Quantum Annealing for Single Image Super Resolution by Hanyao Chung, Suresh Kumar, and Luc van Gool of ETH Zurich. This paper is part of the CVPR 2023 New Trends in Image Restoration and Enhancement workshop. To preface this presentation, I would like to provide an overview of our work. Our work is an early exploration of applying quantum computing to the image enhancement task of single image super resolution. The reason for this exploration is the exceptional capabilities of adiabatic quantum computing to use quantum phenomena such as superposition, entanglement, and adiabatic evolution to solve combinatorial optimization problems with exponential speedup over classical computing. As such, in our approach, we cast the super resolution problem into one of combinatorial optimization, and in particular, we use a quadratic unconstrained binary optimization formulation for sparse coding. Having developed our approach, we evaluated it on popular super resolution datasets. To provide more context, out of the 2 types of quantum computing available today, in this work, we focused on adiabatic quantum computing. In this type of quantum computing, hardware advancements have made it increasingly possible for it to be applied to solve practical computer vision problems in recent years.
The fundamental problem that is solved by adiabatic quantum computing is the quadratic unconstrained binary optimization problem, or QUBO problem. In this problem, Z is a binary vector to be optimized with respect to the matrix Q containing quadratic coefficients determining the quadratic terms, and the vector B determining the linear terms. Once defined, the QUBO problem is embedded onto a physical lattice in a quantum processing unit, and then optimized by quantum annealing. Clearly, the QUBO problem is a highly specialized combinatorial optimization problem, and therefore, in order to solve super-resolution using adiabatic quantum computing, it is necessary to find an appropriate formulation that casts super-resolution into the QUBO form. For this, we refer to the work Image Super-Resolution, a Sparse Representation of Raw Image Patches by Yang Jianchao and Ma Yi and colleagues from 2008. To train our algorithms, we followed the approach of Yang Jianchao and colleagues 2008. We evaluated our algorithms on the Lena image and set 5. We developed 3 algorithms in total, namely raster regression, which carries out conventional sparse coding, classical annealing, which solves super-resolution by simulated annealing on a conventional computer, and quantum annealing. All of our algorithms carry out 3 times upsampling. Following evaluations, overall we found that classical annealing and quantum annealing achieve the same accuracy. We found that annealing-based methods outperform bicubic interpolation and conventional sparse coding on a full Lena image in set 5. However, as expected, we found that the performance of sparse coding approaches nevertheless fall short of state-of-the-art deep neural networks such as SwimIR.
Okay, so this was the presentation. So is the first author or the second author here? Okay. If not, then let's move on to the next. Efficiency, distillation, and iterative pruning for image resolution.
Hello everyone, today I would like to share with you our recent work in NTIRE competition called DIP Mid-Efficiency Distillation and Iterative Pruning for Image Super-Resolution. The NTIRE competition is one of the most influential global competitions in recent years in the field of image and video restoration and enhancement. This year, NTIRE opened tracks for some of the most challenging problems in this field. We participated in the Efficient Image Super Resolution track and achieved first place. First, let me introduce the basic task, Image Super Resolution Reconstruction. Typically, a high-resolution image is given, which undergoes kernel degradation, downsampling, and adding some noise to obtain the corresponding low-resolution image. During training, the low-resolution image goes through a CNN network to generate the super-resolution image, and the high-resolution image supervises the training of the model. The Efficient Super-Resolution track is a relatively popular track, and a large amount of research has been conducted on various large-scale model structures. However, designing an efficient lightweight super-resolution network for practical deployment in real projects is also a popular direction.
This year, the efficient SR track of the entire 2023 competition mainly focuses on a 4x super resolution task, with the evaluation metric being based on achieving a PSNR of 29 dB on the DIV2K validation set, while also comparing running time, number of parameters, flops, activation quantity and depth. One important consideration for the efficient SR evaluation metric is that having lower parameters and flops does not necessarily mean faster running time. For example, we used the shift operation from Ghost SR to process some features during practical operation, which reduced the parameters and flops by about half. However, the actual running time was basically unchanged compared to the original. This extra time usually comes from some multiplication and addition operations. Now, let me give you a brief introduction to some representative works from previous years. This year is the 4th efficient SR competition, and the winners of previous years were IMDN, RFDN, and RLFN. IMDN extracts hierarchical features through a multi-level distilled block. RFDN builds on IMDN by introducing a pointwise convolution to change dimensions. RLFN analyzes speed bottlenecks and simplifies network design by removing redundant add and concat operations to further improve inference speed. This is a comparison between our approach and previous methods in the last few years. As you can see, our method has advantages both in terms of running time and number of parameters. Now, let me give you a detailed introduction to our method, which consists of 3 steps. The first step is to enhance the ground truth. This idea is inspired by a recent paper called HGGT, where they introduced human-guided selection during the GT enhancement process. In our practice, we found that using a model to enhance the GT alone helps small models learn textures and details better. Specifically, we used a 1x super resolution network to enhance the original GT. We chose the state-of-the-art HAT network for this purpose and retrained a 1x model based on its structure. The following images show the difference between enhanced GT and original GT based on our approach. Original GT may be smoother in some areas, but we can see that enhanced GT has richer textures and details. This is another example. To further improve the accuracy of small models, we approached it from both structural and training method aspects. Specifically, in the second step, we used a multi-level distillation method. First, we trained a large teacher network using the enhanced GT. Then, we distilled the student network at both the feature level and image level using the teacher network. The design of the student network is based on some classical structures used previously. We added the reparameterization technique to the RLFB block, including serial convolution reparameterization and parallel reparameterization. This method brought us lossless accuracy improvement, in addition to feature-level distillation supervision in the loss. We also supervised the final output image using large model output image supervision and enhanced GT supervision. Furthermore, we used some tricks to train our small model, such as fine-tuning with L2 loss after convergence of L1 loss training. The final step is an iterative pruning process. We reparameterized the results from the second step and pruned the model. After each pruning, we performed fine-tuning until convergence before proceeding to the next round of pruning. We used L2 pruning as our pruning method. Our team also tried introducing weight normalization and pruning based on sorted weights, but ultimately found that the effect was comparable to the iterative L2 pruning. Therefore, we chose the simpler L2 pruning method. We compared our approach with some state-of-the-art efficient SR methods from recent years based on objective metrics. As can be seen, our method is almost 1/4 faster than last year's champion in terms of time, and our number of parameters, flops, and activations are all superior to last year's champion. Next, we have some subjective image comparisons. As can be seen, in our method, the stripes and other densely textured areas in the wallpaper are clearer. This is another example. Our method is more robust against aliasing artifacts. This is because we use enhanced GT and intermediate results from the large model to guide the training process. Compared to directly learning from high-resolution GT, intermediate results from the large model are easier for the small model to accept. These are some ablation experiments. The first is an experiment on whether to use enhanced GT. We can see that after using enhanced GT, the performance of the teacher network even slightly decreased. This is because the teacher network itself has strong learning ability, and the distribution learned from enhanced GT is inconsistent with the original GT, leading to a decline in performance. On the other hand, our student network has very limited capacity and cannot directly learn clear textures. Therefore, we achieved good results by using enhanced GT to guide it. We compared the effect of distilling using different features and found that distilling with deeper features leads to better results than using shallow features alone. Moreover, using both shallow and deep features for distillation results in the best performance. These are two sets of ablation experiments related to pruning. The first one shows the changes in number of parameters after 3 rounds of pruning. We can see that the decrease is not significant after each round, which is a result of our small and multiple pruning strategy. However, this approach also brings more complexity to the training process. The second set compares L1 and L2 pruning methods. Both operations are performed on weights during pruning. With fine-tuning, L2 pruning is better than L1 pruning. This is a display of the results of this competition. There were more than 40 final submission teams in this competition, and our method achieved the fastest running speed. To summarize our work, first, we adopted the approach of using enhanced GT to train lightweight networks. Second, we combined distillation and pruning methods to greatly improve running speed while maintaining a certain level of accuracy. Finally, we achieved first place in NTIRE 2023 Efficient SR track. Thank you for listening.
Okay, this was the presentation. If the authors are okay. So, can you just give me a sign? So, the authors are not online, then let's move on to the next. Next presentation. The next paper. Another method in the same efficient image resolution challenge. Yes. In this particular case, on a GPU. Is a NVIDIA GPU, the details and so on are on the report, but it's just a standard GPU. As far as I remember, it's supposed to be just a normal GPU, maybe 2000 series or something like this, or 3000. Okay, so a single residual network with ESA modules and the distillation. So the Hunan team, are the members here or not? Okay. So let's see. Back and next presentation.
Hello everyone. In this video, we'd like to present our work, Diffusion, a very large-scale realistic image restoration with latent space diffusion models. Our main contributions are summarized as follows. We present a unit-based latent diffusion model for large-size image restoration. We also propose to change the diffusion-based network from unit to NAFnet. We perform a comprehensive study of cell training strategies to improve the restoration performance, and we evaluate our approach on extensive real-world and synthetic datasets. Our method leverages IRSD as a base model for realistic image restoration.
The previous one. Sorry about that. Okay, so this is the correct.
Hello everyone, I'm Xiaoming from Southwest Jiaotong University. We are delighted to present our latest work to SR community, Large Kernel Distillation Network. The task of single image super resolution involves recovering a high-resolution counterpart from a low-resolution image, which is a challenging and ill-posed problem. We propose LKDN, a lightweight SR network that achieves state-of-the-art performance of efficient SR models. Our main motivation is from the large kernel decomposition and the structural reparameterization. Recent advanced research has shown that large convolutional kernel can strengthen long-range dependency, leading to stronger representation ability. One way to achieve an equivalent large convolutional kernel with few parameters is by decomposing the convolutional kernel into a pointwise convolution, a depwise convolution, and a depwise dilation convolution. Reparameterization is also a practical technique for designing lightweight models that can improve performance without increasing the inference burden. The diverse branch block introduced structural reparameterization by combining branches of varying scales and complexity to enrich the feature space. During inference, these branches are merged into a single convolutional layer. It has been demonstrated that reparameterization is a general approach for designing lightweight models. Taking inspiration from BSRN, the champion of the model complexity in the NTIRE Efficient SR Challenge last year, we rethought its design and made several modifications to improve its performance. LKDN incorporates the novel large kernel distillation block. While CCA and ESA are efficient attention modules typically used for lightweight SR networks, we found some of their design to be redundant. As shown in Figure C, we replace them with more efficient modules using large kernel attention. This approach utilizes large kernel decomposition to break down a convolutional kernel of 17 into a pointwise convolution, a depwise convolution, and a depwise dilation convolution, resulting in improved efficiency and effectiveness. Additionally, skip connections are widely used to prevent degradation in deep models. However, excessive skip connection can lead to increased memory access and inference time. To address this issue, we replace the skip connection in ESDB with a reparameterizable skip connection and added the branches of blueprint severable convolution. As shown in Figure D, we introduced RBSB to replace BSRB with a reparameterizable skip connection applied to the pointwise convolution and the depwise convolution. Regarding the optimizer, Latent optimizer is a recently proposed method that has demonstrated effective improvement in various deep learning tasks by achieving faster convergence. Since most SR models use ADAM as the optimizer, we utilize ADAM for SR tasks and observe faster convergence. In the ablation study, we first evaluate the effectiveness of the proposed large kernel attention block and observe that it improves model performance with lower computational cost compared to CCA and ESA. Next, we demonstrate that skip connections are redundant in BSRB and can be removed. Instead, using structural reparameterization can lead to improved performance. Furthermore, we tested the effectiveness of the newly proposed ADAM optimizer and compared its performance with ADAM optimizer.
Our findings indicate that ADAM converges 5 hours earlier than ADAM with varying level of performance improvement. We propose 2 versions of LKDN, a small version for the NTIRE challenge and a normal version. The main difference between the two is the number of LKDB and the intermediate feature channels. Here is a general comparison with the state-of-the-art lightweight SR models. To ensure a fair comparison with the previous methods, all our models are trained on the DF2K with 2,615 images pairs instead of the newly proposed LSDIR datasets. Therefore, there is still room for further improvement of LKDN. And here is also a performance and the complexity comparison. Here is the visual comparison, and our method provides clear edges and less artifacts. Thank you for your attention.
Okay, so if the author is not present, just take on one to the next presentation.
Hello everyone, I'm Qian from Xi'an University of Post and Telecommunication, the co-author MDRN for Efficient Image Super Resolution. Our team are very glad to be invited to present our winning solution at the CVPR Workshop 2023. Unfortunately, we are unable to make it on-site due to the visa issue. For efficient image super resolution reconstruction, we divided the attention computation in DSA into 2 parts. We show attention map for these 2 branches of ESA, branch A and branch B. Found that attention area from the large receptive field branch is ambiguous, and the large area of lower information content are overweighted, just like the sky. But this is not the area that the network should focus on learning. Why does this problem arise? In fact, one of the original intentions of ESA is to have a larger receptive field. In this branch, convolution with a strata of 2 and max pooling of with large kernel size of 7 is chosen to expand a receptive field. As QC, compression of spatial information can lead to inaccurate attention. So, in order to design attention mechanisms that accurately find a key information in large receptive field, let's start with a simple example, where the DN represent original feature maps that have been spatial downsampled and restored to original size, as shown by graduating the multiple dispersed branches from cross to fine. Attention scores gradually converge to those key positions, realizing focused on key information in large receptive fields. The evolution designed from ESA to our MDSA is shown here. Specifically, the dispersed branch of the single level in ESA is extended to multiple levels. And in addition, in order to give more consideration to high frequency information of image patches, we also referred to local invariance to improve the perception of textual details. It's noting that we only calculate the local variance on branch of largest size to avoid too much computation. And we also add a large residue to optimize information flow. As far as channel attention, at first through experiment, we found that simply
aiding CCA model is not robust to improve the performance. Inspired by RCN, we also combine the residual structure with CCA. Of course, using normal convolution would bring a huge amount of computation and parameters, so we use lightweight convolution as alternative. At the same time, we further insert CCA between the convolution layer. The MDSE and ECCA constitute a basic block of our method to get enhanced distillation block. By using general information distillation, we integrate EADB to construct our form network. Next is our experiment. First, we test the effectiveness of MDSA. It is clear that when increase multiple level dispersion branch D5, D3, and L variance, the performance is greatly improved. We further compare dispersion attention map in ESA and MDSE. It is clear that MDSE is better at capturing key information. We also test the power of ECCA. The performance is steadily improved. Shown here is a comparison of method to other advanced lightweight super-resolution network. As shown, our method is best. And NTIRE won the first place on the model complex track in competition. Compared with the top model, our method achieved the best performance with fewer parameters and computations. Thank you for listening. If you have any question, feel free to contact us through email. Thank you.
Let's see if the outputs are connected. Okay, so if the outputs give no sign, then move to the next presentation. Okay, and we have error. For our night photography rendering challenge.
Hi everyone, my name is Igor Yashov, and I'm here to present the report on 9 photograph rendering challenge. First of all, I want to say thank you to the organizers of the conference and to organizers of this workshop, and thank you for the opportunity to organize this challenge. Our team is consist of mainly of scientific inquiry of Institute for Information Translation Problems, but also colleagues from Croatia and from company Gideon Brothers. I also want to emphasize here Alina Shutova. He is the main soul and contributor of this challenge. Without her, it wouldn't be so smooth and so strict. Thank you very much, Lena. Let's proceed to the classical image capturing pipeline. Usually we have as an input image, and as an output we expect to have rendered image, for example, in sRGB format. And also we know from convenient classical pipeline, which consists of steps of color correction, denoising, demosaicing, white balancing, and so on and so forth. The deal is that usually these steps rely on the most common cases, daylight scenarios, indoor scenarios, and it's hard to tune such type of pipeline for night cases, and let's understand why. First of all, we cannot rely anymore on dominant single light source in the scene. We have many light sources, small one, but all of them affect significantly on the observed scene. Also, we should somehow change photo finishing procedure, as they might not be appropriate for night photos. Also, we cannot rely on
human vision system models, because most of them have been derived for colorimetric conditions, which is usually normal condition with normal illumination. We do not understand how our vision exactly should work in night scenario. And of course, the level of noise much higher than in daylight. And also, the final, last but not least, is that we do not have many scientific publications on this topic. That's why we need to attract attention of scientific community to somehow solve this problem. If we will turn back to the pipeline, we will see that the classical steps, such as denoising, noise reduction, white balancing, exposure, changing, and image enhancement somehow should be changed in accordance with this scenario. What was the challenge about for participants? Each participant has been provided by input raw image, and his role was to develop an algorithm which generate fine or rendered sRGB images, which should be the most pleasant, as pleasant as possible. The question is how to evaluate the level of pleasantness, the level of beauty. The answer, there is no ground truth, and we do not have a single answer for this question. We should conduct or human studies, massive user studies, or we should ask professionals. That's that we have done in scope of this challenge. From one side, we have user study, from other side, we have professional photographer. And according to our timeline, at each leaderboard, when participants submitted their correction of new bunch of images, we have evaluated them using user studies and using professional opinion with help of professional. Final rankings have been performed using our own internal evaluation. We have launched solutions by ourselves using provided Docker files with hidden test data to provide purity of this research. For user study this time, we have used platform Tolaka, and I also say thank you very much for sponsorship to them also. This is almost the same platform as Mechanical Turk for automatic data annotation, and on this platform we have prepared environment to conduct user study as depicted on the left part of the slide. You can see the screen presented to the user. His goal was to choose left or the right image, which is the better one, which is the more beautiful. We presented this particular pair, for at least 15 users, and each image pair among all solutions have been evaluated in this manner. The question is it stable, is it good or not? This is a very hard and long question, but I should slightly mention that we have launched many times the same study and see that correlation between scores of first and the second launch is very high. That is promising. Currently, we are working on the publication to evaluate statistical stability of this type. We now are sure that it's working pretty well. For professional evaluation, we have involved Richard Collins. He's agreed to be judged this year, and he's very experienced, especially in the critical analysis of different photographs, and he's a judge in landscape photograph year competition. His usually feedback after each leaderboard was a recommendation to particular team how to improve their solution to have higher rank according to him. He have also provided some illustration of his criteria. For example, this is very important to have white snow. If we have exactly white object, we are expected them to be white. Also, dark sky should be noiseless. It's very important because noise is very noticeable on the flat regions. and colorful objects should be punchy enough, should be saturated enough to be attractive to the users. In our challenge this year, about 50 teams have been participated, 50 registration, but only 9 of them finished and submitted final solutions. And here they are. This team from Italy, from University of Bokeh, from Bokeh Technology, Xiaomi, Samsung, from Turkey, also colleagues from Olive Networks, University of Würzburg, and colleagues from Stanford and University of Google. Let's talk about the results. According to our people's choice, so according to user studies, we can see the following ranking. The first place have IVL team from Italy, and second team from Bokeh Technology, and the third place is Xiaomi. But according to photographer's choice, we have at the first place Xiaomi, the same second place, and on the third place for IVL team. So the order is vice versa. Let's analyze them in general. We can see the green lines, all lines connects the same team, but between different nomination. So here we can see the structure that actually ranking is close enough, but we have some outliers here. That's why Spearman correlation this year is not so high. I should mention that previous year it was much higher, and it still means that there's some dependence between professional aesthetics and people's face aesthetics. So this type of study, like study using Tolika, has good potential to be used for industry. Now let's look at results. I want to spend some time of you to prepare your eyes. Let's see the results. Here we can see scene number 1. I have 3 winners here. From the left side, you can see the winner according to Tolika, and from the right side, according to professional. Interesting here is to look at the left and the right image in details, and I will switch between them to emphasize the difference. We can see really different working with details, and you can see the results of team of Xiaomi provide much more details and reduce the noise in the sky. Let's see another example. Another example from a wide scene with high amount of distances, and we can see here also interesting results that solution from Xiaomi is very pleasant in general, but when we compare it with IVL, we can see that it's much in close scene more colorimetric correct, because we have gray road to be neutral, while here is not like that. And according to Tolika, the second image here been most preferred. Okay, now we have seen some experience on this image. Be aware, I will go to the right slide again, and I want to summarize my speech. First of all, many thanks to all participants of this challenge. The good news for us that user study worked well and really correlated with professional opinion. Many thanks to Richard Collins for his help and for his expertise. And we hope and plan to organize this challenge again. But next time we plan to restrict the limit of computational resources. Thank you very much for your attention. I'm ready for your questions.
So this was the presentation, and I will this one. online. So if you have questions. So no questions. Then we are proceeding with the presentation from one of the winners of this challenge.
Hello everyone, my name is Simone Zini, a postdoc researcher from the University of Milano Bicocca, and I'm here today to present the work of me and my colleague entitled Back to the Future, a night photography rendering ISP without deep learning. Our proposal is a night imaging specific pipeline made of no processing step with a shallow structure and a low number of parameters to be tuned. The overall pipeline is basically divided into parts. We have a camera color space part where we are working on raw data directly, and there is a second part which is more complex, which works on sRGB color space. The main characteristics of our solution are the fact that the entire pipeline is known, so each processing step is a known step which can be changed at any point. It's a shallow structure and the number of parameters is low, so with respect to neural network we are only dealing with, we will see 12 parameters in total. The overall pipeline is divided into two steps. We have a first group of operation which is called raw processing, which operates in camera color space, and here we have black and white level normalization, dehazing, a first out-white balancing operation, and a transformation to sRGB. The second part operates in sRGB color space and is a collection of algorithms specifically chosen for the task of processing night images. The first operation done is the denoising operation, which performs differently on luminance and chrominance components of the image, as you can see, by applying the same kind of denoising operation but with different strength on details and on the color information inside of the image, leading to better image in terms of final result with respect to operating a denoising procedure directly over the RGB color space. Next, there is the contrast correction block, which is a combination of 5 different algorithms for contrast correction and saturation enhancement, and in general for the enhancement of the aesthetic of the overall image. We start with the local contrast correction enhancement, which is an algorithm from Scatini et al., which locally enhances the overall brightness over the image. This algorithm operates differently in a bright area and dark area of the image, trying to enhance the overall brightness and aesthetic of the entire image. Following, we have 2 operations for general contrast enhancement. So we have a contrast gain around the mean value of the image, and followed by an S-curve function defined from the paper of Kang et al. From 2010, defined as you can see here in the slide. Those 2 operations have the main objective of enhancing the contrast operation after the brightening operation, and to start to give an image an overall good aesthetic without taking in consideration the specific situation or the specific content of the image at this point of the pipeline. Then an histogram stretching operation is performed, which depends on the 0.01 percentile and the 99.99 percentile of the image, and the second value change in relation to the state of the image, in the sense that if the image is too dark, is then selected another percentile value in order to perform the histogram stretching operation. Finally, the last algorithm of the contrast enhancement block is the conditional contrast correction, which takes in consideration the state of the image at that point of the pipeline, and basically if an image is too dark, a second S-curve operation is adopted in order to brighten the image, and otherwise if the image is too bright, a gamma correction is used to darken the image in order to make it look more natural, more like a night scene. Then the pipeline ends with a sharpening operation performed with an unsharp masking algorithm, and then the last step is a final out-white balancing performed using the grayness index algorithm, and which is used in order to make images look more natural and in order to remove the yellowish aesthetic given by the application of the gray word algorithm only. We end up with a pipeline with only 12 parameters that can be tuned with different preferences, and which have been in this case
chosen by hand, by looking at the dataset, by analyzing the images from the challenge, and by dividing the images in different clusters in order to choose the different thresholds. Following, there are some results, an image that has been processed, and so we have the input image and the final output image, and then there are some comparison with the previous state of the art from the last year challenge. In particular, we have our older method and the one from the winner of the last year competition. So thank you very much for your attention. If you have any question or you want to contact us, please feel free to use our emails here reported. Thank you again for your attention.
Okay, so this was the presentation, and I think that we have the author online. Someone. So, yeah, Simon.
Yeah, I'm online. Can you hear me?
Yes, I can hear you. Okay, so if there are questions, the first author is here. So one question from my side.
Yeah, sure.
As far as I understand, your solution is pretty much involving you in the loop. You designed all the steps on the way, right?
Yeah, sure. It's correct.
Okay, so somehow this means that you as an expert, you are acting the learning factor, while the other side to optimize just an objective and fit some model parameters, right?
Yeah, let's say that the idea here is basically to try to find a sort of a baseline made by hand in a certain sense by, okay, let's say expert, but none of us, none of the people in my team is a, let's say, a expert photographer. Maybe some of us are amateurs, but definitely not professionals. And it is to find a way to define a new sort of a baseline for then maybe some optimization algorithm or for next step in this field of research, let's say, because as being presented by the organizer of the challenge, basically the current baseline in image processing from raw to final 8-bit output are basically pipelines that are designed specifically for daytime scenes. So here the idea was, okay, let's start without trying to optimize a big model with tons of parameters, which are kind of hard to tune while not having data by hand, in the sense that, as you have seen here, basically the data are only the input images and some images processed by a baseline, which is not optimal at all. So the idea was to try to keep it simple in a certain sense. So try to exploit the experience in order to choose a set of algorithms that could potentially work in this kind of setup, and try to use less parameters as possible in order to have something which is kind of small and potentially can be optimized by some other kind of algorithm in the future, let's say.
Okay, so another question that I have for you. So how you'll improve?
Sorry, I didn't get the question.
I think that you already are thinking how to improve your current solution. So will you add some learned components, or you are thinking to go into a more complex handcrafted design?
Let's say that this could be the start for multiples. Okay, there could be multiple ways. Of course, the most interesting one, in my opinion, is that at this point, since we have made this sort of a baseline with very few parameters, the idea could be to try to find a way to add a component, maybe in sort of an unsupervised or semi-supervised way, to optimize those parameters in those scenarios where we don't have images, or at least where we don't have like one correct image for the specific input. So yeah, of course, one possible way that we want to study is the application of the learning approaches in order to optimize those sort of pipelines, but also at the same time
keeping it in a handcrafted way, in the sense that this is one possible solution that we have studied in this specific configuration with let's say this setup of people that give us a sort of a feedback during the various steps of the challenge. So of course, studying the entire architecture in a more handcrafted way could maybe help in try to figure out maybe the flows in this pipeline, flows in this architecture, and try to find a way if maybe there are components that can be optimized automatically in order to change those structures, those architecture, etc. But this is another road which is kind of long, let's say. Okay, thank you, and congrats for your. Thank you very much for the questions.
Okay, so now let's move to the next talk. We have the invited speaker, Professor Shaya.
We can. Sure. One is fine. Thank you for thank you. Okay. Okay, question. All right, thank you. Okay, so today I'm going to talk about our recent work on how to synthesize image and videos. And so specifically, I will talk about our recent work on how to synthesize image directly from data or from large language model. So, and yeah, so mainly I'll focus on two recent work. One is that we will present on Wednesday. The other one is at the ICML. Over the year, we work on different parts of image synthesis, on style transfer, image to image translation, or different ways to synthesize image with different assumptions. And I will also briefly touch on our recent work on video synthesis. Again, so I'll start with our recent work on how to learn to synthesize image under limited data. So as we know, there are a lot of good work on GAN model that you can synthesize good result, but the assumption is that you have a lot of data. So for example, when you have only 10% of data, then for big GAN, even with data augmentation, then we have tried that, you won't be able to train the model very well. And so what I'm going to describe is that our recent work on how to add one regularizer such that with same amount of data, even with 10% of data, you are still able to train a good model. And this regularization term can be applied to other existing models. So this is just one snapshot of the data we have, on faces and on scenes and on different modality. But the point is that we always have a limited amount of data. So again, so this is a problem. So then if you look at the big GAN, then this is what we have. If you use all the data to train it, you will do quite well. But if you only use 10% or 15%, then it starts to degrade significantly. And here's FID, so lower is better. So one way to address this issue is to use data augmentation. And there are several ways to do that. And so we also have one way to do that with Remax. And then you can also look into that. And on the other hand, you can here today I'm going to talk about how to use regularizer so that you can add to existing model and you can train the model well
under limited data. So this is what we have with big gun. With it will die nicely, at least it will not die so drastically. And this is a very simple term actually. I mean, you can add on to any existing model. So the main idea is this. So what we do is that we look at a predictor. Well, this is a GAN model, so there's a generator, there's a discriminator, and for any input there is a prediction score. So we keep the average, moving average of the real data and the fake data. So we compute the moving average, and this gamma here is just a decay term. So basically, we're just computing for given a fake data point or a real data, what's the prediction score? And we keep the exponential. We keep a moving average. Then we compute. This is a bit tricky. So we compute the L2 distance of the moving average with respect to the current prediction of real data and fake data. So this, at first glance, this looks a bit weird in the sense that, you have, for any GAN model, what you want to do is when you have fake data, you want to discriminate as much as you can, right? But this, when we add this term, it's like you put two things together because one term is a moving average of real data, and we subtract that with fake data, and the other one is vice versa. So at first glance, it looks a bit odd, okay? But in the paper, we show that why it makes sense and how it would be able to generalize to F convergence. So this is the term we're adding, and that's it. And now you can add this term to any discrimination, any loss you like, Wassler's GAN or any loss you like, or logistic or hinge loss, as you like. And yeah, so that's that. And again, in the paper we show that why this will perform well, and it can generalize well to F convergence. And empirically, I will show you some results. So this is what we have. So then in the paper we show that it can be generalized and to a new F divergence measure, and we call it Lagrange divergence. And it basically shows here there are different kind of distance you can use to measure distribution distance, but then here this one generalizes better. Okay, so here are some empirical results. So we use that with big GAN and star GAN, and we train with different amount of data. So with 20% of data, then we would be able to train the model converge very well. If you look at big GAN here, the model doesn't converge that well because you're still missing some parts, like bird, head, and so on and so forth. And this one, with this regularization term, you can have a better result. And yeah, this is another thing. So even with the full amount of data, if you use this regularization term, this also performs well, but it performs better when you have a limited amount of data. Okay, and yeah, so so then again, we apply that to different model. So this is 10% of data, and with big GAN, it still performs pretty well. And this is 25%, well, different number of data points. And here, this is a result. We only have 100 image, and we still are able to train a model for Obama. I mean, this is pretty good because usually you need a large amount of data in order to train a good model, but we only use 100 image, and we are able to train StarGAN V2 from scratch, not fine tuning. We start from scratch. Okay, so that's one work that we presented in CPR 2 years ago, and then so I'm going to talk about our recent work on augmentation. So the augmentation, the problem is very simple. So basically, you have a small image, you want to extend that in different ways. So you can expand that this direction or the other direction. And this problem has been posed as an image-to-image translation. So there are two other prior work. What they do basically is they pose the same problem as image translation. So you mask out some parts and then ask the model to synthesize the missing parts. The problem is usually you have a very, it works well to a certain extent, but when you extend further, then you start to see some repetitive pattern or simple extension. For example, here you will see that, you start with this image, you extend it, you start to see some repetitive pattern and all very simple extension. So this is what we want to address. So there are two methods that we developed. One is called in and out. The other one is called infinity GAN. So this one is very straightforward. Basically, we use GAN immersion for augmenting. So for those guys from US, you know in and out burger, but my student is a big fan of that. So anyway, so the problem, so what we do is, okay, so you have image like this, then we want to first train an unconditional GAN, and so that given an input, you find the latent code. And then once you find the closest latent code, then you can use retrain model, retrain latent code so that you can use that for synthesis. I'll explain that in more detail. And once you have that, then you will be able to synthesize different way you like. It's like in old days. I'm sure you are familiar with PCA eigenface. You have except this is inversion, not projection. But in old days, you have data you project onto latent space. You can use any manifold or just subspace method as you like, and you can traverse a latent space and use that for tracking, for recognition, for synthesis, all that. Okay. The idea is similar. So here, what we do is during training. So there are two setups. One is categorical setting, the other was non-categorical, meaning that whether you know the class label or not. Okay, so let's just say you don't have any class label. And then what we do is that we train a GAN, unconditional GAN based on coordinates. So this is based on my student prior work. So using a 2x2 image as example, you have a coordinate. Then you can synthesize, then based on that, then you train the GAN model to synthesize patches and you put them together, thereby you get the image. And so this is what you train without any class label. And with class label, you just add in. This is very typical as people often do in image-to-image translation. You add another class label there. Now, during the inference time, what you do is that you give an image like this, then you find the latent code, and you find the closest latent code, and then you use that to synthesize the image, and that's pretty much it. And now I'll tell you how the prior or the regularization we had in order to learn the latent space. So again, so the best model is based on a patch-based GAN. So we use Diagon 2 plus Coco GAN, my students' prior work. So then based on the training data, we have to add in some more regularization in order to train well. We add in a few losses, and those are very typical. And we also use that in our prior image-to-image translation work. So, for example, here is one that you have training data. You have to compute Monocular distance in the latent space, so that you want to make sure the latent code doesn't deviate from the mean too much. And we add in this our prior work in image translation, where we add in we call most sticking loss, because for GAN model, one problem is a mode collapse. So here, what we want to do is that we want to encourage that once you have two latent code, the synthesized image will be as different as possible. I mean, for all-timer, for the feature linear discriminant analysis, if you are familiar with that, that's a similar idea. So we add in that, and the other one is also commonly used for latent code. We want two consecutive latent code to be somewhat different, so that we can synthesize image with diverse outputs. Okay, and then again for the categorical part, we just like any image translation model, we add in one more code, the class label for that. so that when you synthesize, you know which data set or which latent space you want to use. Okay, so here are some results. So here are the inputs, and then we can synthesize results with diverse outputs, and they are they have different outputs, and they are not at least they are not as repetitive as the others. And here is again is input. You can synthesize output with diversity. Likewise, here this input, then you can synthesize, or church, you can have synthesized with different results. And this is without categorical, without any labels. And with label, you can do better. So, and then you can synthesize, you can outpan image in different ways, left to right, right to left, up to down, or from one quadrant to all the others. Or you can also use a region for outpan. And if you have labels, then say you have an input like this, you have a 4 here, and then you want to add in some labels such as waterfall or rock or mountain, then you can synthesize contents with different latent space and then with different results. And likewise here, you have an input like this, and you add in some tower, mountain, tree with different input, then you will have different results. And we can also do a panorama translation. So you can start from one end to the other, or from middle to, you can extend in any direction. Yeah, for this prior, so this just goes to show that we have to add in some more prior in the latent space. Otherwise, you won't have a very good result. That's it. And so the follow-up of this work is called infinity GAN. So basically what it is that we find there are some issues with in and out work, which I'll show you. And then we added, we changed that and have better results. So again, this is based on my student prior work on Coco GAN. But this is a patch-based GAN model. Basically, once you have coordinate, then you can query and then synthesize different results, and then you can put them together, and then you can have the synthesized outputs. So in this model, this is basically a GAN model. So there are generator and discriminator. So in the generator, we have 2 modules. One is called, okay. Oh yeah, so we use this to extend to find the patches and then put different patches together. So, and we can extend in different ways. So in the generator, there are 2 functions. One is called structural synthesizer, the other one is textual synthesizer. And the first one is basically just allow us to query, so to query a coordinate to find some latent code in the feature space. And later on, we use the latent code in the feature space to synthesize the actual output. And in order to make sure everything will be consistent, we add in one global latent code so that all the synthesized result, because you use patch by patch, so you want to add some more constraints such that the synthesized result will respect certain code. So this global latent code is fed into both discriminator and generator. And then given the coordinate, then we add in some local perturbation. So to add some more local variation. So once we have a coordinate, then we can ask this function to synthesize the output in the feature space. And we send this intermediate result to the textual synthesizer to synthesize the actual output. And then we can put them together. And then we can extend in different ways. So here are some, so let me show you some results. So, this is a padding, so I will skip this. So this is way too detailed. I thought I hide this, so don't worry about it. Okay? All right, so yeah, and then we have discriminator. This is similar to typical GAN model. So basically, you just have data set and you patch, and then you just want to synthesize that and see whether it's real or fake based on patches. Okay, so again, this padding, this should not be here. These are way too much detail. Okay, so forget about that. Okay, so now, so what we do is that you given a global latent code, then you can query the coordinate, and then you can synthesize patches, and then you put them together. So with one global latent code, you can do that, and you can also use that with multiple latent code. And so this is a large image purely generated based on noise. And if you have a one latent code, you can synthesize that, and with another latent code, you can synthesize different patches, and you can put them together and have a larger image like this. And each patch is actually this is 2K by 1K. Okay. And so yeah, so these are some of the comparisons. So we compare with CoreGAN, ThinGAN, which received Best Paper Award in ICCB 2019, I believe. And then we compare with StarGAN with extension. So you can see that most of them will not be able to scale up. You cannot even fit in the memory. And we can synthesize with different diverse outputs in different direction. So you can, in terms of structure or in terms of texture, you can synthesize, you can control that so that you can have a diverse output. And this is 2K by 2K. And this is 256 by almost 10K, and it's a long image. We just show that row by row. And the code is variable, so you are welcome to try that. So this one is basically, we just it basically use global and local coordinate, and then there is a structure synthesizer and texture synthesizer. We separate that in order to control the content with local variation. So we use this for all painting and compare with in and out, which I just presented a few minutes ago. Okay, so yeah, okay, let me show the differences. Yeah, so here I just you can have different outputs. Again, we usually like to synthesize result with diverse outputs. So here are some comparison with the recent work, boundless NS output in and out or prior work. Even though we can synthesize better result, but if you extend further, you will still see some repetitive pattern in the end. But with this infinity GAN, you would this problem be addressed. And you can do in between, given two images, you find the latent code, and then you can synthesize that. And yes, it's it doesn't really matter about the distance. Okay. Yeah. So these are just some results. Okay. Yeah. So this one performs better than the previous one because we have better control of the structure and texture. And yeah, again, the code is variable. You're welcome to try that. And the thing is, we can try that with one GPU. So it's pretty interesting. And so then there is another work from this work. We find out there is an important issue about positional encoding. So my student Hubert, he has a recent paper on that to analyze the importance of position encoding, and it will create some problem in many synthesis work models. So please check out our ICML paper. And he also extended. So I was talking about infinity GAN in 2D. So recently he extended to 3D. So for GAN noise, you can synthesize a building or polygon first, and then synthesize texture. So this this work in review. So anyway, and we will make it code variable soon. Okay, so I'll just briefly talk about our work on video synthesis because and I don't have time to go over that. So and there's one work that we did on dancing to music. So based on music, how do you can think like music to video. Given if you hear some music like this, Oh, I don't have music. Sorry. Or like this. Anyway, so when you there is echo. So when you hear some music, you will be able to some bit. You will see some different dance pattern, and then we have one method to synthesize different dances, and then from music to skeleton first, and then so you can mix different dance style together, and then from skeleton you will be able to synthesize real human. Again, and like this. Anyway, you can check out this paper, okay? And there are some other work. I don't have time to go over that. So I will move on to talk about our recent work on Muse and also Magvid. So skip this. Okay, yeah. So I'll use the last 10 minutes to talk about our work on Magvid, which Adrian will present on Wednesday. And so this one is pretty interesting. So basically, this is what our recent result on how to synthesize the videos. And so it has real-time, well, it has real-time, quote-unquote, real-time performance. But I'll show you some number first, okay? So you can see that, okay? So in terms of quality, it increased a lot. So this is one model, and then we can apply that for 10 tasks. And on different data set, we can have a significant improvement on video synthesis. And in terms of efficiency, it's also very efficient because there's a task that's on 3D HTCAN, and it's about coding. And then basically this our compression rate is much better. So this is about inference. Also on GPU or on TPU, it has a real-time performance. Again, he will present this on Wednesday. I'll just give you a preview on this. Okay, so and then we can apply this for frame prediction. We can apply this for frame interpolation, outpainting, inpainting, or just straight up sequence smoothing. Okay, so the idea, so basically there are two stages. One, the first stage is to train the code book. So we use these videos. We have a 3D spatial temporal colorization. So I'll show you in a bit. So we extend a task with a deeper network so that we can have discrete tokenizer. We can have discrete tokens. And then once we have that, then for different tasks, we just mask. For different tasks, it just depends on the input. Then you have a certain condition. You mask out some parts and force the model to learn that. This is very similar to mask autoencoder, the idea. So obviously this is, this basically what I want to tell you is this is based on tasks, and then we have much deeper network, and we have up and down sampling modules, and so it performs better. Okay, so with this 3D tokenizer, then we can have a much better compression rate. So given a video, this is a raw video from YouTube, and then we can have up to 600 times of compression. And with this, we can do a lot of stuff already. And yeah, so this is in terms of length, in terms of size and time. So with this tokenizer, with this 3D token, then we are able to do all video tasks. Say if you want to do straight up synthesis, you just mask out everything and then you just force the model to learn that. Well, you basically for this basically are some condition. Okay, so for example, if you want to do prediction, you use the first frame as condition and then ask model to predict the following frame. And likewise, this one you have some condition. This is outpainting, so you have some condition, you have some input as a condition, and then you force the model to learn the others, and likewise for the others. So the main thing here is that again we have some condition token, and we have some Once you, and that will be the task. And then we mask out some part of image and force the model to predict the missing parts. And for different tasks, we design different masking schemes. And so that you force the model to learn. And again, there are 10 tasks in this model. So we also have scheme to sample that. We have to jump between as a model to learn different tasks alternatively. Okay, I'll skip that. And for detail, please come to his talk on Wednesday. And he also has a poster. And okay, so here are some. So then this is coding. So during the inference time, what we do is that you're given some. This is the condition part, and then we start to predict. There is a procedure that we need to do sampling. So we start to predict some missing parts, and gradually predict more. So these are blue dots are the predicted one. So you may think that, okay, why don't you just predict everything in one shot? We tried that, but it didn't work well. So then we come up with a great progressive sampling scheme so that we decode and predict the missing codes gradually. And this one performs better. And okay, so I think I use all the time. How much? Okay, so I'll skip this. Okay, I'll skip some. Again, for this result, you just look up and then, but here are some results. It's pretty interesting, pretty cool. See the result on Wednesday, please. And yeah, we can also use this for painting, for video. And yeah, for video, not for image. And you can do frame prediction, interpolation, and all that. 15 frame. I mean, not long. We are working on a long video, but so far we can predict 15 frame also. Okay, I'll skip this. All right, so skip it. Okay, I'll just use 2 minutes to describe our recent work on Muse. So this is a text to image generation. So this we're going to present with ICML. So this is a text to image. So far I've been talking about noise to image or noise to video. So this one text based. So basically, this is also based on MacVic work. So these two work are based on one prior work by Huiwen. So there are a lot of models recently. DALL-E 2, Midjourney, Imagine, Party, Stable Diffusion. The problem with those things will be some of them are auto-regressive model or some of them are diffusion based. So the problem is that they are usually slow. It takes quite a while to synthesize image. And so so diffusion model performs better, but then it's still slow. And stable diffusion with latent diffusion model, it performs better and it performs a bit faster, but there is still some scaling problem. So this is why we developed this model. This is pretty fast and it has it's like high fidelity images. It's also flexible. So the key idea is this. Okay, I'll just tell you this, and then there are two. So this is very similar to the work that I just described. In fact, these two this work were carried out at the same time. So the mask is Huiwen's prior work, and basically you learn a quantizer and you mask some parts and force the model to learn. And so this is also the thing that I just described. So if you want to synthesize the image and then you start to ask model to predict some parts, for example, this part, and then you gradually ask the model to synthesize to predict other parts. And again, there's a procedure we need to use in order to synthesize all the codes, not at one shot, because it doesn't perform that well. And if you do that progressively, it performs better. And so I'll skip that. So okay, so this is one slide that you can see. Okay, why this one performs better. So for all the other auto-regression part, you have to synthesize previous parts, and then you like imagine you have to predict or synthesize previous location before you predict next one. But for this one, we have non-auto-regressive model, and you can predict all the parts at in parallel. Okay, so yeah, so I use all my time. So basically, this is the work we are going to present on ICML, and I'll give the slides to Radu, and if you want to see that, please take a look at that. Okay, so that's all. Yeah, so these are some of the results we compare with Imagine and DALL-E 2, and it basically attend to the text much better than the other. Say number of books and also details. And yeah, so I'll skip this. And okay, this one also allow us to do imprinting without this one with masking. This one we can also do we can do editing without mask. So basically you can use text with different prompts, you will synthesize different result. And you can also change some parts like this with text. You don't need to use any mask to do that. Okay, so that's all I have. I want to thank all the collaborators and students for that. And yeah, for details, please check out people. Thank you.
I see that somehow some of the solutions, and I saw also a couple of slides there. On one of them was saying relational to the diffusion models. So, for example, when you are doing the sampling or to do the outpainting or creating some contents, you are going in a gradual manner. Is somehow similar with the diffusion process.
Well, the diffusion basically is progressive, right? You have to these steps, right? So that's why it's a bit slow, right? And then, so what we're saying is, for imaging, so basically it's based on transformer, but it is like transformer, sequence to sequence. So it's sequential now, and they use that to do synthesis, which is fine, and then which has good result. But the problem is slow. It's sequential. So what we do here is that you don't need auto-regressive model. You can just, but then again, you may think, okay, if it's a non-auto-regressive, why don't you just synthesize the result in one shot? In theory, you can do that. In reality, it doesn't perform well. So we force the models to synthesize some parts, to synthesize a few position first, and then based on that to do the follow-up of prediction. But then usually just a few steps. We don't need a lot of steps. So this is the part that we try out and it works well. So again, it just what it is. So this is the detail that you can check out paper. So basically here you predict one, and the next one you predict a few, and then predict more, and then there's a procedure for that. So yeah.
But here is the proof that actually there is light.
Yeah, so you're right. So basically, we think this transformer-based performs pretty well, but then we also find out that with a different data set, the latent diffusion model or stable diffusion model performs pretty well. But for that set of data, the Muse model doesn't perform as well, but we are trying to figure out what's the secret source there. So the jury is still out, so we'll be able to tell you later. Yes. Probably. I mean, again, it's we are push the envelope, right? And I believe at some point the model will fail because you can stretch so much, right? So I won't say that, this term is, in fact, this was one of the contention issues. What do you mean by infinity? So so yeah, I agree with you. I mean, if you look very closely, I think there was still some repetitive pattern. It's just that it outperformed the other alternative. Yeah. So now, if you're talking about yeah. So I think there's certainly still room for improvement, and then you are welcome to test out the code and then play with that. I mean, the code is available. And the good thing is this was done at school, so we did not have a lot of GPU. The student used one GPU to train this and fit everything in one model. Because if you just straight up use existing model to synthesize largest image, you simply won't be able to fit that in one GPU. And when he did that, he used one Titan X GPU and he was able to do that. Data is the new oil. So it's not surprising at Google and elsewhere. It's when you talk to a lot of people in the industry, the model, usually the model is, you need to have a good model, but more importantly, you need to have good data. I mean, this is what it is. Yeah, it's possible, but we don't really model motion. I mean, so yeah, I mean, yes. So that's where you perturb the latent code a little bit, but if you, I mean, I think you certainly can use. You can do that. We just didn't do much on that. So. Yeah. Yes. So if for old timer, you probably have seen dynamic texture, all those kind of stuff. Latent space, if you traverse that, I mean, this is why I mentioned about tracking and synthesis, because if you can find some paths, latent space, then usually you can do a lot of stuff. We just didn't do that yet. But good question. I don't know. I had to ask my student. I don't know the detail, but he went on to do different things, but we didn't. Wait. So are you talking about Infinity Gun or talking about the latest? Muse or okay. Or magnet. Okay. So for Muse, so there is a super resolution module, and we only go up to 1K by 1K. So you are right. We didn't go up to those things. Yeah. And for megabit, it's also not 1K to 1. Because again, we didn't go with that. So good question. Maybe next one. Okay. Yeah. Yeah. So. Well, after all, it's all based on data, right? You learn some pattern from the data, and we add some perturbation. And yes, you can have slight variation, but that's the best you can do. And then let's also add some prior so that you perturb in different ways. But I agree. I mean, but the main thing is that everything is like on drug, right? So everything is synthesized. So it's not it's not that realistic yet, but notice that this everything is synthesized.
will generate more and more details.
Yes, but that's condition, right? So
Yeah, the conditional, but we
Yeah.
don't do it.
Yeah, but this is we don't condition anything. It's only condition on training data. But otherwise, it's only condition. Oh yeah, it's still condition, but it's based on the input and then find latent code and do that. But yeah, if you have more information about yeah, if you add some more knowledge or some more fire, then probably you can do that. So thank you. I'll send you a slide.
Okay, so yeah, I think this is the last talk of today and also the workshop. So for those that are here in person, we still have another session of posters. So if there's still time, we can go and chat at the posters. Otherwise, thank you all for staying till the end of the workshop. Thank you to the participants, also to the participants in the challenges, to the authors, to those that submitted and got their papers accepted as well, and also to all the program committee organizers, and yeah, my students that helped me at least. I think that now I'm having more pictures than my entire life. Okay, so I'm getting exposed. Okay. Yes. Yes. Okay, so thank you all, and hope to see you again next year or at the next two workshops that we are organizing for challenges. Okay, so bye-bye.
Thank you.